So very good morning to all. Uh, before getting into the session, so make sure that my voice is audible to you. So and can you, I think you can able to see the screen there. If in case between the presentation, if the screen is not visible to you, or if the voice is not audible, or it's maybe disturbing, means just let me know so that I can able to clear you, so that you can able to get whatever I am trying to put forward there. So today's presentation will be based on the Internet of Things, or we could say now we could say industrial Internet of Things, and one step ahead we can able to say Industry 4.0. So these are the things we are going to touch upon in this presentation, and how we can able to implement this particular one, maybe in the academic side, or how we can able to start doing the necessary things to achieve and industrial IoT, or maybe in industry 4.0, how we can able to educate the students and prepare the students in these domains there. So that's what the presentation. So I will be giving you overview about what exactly this industrial Internet of Things, and what are the necessary things we require to achieve this particular one, and what is the platform we are going to use it here. So, and we are going to focus on industry 4.0 also. So this is the overall picture of this today's presentation. So I am Balaji. I am working as associate manager in EduTech India. So EduTech India has multiple verticals will be available. So basically, we are the 30-year-old company, and we will be doing multiple activities in setting up the labs, the technological labs and innovation labs in the academic institutions, where we can able to prepare the students for next next technology over there. So we are doing this we are doing these services in 30 plus years we are doing this particular one, and we have offices in 7 countries there. So in India itself we have a in 7 cities, in 7 major cities we have offices will be available. So I am joining from Chennai, and I'm joining from Chennai here. Apart from, we have offices in Bangalore, Mumbai, Kolkata. We have multiple offices there around the India. We have multiple clients available. Majorly we will be working with the top tier IITs, NITs, and private universities, top tier private universities. We are providing solutions in traditional lab equipments, and as well as the emerging technologies there. So basically my background, so I will be experienced in LabVIEW platform. So with the LabVIEW platform, I'm just working on a data acquisition side, so and and IoT part. So after this particular one, so now technology is emerging there. So we are just talking about the artificial intelligence, machine learning, and AR and VR. So these are the places I'm just working, and I'm just experiencing these domains over there. So the areas what EduTech we are working here means, we are working in 4 verticals here. One will be K-12 division, vocational. K-12 and STEM education will be for school students. So we'll be doing a support, and we'll be doing a services for K-12 and starting from school education is there. And for the higher education, so for higher education we just collaborated with top tier universities there, and as well as the NITs and IITs there. Okay, so there we are giving a solutions in teaching. We are giving a solutions there and setting up the lab system kits available. So with that, we are going to provide a hands-on experience in these places there. So coming into this higher education side, in higher education side, whatever the necessary things required this particular time, we are just providing solutions for all the areas there. So now the buzzword what we are talking here means, so AI/ML, artificial intelligence, machine learning we are talking there. Then we are talking about the AR, and we are talking about there. So how we can able to implement these technologies there, and it's of course IoT will be also comes into picture there. The blockchain technology, multiple things will be associated with this with this point now. So we are providing the solutions in all the domains there. So this is a brief introduction about what we are doing there, what about our company, and what we are doing here. Okay, so coming into agenda for the today's presentation will be, so we're just going to refresh about the history of the IoT. No, I'm not going to bore you with these things. Okay, so starting with a small history, what exactly IoT and Industry 4.0 how it is evolved. So IoT is there, but how it is transitioning and how we are talking as a industry 4.0, that we are going to talk as in simple words. Then how we are going to implement this industrial IoT. So what are the ways available and what are the prerequisite we require to implement this industrial IoT, and what is the application software we require, the platform we require to realize these things there. So last will be we are going to see the demonstration there. So the demonstration has been split into two different things. So one will be we are going to discuss about the first demonstration will be you are seeing on the screen in the left side, discrete IIoT system with NI Myrio. So we are going to discuss about the major general things we are going to discuss about that, but how it is getting compatible with one academic side. So if anybody wants to get into this IoT platform means, so how we can able to prepare for particular one, and how we can able to realize, okay, how I can able to send the data to the cloud, how I can able to retrieve the data from the cloud, what kind of cloud he is going to use, the protocols he is going to use it there, that we are going to talk it, and we are going to demonstrate the same thing there. And the second demonstration will be, so I have just in the title itself I have told industrial IoT, along with we are going to focus on industry 4.0. So whereas industry 4.0 we are talking about means, so it has to be a complete the process should be there. So process should be there means, so it has a warehouse should be there, so and it has to make a warehouse should be there, then it has to scan all those things, so then it has to do all the necessary things it has to do over there. So for that, what are the things we require and how we are going to implement that. So for this demonstration, so my team from Bangalore, so they have just joined in the meeting there. So on the later part of the, maybe it's the second part of the webinar, so we will be demonstrating you how this is working there. So the lab we have set up in our Bangalore office there, so my team will be giving the demonstration on the same thing. So these two things we are going to discuss and discuss in this overall presentation there. So just I have told about just going back to the history that how it is transformed into industry 4.0 from IoT to how it is transformed into industry 4.0. So first of all, we want to understand what exactly IoT there. So we know IoT means, so the data will be there. So data we are going to communicate, or we are going to share the data over the internet or over the cloud we are going to implement there. But what we require, so the data I am going to share means, what I am going to require here means, so basically I am going to require the sensors. So any sensors I will be required there, and it has some processing capability, so that I will be doing that processing capability I may do it on the software side, or I can able to do it on the cloud itself, so that I can able to go for cloud computing also. So the data, the cloud itself will take us some we're going to mention some rules over that. Based on the rules we are giving in the cloud, so it is going to take a necessary action that will be reflected on our system. So multiple technology will be converging here to make a proper industry 4.0 here. Okay, so coming into this particular, the history here started with the industry 1.0. So where majorly we have utilized the manpower there, so we don't have any machines that particular time. So machines and all available there, but majorly the manpower is very important, and this is given majorly to the manpower there. So we started working with generating the power and steam, how it is getting generated, how we are going to transport there. But later on this 1.0 revolution only identified, so how we are going to transport this one. So we are doing the production, we are doing that, so how we are going to transport this particular one, so that it will be transformed into the next stage called 2.0. There we have a there we have a multiple trucks will be comes into picture, the transportation will comes into picture there. So with the help of the transportation, the available transport in the particular time, so we just started the whatever we are producing here, the production can be given to the transportation. So which in turn what happened, so we can able to see mass production, we could able to see over there. So whereas then in the 3.0, where the computer will be started into our human community there. So where a computer makes the life sometimes easier that particular time, because it's in the early stage the computers enter into the human community there, so that it makes us somewhat easier there. Still we need a manpower there, but computer is making the work easier there, so we can able to do some computing automation. The software will again comes into picture. These are the things available, so that we can able to make the process better, and we can able to club it to the previous generation of industries there. So now we are in the industry 4.0. So industry 3.0 played a major role. So to transition to the 4.0, what I felt okay, because the computer is available. If computer is available, internet is there. So through the internet and computer, we can able to converging many technologies over there. So in the similar way, the last will be we are talking about the 4.0. So the 4.0 we are telling us here cyber physical system. We can able to say, or we can able to say cloud computing. Any words we can able to say basically there. So we'll talk about this cyber physical system in the next slide. So what exactly the cyber physical system or might be the architecture will be talking about that. So this industry 4.0 only with the help of this computer and this technology, AI and machine learning, the cloud computing, these are the things will be combined here, and we can able to see the process there. Sometimes the AI is also taking a place what man will be doing that. So AI is thinking more than the particular one over that. So recently I have read some article regarding this AI. I don't know, maybe you have also come across the particular article. So the AI is giving, so whatever things we are able to type it there. So if you are giving some keyword, means it's trying to give it is trying to give some paragraph it is giving over there. So we want to write some essay over there, means the AI itself trying to provide the essay for 2 paragraph or 3 paragraphs giving over there. So these are the way this is happening over there, but it is how it is connecting to the industrial places. So we'll see. So I have talked about the cyber physical system. So in the cyber physical system, the process is starting from this particular places. So where they have a dashboard will be available. On the dashboard they are going to monitor. So what is the warehouse how much warehouse quantity will be available, so how much production is going on, so how much will be in the delivering place, so how much process will be on the conveyor. So all they are going to look it on the dashboard process here. After seeing this particular one, so the entire machines will be available. So it's going to cross every stages there. So whenever you are doing any production, so it has to go from some manual testing over there, and machine testing it has to go. And whenever we have a sorting line available, it has to sort all those things properly to to their need over there. So that's what happening in this particular place. So here we have a conveyor will be available, and it has a one checkpoint will be available there. So in this checkpoint, it's going to verify whether the process, whether the cans what we are seeing on the particular page, the cans will be going on over there. It's going to say whether the can has any defect available. If defect available, what we are going to do with the particular one. So how we are going to reiterate the particular place there. So if it crosses a checkpoint, means so it's going to the next stage here. Whereas in the next stage, maybe we have to fill the water over there. So at the exactly place we have to fill the water. So once it is done, the other person will be it again goes to the conveyor, and it's going to make a packing over there. So this is a simple example of what I'm trying with this example there. So like the way we have a multiple examples, we can able to say, suppose if you are going to manufacture one truck, means truck if you are going to manufacture, means so for manufacturing a truck we have a various stages will be available. So first we need to build the chassis there. So chassis will be the first part. We have to build the chassis over there. Once the chassis will be built, that means it goes to the next stage. There we have to make some axle, we have to make it there. Then after making the axle, we have to make the body, and we have to make the steering and all. So this will go all the process. We have to make these are things we have to make. At the last stage only we'll go for the packing, then it will delivery will be going there. So all this data will be monitored in the cloud there. So that's what very very important. All the data, whatever we are talking in the industrial place, this has to be updated on the cloud. How many trucks will be in the processing, how many trucks will be delivered, how many trucks will be on the second part processing. The second part processing means so assembling assembling over there. So these are the things we have to be ensure how we are going to display this data on the cloud. So we are just going to create a dashboard, where the dashboard, So we are going to monitor that. So based on the dashboard, if anybody wants to order something, means we can able to order that. Depends upon the process will be goes on based on our convenience we can able to make. So to do this one, what are the things we require? So we require totally three things we require. That one will be computation we require, then we require the control, and we require the communication there. So whatever the process I have told, all will be scattered one. So somewhere the computation will happen, then control will be happening there, and communication will be happening there. So we have to combine three things to make the better system there. Okay, that's what these three things will be separated, that we are taking into the, we are going to combine it over there. So computation is one part. Based on the computation, we are going to make the control there. And the computation control, how it is going to happen here means with the help of the communication there. Okay, so for example, so we are doing some we are developing some application. Let's take example, the truck example there. So I am going to make the first part where I am going to build the chassis here. So the chassis I am going to build there, how much I am going to move the conveyor, how fast the conveyor has to be moved there at the same time. So I have to fix the axle on top of that. At that time, so I need some grippers I may require there. So how I am going to take the gripper into the place. So these are things will be control part will be coming there. Computation part will be very in computation part. So we'll be giving the how fast we have to move the conveyor, the axle, the chassis we are going to move it there. So the communication, so communication will be seen in terms of how it is going to communicate with the cloud there. So you are talking with the software, you are talking there, but software and the cloud will be available. How these two things going to communicate to the cloud and to complete this system over there. So three things will be very, very important: computation, control, and last will be communication there. So these are the things we are going to discuss on the next part of the presentation there. So how we can able to communicate and how we can able to use the computation and the control part. Okay. So to implement the IoT, we require the four ways or four parts we require basically. So four parts will be very, very important, but somewhere, some point of time, we'll come across all the words over there. Okay, all the words will be come across in that. The first one will be, we are going to see about the protocols. So protocol is one of the important one. So that's why I have talked about the communication part there. Then you have a data files will be available. If you want to store the data on your local computer, or the data should be on the cloud. So how I am going to see the data on the cloud, so that we are going to see it on the data files. Then we are going to see about the web services, like a machine to machine communication, so that we are going to see it there. Then last will be API, we are going to see application program interface. So this API will be, so I'm going to do some I'm going to do communication between some protocols. The protocol must be supported by the software platform there. So the API should have been there. If the API is not available, so we cannot able to communicate properly there. Okay, so that's why the API is very, very important. So these four things we are going to realize, we are going to discuss in the next part there. So starting with the protocols here. So starting with the protocols, basically protocol will be, we are going to communicate to our hardware to the software, maybe hardware or software. Maybe we are going to communicate over that. We are going to exchange some messages over the message. We are going to exchange it over there. So the message exchanging will be in multiple stages will be available, which multiple protocols will be available. What kind of message we are going to exchange there, whether it is a number value or the message will be in the format of JSON. So how we are going to exchange the data here. So what you are seeing in the below images will be, so you have a multiple instruments and multiple hardwares I have provided us. So these are the places you can able to communicate to your software there. So the first one, what you are seeing in this case will be the NI compact Rio will be available. That comes from the National Instruments. NI compact Rio will be available. Then you have some PLC kit will be available from Allen Bradley. PLC kit will be available. So how we are going to communicate this particular instrument or the compact Rio to your application software through some communication like a protocols there. Then what are kind of protocols will be available? What is the protocols we need to know for doing this particular one? In the next slide. Okay, so the next slide is, so the key protocols we can be able to say. Okay, so key protocols in the sense, so we have a multiple layers will be available, starting from physical layer, link layer, and network layer will be available. So whereas in the network layer only, the protocols will be comes into picture there. So multiple protocols will be available there, starting from the familiar protocol will be starting from TCP is the one of the protocol, then UDP protocol, then you have a HTTP protocol will be available there. So these are the key protocols. Of course, MQTT also available there. So these are the key protocols we may come across in any point of time, not only in this platform. Okay, any platform will be come across over there. Okay. So through that, how we are going to communicate? So we are just communicating through any of the protocol in this particular case. Okay. So the common protocol whenever we are going for IoT will be, so I have told already, MQTT, one of the important protocol. Then OPC UA protocol also available, Open Platform Communication Unified Architecture protocol. Okay. So this protocol is available there. Then data distributed system protocol also available. Then like MQTT. Then you have HTTP and all will be available. So we'll see these things in our demonstration there. How one of the protocol is executing there. How we are communicating to the cloud. Okay. So here, if you look at the protocol, IoT protocol here means, so here our application software is going to be a LabVIEW here. LabVIEW is one of the applications that we are considering in the first part here. So for that, this first of the presentation will be focused majorly on the LabVIEW here. So if you are going for the OPC UA, that is Open Platform Communication Unified Architecture platform means, so in LabVIEW they are providing the API support they are giving there. Suppose if you are doing any process with the PLC or SCADA system means, so I want to see the data and I want to compute the data and I want to make some algorithms in the LabVIEW platform means, that's a software. LabVIEW is a software platform you want to do means, that time you require the API to get the data there. So that API support is they are giving over there for OPC UA, and same way for data distribution also they have a API support will be available for MQTT and AMQP. The rest of the protocol also they are providing the support in LabVIEW. So next will be they are going to see about the data files. So data files means, so we have communicated we have just talk about the communication there, how it's going to get communicated. Once it is getting communicated, so then we have to, whether we are going to store any data in the cloud, so or we are going to store the data on our local computer. So how we are going to keep the data here, so that will come under the data files there. Okay. So for data files, we have a multiple options will be available for data files. So if I'm talking about in terms of LabVIEW itself, means you have a Diadem will be available. So Diadem is one of the software platform where you can able to keep your data over there. No, I want to store the data on the cloud part, means the data I'm acquiring from the sensor, that data I want to view it on the cloud means, that particular time you can able to go for Amazon Web Services, one of the most familiar cloud. Of course, anybody will know this particular cloud, the Amazon Web Services, where we can able to store our data and we can able to return the data at any point of time. Okay. So similarly, you have a Microsoft Azure will be available. So two important clouds will be available. So you can able to utilize and you can able to read and write, retrieve the data. So, okay, in a file format, that's very important. In a file format, you can able to get the data there. So next we are going to discuss about the web services there. So web services is basically machine to machine communication or machine to machine interaction over some network there. Okay. So I have one hardware will be available. I have some target hardware will be available. I have a software will be available. So how I am going to interconnect through the help of the cloud. Okay. So you can able to see. So here I have a target hardware will be available, and I have a software. My host computer will be available. How these two things going to communicate through the cloud? Okay. So which means, to give you an example here, I am going to send some sensor value to the cloud. In the cloud, I am going to do some rules over that. Based on the rules I am giving in the cloud, that action should be taken. That impact should be will be implement should be reflect on my hosted my target there. Okay. So through the cloud, both are going to get connected there. Okay. So this is something will come under the web services or machine to machine interaction. So then last will be API. So I have told already API represents application programming interface. Okay, so this application programming interface basically gives some flexibility to communicate the platform with a third-party platform very easily over there. Okay, so here I have a LabVIEW I'm considering here. For LabVIEW, so I'm just going to take an example for the AWS cloud platform I'm taking over there. So AWS is providing the cloud services, and LabVIEW is both are different extremes there. So AWS will be the cloud services platform, and LabVIEW will be the application software where you can able to do some programming. You can able to do it over there. Okay, so but I want to get these cloud services into the LabVIEW, and I want to access the AWS cloud server. Means that time we require the LabVIEW API for AWS. We require that. Through that only we can able to communicate LabVIEW and the target platform to the AWS. So here you can able to see with the LabVIEW and combination of LabVIEW and Amazon Web Services, you can able to communicate to NI platform, the PXI, Compact Trio, and other DAC systems you can able to communicate there. Okay. So in case of if you're going for Amazon Web Services, the platform has multiple things available. So the support they have given in the given for LabVIEW will be AWS S3 available. S3 represents simple storage service will be available. Then AWS SNS is there. So simple notification service. SQS represents simple queue service. Then last IoT part will be available there. Okay. So these are the things will comprise. So the things whatever we have seen starting from the protocol, data files, web services, then last we have seen the APIs there. So these are the things will comprise about the will be one of the tool to communicate to the cloud platform there. Okay, so not only for LabVIEW. So since we are going to use LabVIEW in this webinar here, I'm just talking about the LabVIEW there. Okay, if you are going for MATLAB programming or any other Python programming, means that particular time, so Python also will support the AWS cloud. So that part that time, so we need to install the respective repository or the API we need to be installed over there. Okay, the same thing is happening here also. Okay. So then, so till now I have talking about the LabVIEW as a platform. We are going to implement it over there. But exactly what exactly is LabVIEW here? So what exactly is the LabVIEW there? So LabVIEW will be basically a graphical programming environment where you can able to where you can use the LabVIEW to develop your prototype, and you can able to validate the prototype. You can able to validate over there. Okay. Basically for the automated test systems, you can able to develop your algorithm. After developing the algorithm, you can able to deploy the algorithm in your hardware, in your DAC or in your system. You can able to deploy that. After deploying this particular one, you can able to validate also. Okay, so any engineers going to want to use this particular wants to do any research and all, means they can able to go for this LabVIEW platform. Okay, so anyway I will be exploring you this LabVIEW platform in 5 to 10 minutes. Okay. So in LabVIEW, so I have told this is a graphical programming there. So it is a graphical programming. So you are not going to follow any syntax there. Rather following the syntax, you are going to use the syntax. You are going to follow the graphical icons there. There the graphical icon is going to be going to do the purpose, going to resolve our purpose over there. Okay, so that's the important one thing about the LabVIEW. And it has in LabVIEW you have thousands of analysis functions will be available, analysis icons will be available. That I can see it on the right side of the screen there. So if you are going to use any measurements, means the signal processing, if you want to do, for example, if I'm going to do signal processing, means you have for signal processing, what are the icons we require? Signal processing is a domain. Under this domain, so we are going to require the window technique we may require that, then filtering technique we may require that. So these are the things will comes there. In filter itself, what kind of filter we are going to implement there. So these are the functions, these are algorithms will be built into this LabVIEW, so that we are going to use the icon there. The theory will be transformed into the icon, so that you can able to use the icon. That helps to go for the research here. that helps to go for the research here. Okay, so then I have told about the signal processing here. For a signal processing, I have told about for the signal processing department there. Okay, same way you have a image processing will be available. Under the image processing, capturing the image, after capturing the image, analyzing the particular images there. So how recognition you can able to do it there. So image processing tools, then control system tools will be available. So implementing the PID controller, then Fasiraji controller. So these are control algorithm will be available there. Then apart from that, if you're anybody going for a electrical side, it means electrical power toolkit will be available, where we can able to identify the what is the power going from the particular motors there. So we can able to identify the efficiency of the motor. We can able to identify there. So simulation also we can able to perform that time. Same time we can able to implement in your hardware also. Okay. So basically, LabVIEW will be widely used in academic side as well as academic and towards the research side also. Okay, so depend upon our own application development, we are going this even into the 4 categories there. So first one, starting from the academic side, so controls and circuit and electronics over there. Then second one will be measurements and instrumentation. Then third one, control and mechatronics. Last one will be wireless communications there. Okay, so here we are not going to discuss all the categories here, since we are discussing about the IoT part. So I'm not going to discuss anything over there. So we are just going to discuss about the control and mechatronics there. So for control and mechatronics, so what is the solution is given from the NI. Okay, so NI, last national instrument, what is the solution they are giving there? The solution they are providing will be, of course, DAC devices will be available. Apart from the DAC devices, I want to communicate to the cloud, and it should support some standard protocol. Means that time we can able to go for the device name called NI MyRio. Okay, so with the help of NI MyRio device, MyRio device, so it has a standard IO terminals will be available, and it has a inbuilt processor will be available there. So the processor will be take care about the programming what you are writing on the LabVIEW, as well as it has a FPGA processor will be available. So if I want to deploy any FPGA programming, means you can able to deploy the FPGA programming, and you can able to get the bit file also. Okay, so that for both 2 processors will be available. One will be a real-time processor called ARM Cortex processor will be available. Then you have a Xilinx FPGA processor will be available. So other than this one, you have a standard communication protocol will be available. It supports the protocols what we have discussed. So MQTT, HTTP protocol. Then other than this one, you have a the protocol called UART protocol available. Then SPA protocol, IAC protocol support also they have given that. So maybe here you can able to see here. So 40 lines of digital IO, SPA, IAC, then UART protocol will be available. So this pretty much covers what exactly we require. The IOs will be available, protocol supports also available over there, and it has a Wi-Fi capability will be available. So you can able to deploy the applications there. So that's what I have talked in the previous. So you are developing you are going to develop your algorithm. After developing the algorithm, you are going to dump the algorithm in this NI MyRio. Okay, after developing the algorithm in the NI MyRio, you can able to store the program, or you can able to store the algorithm in your MyRio itself. Okay, so you can able to make the system as a standalone. By giving the power supply itself, the system can start doing its work automatically. Okay, no need to be always connected to the host computer. You can able to deploy your own application. You can able to rewrite later part. Okay, but still once the process will be done, means you can able to validate in this particular fashion. Okay, so with this one we can able to realize multiple domains. We can able to realize that. So the domains will be starting with the basic embedded system. You can able to realize that. Then control systems you can able to realize, image processing you can able to do it there, robotics you can able to implement that. So these are the multiple areas. So this particular hardware is going to covers there. Okay, so these are all areas anyway time going to connect it to the IoT there. Okay, that we will see it on the demo. Okay, so how we are going to use the particular hardware. So I have a hardware. I will show the hardware to you to the camera. Okay, So how we are going to use the hardware, how we are going to communicate this hardware to the IoT platform. Okay, so which IoT platform we are going to implement here. So all will be talking in the demo part. Okay, so let me quit the presentation here. Let me go back to so here what I have opened here means, so here you can able to see, so the screen will be lab view. Okay, so lab view basically represents laboratory virtual instrument engineering workbench. Okay, so this is a graphical programming. So it has a two windows, two panels will be available. So the first panel will be here, you can able to see here front panel will be available. The front panel is basically a user interface panel. Okay, so where you can able to where you can able to have your controls and indicators. So here control is mentioning about the input data, indicator is available where indicator is mentioning about the output data. Okay, so where how we will get this input and output means by right click on the front panel. On the front panel, just right click there you can able to see input numeric. Of course data type will be comes there. Okay, so control will be a numeric control will be available. So where numeric control represents the numeric input there. So I am just taking a numeric control, numeric input here. Then similar way, I am going for numeric, I am going for numeric indicator. So where this numeric indicator represents the output. So indicator represents the output, control represents the input here. So this will be common for rest of the data types also. Okay, like the familiar data type called numeric, boolean, string, arrays, clusters. So these are the things will be common there. So with the help of the front panel, you can able to create the user interface. Okay, so I don't want this numeric control wants to be a normal number there. I want to make some thermometer, or I want to make some tank, the meter I want means. So here you can able to see meter will be available there. So you can able to see, so both are going to do the same process there, but how we are going to display the data there. Okay, so the meter will be available. Similarly, you have a thermometer, tank. So these are the things will be available there. Okay, depend upon the application we are building, we can able to use it anything over there. Okay, same way for if you go for boolean means there we have a buttons will be available. So push buttons, the toggle kind of switch will be available there. So on switch, off switch, then LED will be available for the indicator part. Okay, so similarly for string and arrays. Okay, so I want to see the data in a graph manner means, so I have a set of data will be available. I want to plot the data means how I can able to see the data means. So for plotting the data, we can able to go for waveform chart will be available. With the help of the waveform chart, you can able to plot the data there. Then you have a waveform graph will be available. So waveform chart I have here. Similarly, you have a waveform graph will be available. So waveform graph and waveform chart will be available. So to plot the data, so continuous data, you can able to have a graph and chart you can able to utilize that. So to basically to make the user interface, you can able to go for the front panel. Okay, then where I'm going to do the programming, we are going to do it on the block diagram. Okay, so the window name will be here, you can able to see here the window name will be block diagram. So in the block diagram only, we are going to start doing the program with the help of this controls and with the help of this input and output. Okay, so where basically functions will be there. So by right click on the block diagram, you can able to see start from the numeric. So basic arithmetic functions will be available and some conversions will be available. I want to convert the value from numeric to string or string to numeric means the conversions and all will be on this numeric palette. Then some rounding of the round of function, some constants values also you can able to see. So you can able to see some constant values also. Okay, so in the block diagram, the functions will be available, and boolean, if you see the boolean means that you have a gate functions will be majorly gate functions will be available there. String palette, the basic string functions, again the conversions will be available, converting number to string to number, array conversion. So these are the things will comes there. So for looping, say if you go to structure palette means that we can see loops will be available there. So where we have a for a while case structure events, so all the necessary loops will be given on the structure palette there. Okay, and variables, feedback node, all will be available there. Then array palette cluster, so pretty much whatever things we require all will be given on the basic functions there. Apart from this one, so to log the data, so if I'm coming down to the file environments, you can able to log the data on the host computer. Okay, so that I have file IO techniques also they are given over there. Okay, so next will be next important thing we are going to discuss about here. I have talked about image processing toolkits, then I have talked about the signal processing toolkits. Now that we can able to find these things means, if you, of course these are the separate package you have to install. Okay, whatever I have shown here, this will come built in with a LabVIEW. So vision and motion will be a separate package we may need to install that. So there you may have all the image processing algorithm will be given on the vision and motion there. Okay, then signal processing will be comes inbuilt with the software. Okay, so no need to install it separately. So there you can able to generate the signals, introducing the noise over there. After introducing the noise, how I can able to filter out the noise. So here you can see filters will be available. Filters, then window techniques. You can window techniques, probably here it's not available. Window techniques will be available here. So and so this is the way you can able to start using the signal processing toolkits. Like the way you have a control systems toolkits, then electrical power toolkits and all will be given there. Okay, then where I can able to find the communication, the protocols where I can able to identify means the things will be available on the data communication place. There we can see protocols will be available. There we can see the starting with the TCP/IP protocol will be available. Then a HTTP protocol, UDP protocol will be there. Okay, so now in this demo we are going to use the HTTP protocol. With the help of HTTP protocol, we are trying to push the data to the cloud, and we are going to retrieve the data from the cloud also. Okay, how we are going to do that? So that I will be showing you. Okay, so before that I will try to show the. So before that I will try to show the hardware which we are going to see now. Okay. So hopefully you can able to see the hardware there. Okay, so so this is the hardware I have I have talked in the presentation there. Okay, where we are using the NI Myrio. This NI Myrio is connected with the Wi-Fi now. Okay, so it's connected with the Wi-Fi now. So we are, it has this NI Myrio has a this side you can able to see, probably here you can able to. So you can able to see here. So we have a general purpose IOs will be available on the NI Myrio, where it is comprised with the analog input, analog output, DIO things will be available. Pulse width modulation protocols will be available on this particular place. Okay, if you look at the other side here means in other side also we may have some of the IOs they will be given there. Okay, so now what we are going to do here means backside of this Myrio, so it has a accelerometer will be available. With the help of this accelerometer, we are going to acquire the accelerometer data. That data we are going to see it on the cloud. Okay, so that is the first part, that how we are going, which protocol we are going to implement, that we will see now. Okay, so after sending the data to the cloud, we are going to retrieve the data from the cloud also. Okay, so that will help for the processing. Okay, the analytics you can able to do it there. Okay, so for this doing this particular demonstration, how we are going to implement that, what is the cloud we are going to use it here, all will be seeing now. Okay, so now so let me go back to the LabVIEW. So on the LabVIEW, so here you can able to see here. So I have done the program for the. So I have done the program for sending the data to the cloud. Okay, so what kind of data we are going to send here means, so the sensor data. Okay, sensor, as I haven't connected any external sensors, but still I have connected the sensors which is given built in the Myrio itself. Okay, so for that, so what is the protocol we are going to use here means, the protocol we are using here will be HTTP protocol we are using here. With the help of the HTTP protocol, we are going to send the data so to the cloud. What is the cloud we are going to use here means, we are going to use the cloud called Google Firebase. We are going to use it here. So we are going to use the cloud called Google Firebase cloud. We are going to use here. With the help of the Google Firebase cloud, I am trying to send the data. Okay, so in turn I'm going to receive the data later over there. Okay, so first we'll walk through about the programming, then I will demonstrate you. Okay, for this programming walkthrough, so I am going to create the HTTP reference I am creating over there. So with the help of the HTTP reference, so that it has to understand that. Okay, then I am going for the accelerometer here, where I am getting this particular icon, means this icon is given on the block diagram. So because this accelerometer will be available only for the MyRio. Okay, so there I can see accelerometer will be available. So I can able to see here accelerometer will be available. Through this accelerometer, we have a X value, Y value, and Z value will be available. So at a time, you can able to acquire X value, Y value, Z value in the 3 different directions there. Okay, so if you want to disable or enable anything, you can able to do it there. Okay, so in this case, I have taken the accelerometer value here. This accelerometer value is going to send it to the cloud. Okay, to send the data to the cloud, I am going to use the function called put function. Okay, put means I am going to post the functions there. Where I will be getting these functions means these functions will be on the block diagram. So in the data communication, in the protocols, in the HTTP client, there I can see open handle will be available. Open handle just trying to create the reference here. Okay, then I have a get will be available. Get means so retrieving data from the cloud. Okay, so getting the data from the cloud. Then you have a put will be available. Put means you are going to push the data to the cloud. Okay, so majorly you are going to use 2 functions there. Put function will be for sending the data to the cloud. Get function will be for retrieving data from the cloud. Okay, so 2 things you are going to implement here. So I'm going to send this data to the cloud, then will retrieve. Okay, so here I have made some conversions there. So conversion compatible to the cloud platform. Okay, so then I am going to close the data here. So what is the thing I have made here means this is the loop I have placed here, specifically while loop I have made here. This while loop will continuously execute my program, continuously executes my program here. Okay, until I am stopping the program. So while loop I have used here, and here you can see I have a 200 millisecond delay will be available. This delay will be basically for every 200 milliseconds my program will be getting executed, or my program will be getting iterated. Okay, so now I will go back to the cloud here. So I'm just going back to the cloud here. On the cloud, so how this cloud and my program, the hardware is going to get communicated means we have told HTTP protocol. Okay, other than this HTTP protocol, we may require some API key. We may sometimes we refer as a API key, or some credentials may require that. Okay, so here where I am getting this API key means, so here I have a URL will be available. So in this case, I'm telling us a URL. Sometimes in some other cloud we may refer as a API key, or credentials we may refer that. Okay, so here I have a reference URL will be available. With the help of this reference URL, I'm going to give this reference URL in my program. So I just already given the reference URL here. You can see here. So the reference URL I have given in this particular place. Once I start executing the program, so it will start communicating over there. Okay, so let me run the program here by keeping the cloud as okay. Let me start. So to run the program, running the program here, maybe you can able to maybe I will go for chart also here. Let me take one waveform chart here. So I have taken a chart over there. Okay, so now let me minimize this block diagram. Now I am going to keep it here. So now you are going to see the data here, data from this particular place here. Then you are going to view the chart value over there. Okay, now I am running the program. So whatever data coming from the accelerometer, the accelerometer data can be viewed there. Okay, so I'm running the program now. So we need to save the program because it has a inbuilt processor will be available. So program we are doing here. So once I started running the program, you can able to see x-axis, y-axis, and z-axis has the value. We have started seeing the value there. The same data will be goes to the cloud also. Okay, so we are just reading the data on the cloud there. Okay, and graph also started plotting data, but still you are seeing the straight line you are seeing for almost for the all the axis. Okay, now I am going to tilt my Myrio here. When I started tilting the Myrio, you can able to see the data is started. Data plotting is can able to see data plot over there. Okay, so previously why we have seen the same line means because of the stationary place. Okay, so now we can able to see the data is started rolling around. Okay, I don't know. I don't know. Can you able to see here or not? Okay, maybe you have to pin it there. Okay, you have to pin my camera means maybe at that time you may able to see it clearly there. Okay, I don't know. You may not be getting that. Okay, maybe you can able to see in your computer that. Okay, so based on my changes in the Myrio, the accelerometer, this is not the value I'm generating randomly. Okay, so from the accelerometer, we are just seeing the data. That data we are displaying, that's sending to the cloud platform. Okay, with the help of this Google Firebase. Okay. So similarly, if you want to retrieve the data means, so that we have, what we have done here means we have seeing the data on the cloud. Okay, how we can able to retrieve the data means, so whatever data I'm seeing, the data I have to see it on the other side to process that data. Okay, from the cloud we are just getting the data. That data I'm going to process there. Okay, so how we are going to process here? So for doing this process, so I am going to stop the program here. Okay, so I am going to open this receive data from the cloud. So the program does not have much difference. Okay, so program has a simple difference will be, so here you have a again open handle configure SSL will be there. So difference where will be get the difference means in the sending the data, while sending the data you have used the function called yes put function we have used here, but here we are going to use the get function I am using over there. Okay, so this URL must be, both URL must be similar URL you have to implement there. So not this panel, so we need a so this URL, what that URL you are seeing from this send data to the cloud and receive data from the cloud, both should be the same URL. Okay, then only the data is going from the cloud, the cloud value we can able to retrieve there. Okay, so now let me run both the VAs here. First of all, I have to run the send VA data. So let me arrange it properly here. Okay, so here you can able to see the send VA. So receive VA data will be available. Now I am going for sending the data to the cloud. Okay, so this will be sending data to the cloud, and here you have a receive will be available. First let me run both the VAs here. I'm running both the programs here. So data is started sending to the cloud. Now we are going to retrieve the data. So you can able to see here. So now you can able to see the data is going from, so in the send VA data, the data is going to the Google Firebase. That after getting the data, so this particular data will be again pushed back to the push back to the receive data from the cloud. Okay, from the cloud, the data is will be getting retrieving there. Okay, so this is the way we can able to initially we can able to start doing this kind of a project over there. Okay, then we can able to start doing the cloud computation. So all these things we can able to implementing over there. Okay, so let's talk about first demonstration. Okay. So kindly mute yourself, anybody. Okay. So participants, anybody kindly mute yourself, anybody.
Participants, please make sure that you are muted until unless you have. Yeah.
Okay, fine. Thank you.
Balaji, just a second. Wait, we are muting them. Yeah, please continue. Please continue. Balaji, can you hear us?
Yes, sir. I can able to hear you, sir.
Yeah, please continue.
Yeah. So this sum of our first demonstration. That okay. First demonstration. The idea will be, so we have discussed the multiple ways of 4 ways available. How we are implementing the 4-way into an actual working model over there. Okay. That's some of our first demonstration over there. Okay. So let me stop both the things, receiving the data as well as the sending the data. Okay. So this is the way you can able to get started with the started getting into the IoT platform over there. Okay. So but you are looking for something, you may be looking for, I want some full setup, the industry 4.0 setup if you want, means so that particular time again various stages will be available there. Okay. So how we are going to use the particular setup there, means so again we'll go for the presentation there. So we'll continue with the presentation. So on the presentation, so why? So I want to reiterate the process once again. Okay, I'm not going to talk about anything about the cyber physical system, that's CPS. Okay, so I am going to reiterate this process. What happened? What you are seeing on this above file. Okay, so the process will be multiple processing stations will be available there. These multiple processing stations I want to realize, and the same thing I want to see it on the cloud also, cloud dashboard also I want to do it there, means how this going to get executed and how we can able to set up this kind of things in the academic area. Okay, so both will be little bit getting into the IoT platform. We have seen the myri of that, but having a full entire setup, the industry 4.0 setup, the kind of setup, so how we are going to do that, so we'll see on the next. Okay, so for this industry 4.0 setup, so we are just partnered with the Fisher Technique. Okay, so Fisher Technique is the company. Basically, there is a French company there. So they will be giving the solutions for, they will be providing the simulation solutions for the full industry 4.0 setup there. Okay, so whenever we are going to discuss about the industry 4.0, we have to realize multiple levels will be available there. Okay, so that has to be simulated, how we can able to learn and how we can able to apply in the small scale there. Okay, so in a factory we have a bigger scale will be available. The bigger scale, the process is difficult to understand. Okay, the process you can able to make it, the process has to be making into the made into simple prototype over there. Okay, the prototype will trying to mimic or trying to replicate the actual process there. Okay, so depend upon the process you would like, you can able to modify the your projects over there. Okay, basically, so this learning and this Fisher Technique learning environment, so it will be used to learn about the industry 4.0 applications. Just I'm again telling that. Okay, and who and all can able to use this particular applications, means so anybody from education side, or any companies wants to educate their educate their diploma students, or educate anybody, they can able to go for this Fisher Technique. There they can able to explain, so this is the process is happening there. So and they can able to modify that. Okay, and universities and colleges also, they can able to put the students into this, and they can able to say it. So this is the model actually working over there. Okay, so this model is trying to depict the starting from the ordering process. We'll see the demonstration also. Okay, so starting from the ordering process, then it will start doing the production process and delivery, and all this process can be viewed in the cloud also. Okay, so basically what available on this particular Fisher Technique, this factory simulation prototyping. Okay, so you have totally 4 important things will be available, 4 important model will be available there. Okay, by combining 4 things, that makes the full entire process. Okay, so separately also available, separately also there. So we are going to combine, we are going to club it all those things in this particular case. Okay, so starting with the here you have a sorting line with color detection will be available. That's the first one, sorting line with color detection. Then you have a vacuum gripper robot will be available. Then you have a automated high bay warehouse will be available here. Then last you have a multi processing station will be available there. Okay, so every these four parts will be doing the multiple works over there. Okay, whenever the process is coming there, so it's going to do the work over there. Okay, so how the process is going to get executed means, so here you can able to see the first stage will be the stage one will be, so work pieces will be available. Work pieces means our model or our the project or whatever. Okay, so here the work pieces will be one model will be available over there. Okay, so that model we are going to get from the warehouse, from the automated bay warehouse. Okay, so here you can able to, I don't know whether it's clear or not, so let me show you. So here you can able to see in the automated warehouse, so they have maybe here you can able to see on this place, you can see the red color pieces will be available. Red color pieces will be there on the top of it. You can see red color pieces, then blue color pieces, then white color pieces will be available there. So the process will be start from the automated high bay warehouse there. Okay, so from that it will get the rate, it will retrieve from the automated highway bay house. Bay house it will be retrieved there. So then it will goes for the multi-processing stations. So where in the multi-processing station, so here you can able to see multi-processing station will be available there. Then will goes to the then will go to sorting line with color detection. It will go. So what is the piece we are retrieving from here? It will see the color detection. Based on the color detection, it will try to keep it in the proper slot over there. Okay, because here we have a three different pieces will be available here. So here itself you can able to see. So the image itself we have a regular pieces taking from the automated highway warehouse that will come across the multi-processing station. Then it will goes to the color sorting detection. There in color sorting detection, here we have a three delivery points will be available there. So here we can see the three bays will be available there. There it will try to sort it in the proper places there. Okay, so red color means will try to go to the red color properly. White color means the conveyor. There we have a conveyor system, conveyor belt, conveyor will be available. How fast we have to move to the conveyor there. So where the white warehouse will be available, where red color will be available. So we are just going to identify with the help of this sorting there. Okay. So once it is done, then last it goes for the vacuum gripper there. So once it is done, so it will go for the vacuum gripper. Then again, the data will be stored in the warehouse itself. Okay. So this is the way the process will be happening there. Okay. So to do this particular process, so what are the controllers we may require in this case? Means so you may require the controllers. What you may require means you may require so here you have a PLC controller will be available. Maybe PLC controller will be available there, as well as you have a TX3 controller will be available. So you have a two controllers will be available there. Okay. Anyway, my team will be there. They will be giving a demonstration on this one. Okay. So you have a two different controllers will be available. So you have a PLC controller, Siemens PLC controller will be available. At the same time, you have a TX3 controller also available there. Okay. So this is the four stations what I have mentioned there. Okay. So starting, this is a separate model. This has been combined into a single model over there. Okay. That only what we are seeing on this particular screen here. Okay. So warehouse high bay will be available. So this has a suction gripper will be available. Then motors will be available there to pass to the next stage there. Okay, so grippers this will becomes there. Then in the multi-processing stations, so what happened is we're trying to simulate various techniques over there. Okay, so in sorting, I have told already we're going to sort the color over there. Here also you have a here also where color sensor will be available there. Again, motors, the required motors will be given over there. Okay. Then last is surveillance will be available. Surveillance is something. So you can able to see the factory, the simulation in any parts over there. Okay. So this will be comes along over there. So on this place, if you want to monitor the multi-processing station, means that you can able to turn the camera to the particular place so that you can able to view it there. Okay, I want to see warehouse, high bay warehouse. I want to see means you can able to turn the camera over there. Okay, so that if you want to monitor the entire process, means you can able to surveillance option will be available there. Okay. So these options will be available, but there we are going to see all those things over there. As a hardware part, yes, we have a different stations will be available there. On the different stations, different operation is getting executed. Okay, but how I am going to see all those things there? Okay, to see all those things, they have a dashboard will be available. They have a cloud dashboard will be available. With the help of this dashboard, you can able to get all the necessary information there. Okay, so how many work pieces will be available there? How many work pieces will be kept on our highway warehouse? So highway warehouse. So, and what process is happening actually? Okay, so whenever it is taking the taking the pieces from the highway barrels means, so what is the process it is come acrossing over there, all can be seen on the view it on the cloud dashboard. Okay, so then same time you can able to see the camera output also. Okay, so you can able to control the camera in the cloud dashboard over there. Okay, so we'll see you. Okay, so this makes the complete environment there. Okay, so this makes it giving the complete environment there. So starting with you have a PLC controller will be available. Siemens PLC will be available. So the Siemens PLC going to get communicated to the IoT gateway. So they have given the inbuilt Fisher Technic cloud. They have given the. I want to use some other third-party cloud. I mean that third-party cloud option is also available there. So through the help of the third-party cloud, you can able to use either AWS cloud. You can able to use the over there. Okay, so starting with the particular PLC, Siemens PLC here. So Siemens PLC basically going to control the interactions over there, and the other controller will be available. TXT controller will be available over there. Okay, so this TXT controller will be helps to connect any IOS. If any IOS requirement, we can able to connect any IOS over there. So that will be again communicating to the human machine interface dashboard there. Okay, that dashboard we are seeing as a Fisher Technic dashboard. It's get communicated over there. Okay, I don't want this Fisher Technic cloud as part of that. So we may have other cloud means. So you can able to use the Node-RED open source software. You can able to use, and you can able to send the data to the cloud, whichever cloud you may expect that. Okay, so I will just play this video here. So I will just play this video here to understand how the process has been getting executed. Once it is done, so we'll be giving the demonstration also. Okay, so it does not have any audio. Okay, just have a look into that. Okay. So this is what the entire process. Okay, so this I have shown as a video there. Okay, so now on the other side, so I have my team will be available there. Okay, so we have set up the same what you have seen in this video there. We have set up the same setup in our Bangalore office there. So that you may see what exactly happens there. Okay, so the video it will give something there, but you can able to see the demonstration. So how exactly it's working over there. So on the other side we will see the demonstration. Okay, so let me stop my sharing here. So you can able to pin your screen also. Okay, so you can able to see that we have a setup we have been made here. Okay, so my teammate is sharing the screen. Okay, and he will take over. Okay, so Shamit, you are talking. You are not audible.
Yeah, am I audible now?
Yes, you are audible now.
All right. So good afternoon, one and all. So I would like to take you through the cloud part of this particular equipment. So as you can see, this is the customer profile. I can see that there is the availability for a blue color item as well as the red color. So I can go and proceed with the order placement, and I can see exactly what is the status of the factory as well. And if I go down, I can see how many pieces are available of individual unit, and the camera as well. I can physically maneuver the camera as per my requirement. So this is all internet over things, and I can control it from anywhere as long as I have access to the cloud. We need to create a Fisher Technique cloud login, and then we can proceed. And you can also see that there is a sensor unit which is going to give you the current air quality, what is the humidity level, and what is the air pressure, temperature, and so on. So let me proceed and go ahead with the order placement. So maybe you can click the video and you can see what exactly is happening.
So maybe you can able to pin the video. Okay, so then you can able to see what's happening there. So side by side you can able to have a look into your app cloud also. Okay, so currently it's getting ordered here. So we are just seeing the status in this place. So and here also you can able to see.
You're not able to see the video, Balaji?
We can see the video, Shamit.
Okay. I can see the live status in the cloud, where exactly it is, in what part of the factory and in the assembly line. So that gives me an idea as to what are the issues that are being faced.
Sorry for the interruption, but we are only able to see this Fisher Technique, this cloud page, not beyond that.
You will have to
could
pin the
see-
video, sir.
Okay.
change the view options in the Zoom maybe?
Yes, you need to change this like sharing option. You need to share the screen, I guess.
No, sir, that's normal camera only, sir, laptop camera only. So I can see, sir, I have changed my Zoom view to side by side gallery I have made, sir. So then I can able to see the video as well as screen.
One of them has to stop sharing and the next will take over.
No, Shamit alone shared the screen, sir. So I haven't shared the screen.
Okay. So we are only seeing this Fisher Technique Cloud, this page.
Okay, okay. So maybe the participants, you can this is normal video, sir. So normal laptop cam videos, what you are seeing here.
We are not seeing anything here.
You are not seeing anything.
What you'll have to do is there is a grid view where you can see all the participants, and there are a couple of views where you can pin a particular participant. So you need to go ahead and pin either Shamit or Harshita, and you can have the view of that particular video along with the screen sharing.
Okay, cool. Thanks.
Let me know if it's happening. I will redo the process again.
Yeah, now we can. Which one I had to ping, Shamit or?
You can ping whichever angle suits you. Both are covering all the aspect of that particular equipment.
Fine. And now it's working.
All right,
You
sir.
can.
So yeah, let me go ahead and redo the process so that you can understand what exactly is happening. So
Yeah.
as you know, in the warehouse, as per the particular data, I can see that there is a red quantity available. So I'll go ahead and order it. So this is the warehouse currently. So these are the items that are in stock, and I can see only one item, which is the red color. Blue was previously procured. So now I'll go ahead and place the order for red. And now you can see that the vacuum gripper arm is going to collect that particular item. And since it is NFC tagged, you can track exactly where it is in the production line, and you can get a data about it. Right now, this is the customer view. I can see what is the exact status of my order. This would be the production view, where exactly in which part of the assembly line or the production line it is.
So it has a camera available. So with the camera, so we can able to monitor each and every station. So that's what Shamit is doing from the other end. So we can able to pre-position the camera. So which process is happening there? That position we can able to move it with the this is the directions, and we can able to see which process we want to monitor. Which was that's what he is doing there.
Now you can see that the red color is identified and it has been sorted in the sorting line. It's being maneuvered and it will be placed to the delivery part of it. Yes, I can see that it has been placed to the delivery unit, and now I can see that it is being shipped. So this is the entire process. Balaji, you can take it forward from here.
Yeah. So what we have seen from here, so a full entire process there. Okay, the process we are just understanding how it is crossing the various stages. So after crossing every stages, starting from the taking a material from the highway warehouse, then updating on the cloud. So we are just ordering the which workpiece we want there. So after ordering this one, so just taking from the highway warehouse, then it's going for the gripper part, then it's going for the color sorting, then last it's going for the delivery part. So all it's happening there. Okay, so everything we can able to monitor, and it's always getting updated on the Fisher Technique cloud. Okay, so this is a cloud, yeah, it's updating over there. There we can able to see multiple views there. One will be the customer view. There only we are just ordering our.
Balaji, sorry for the interruption. Can you share
Yes.
the screen again? Yeah.
Okay. Shamit, you can stop the screen.
We were seeing the video shared by Samit, but now since you have taken over, we cannot see the PPT.
Okay.
Yeah, now we can see.
Okay, now you can. Okay. So basically, that's what's happening there. Okay, so every process, whatever happens, whatever you have seen in this video, the same kind of processes has been happened over there. So these are the informations we can able to update on the cloud, and we can able to retrieve the same thing. We can able to see it on the same thing also. Okay, so the dashboard has three views available. The customer view, where we can able to order our pieces we want there. So that's a customer view. That then we have a production view will be available. So on the production view, you can able to understand what are the process it is going over there. So starting from taking a work pieces here, so you can able to see the gripper part, then sorting the line, color sorting, and last end up with the delivery there. Okay, so at the same time, the important thing about this the prototyping model, the Fisher Technique prototyping model has a camera will be available. So we want to see which camera we have. We want to see which processing unit we want to see over there. We want to see which processing unit over there. Okay, so we can able to adjust the camera depends upon our need over there. Okay, so at the last, so you have some sensor unit will be available. That sensor unit trying to measure the temperature, the intensity, the brightness. It's going to measure over there. Okay, so I don't want this Fisher Technique cloud. I want to implement our any other cloud like AWS. Any other cloud means we can able to go for AWS cloud with the help of the IoT gateway. We can able to implement the same thing also. Okay, so this makes the some of our second demonstration there. Okay, so to conclude our presentation, what we have seen here means the first part we have discussed how to getting into the industry IoT part. Okay, so industrial IoT. So what are the techniques we need to know? How we are implementing the technique into the one application platform called the LabVIEW. We have just implemented there. Then to the next step is we have IoT available, but to make one process, the factory process means for the factory process we have a Fisher Technique is providing the prototype factory process. It's giving that where it covers the entire stations over there. Okay, that data can be seen in the cloud also there. Okay, so that's what we have mentioned implementing the industrial IoT and how we can able to transition that IoT into industry 4.0 process there. Okay, so with this industry 4.0, the Fisher Technique the factory model. So many leading corporates are taking this Fisher Technique model, and they are trying to do their factory model there. Okay, so let's take an example. So they have a BMW will be available. So they are trying to make their factory plant into this to tell them how the factory plant will be available there. Okay, so to tell them to the any students or anybody there, so that's using this model there. So what process they have been doing there? Okay, suppose they want to make some any trucks, means how they are doing their trucks over there, what process is crossing over there. So here we have some work pieces will be available there. So rather than work pieces, they may have some trucks will be available there. The trucks, how it is fitting, how it is building the chassis here. After building the chassis, how it is moving to the axle part, then how it is moving to the next the box, like the driver part, the into other layouts and all. Then how it is going for delivery method. So the based on their requirement, so you can able to go with the process there. Okay, so multiple case studies we have been with the Fisher Technique Industry 4.0 process. Okay, so that's it about this this presentation. If any questions, yes, you can ask the questions. So we'll give you answers there.
Thank you, Balaji. Participants, if you have any questions, you can ask. You can unmute yourself and you can ask the question.
Hello, sir. Am I audible?
Yes, sir. You are audible,
Yeah.
sir.
Yes, sir. Thank you, sir, for your knowledge sharing session. And I have a small question.
Yes,
Right,
sir.
you're connecting just IoT with industry. And I can see in your presentation, the communication technology that you have used is to communicate is Wi-Fi, right?
Yes, sir.
Yes, it's like I'm working with IoT communication technologies itself, low power wide area networks, and I came to know that the using of Wi-Fi or Bluetooth technologies having certain drawbacks in IoT communication. So how far this Wi-Fi will help us? Because I'm working under like low power wide area networks, so like LoRa devices, POX and NB-IoT. So when we have those devices, is there any difference of using this Wi-Fi or LoRa and NB-IoT? What kind of practical limitations that you come across?
So might be not much difference what I'm feeling, sir. So basically the LoRa WAN, what we have seen, this Wi-Fi, basically not much difference between this one, sir. So I don't have much idea about this LoRa WAN, the platform, sir. So but Wi-Fi seems to be working fine. So it does not have any problem also, sir. So this will comes with the router also. So they have a Wi-Fi routers along with this prototyping. They have a router will be available, so we can able to configure the router. So with our internal network there, so that won't be a problem. So in the processing there.
Yes, sir, and thank you. And another thing is like you have shared the LabVIEW tool too. Can we able to get that particular software? Because the tool is very good and it internally it consists of more number of toolboxes also.
Yeah.
Yes, can we able to get, sir, like can we able to access?
You can get the tool, sir, but that tool will be for only 7 days evaluation, sir. So you may get the trial version. You may get, sir.
Okay.
So if you tell what kind of domain you are working there, maybe that helps us. We can go for the software licensing, means so based on that we can able to plan, sir.
Sure. We're working on this IoT itself. A particular application will not fixed, but since the software which you have shown, it internally consists of more number of toolboxes. It really helps us.
Yes,
thank
sir.
you. Thank you so much for your session.
Yes, sir. You are from SRM, sir? SRM AP, sir?
Yes, sir. Yes, sir. SRM AP. I'm a research scholar in ECE department.
Is research scholar ECE department. Name, sir?
Srinivas, sir. Srinivas.
Okay, sir. Okay, sir. Okay.
Yeah, thank you, sir.
Okay, thank you.
So, Balaji, yeah, we have
Yes,
one
sir.
more question. I will like to read for you. Question is asked by Siva Ramakrishna. How will you handle security challenges like hacking in the products and solutions of Fisher Technique Industry 4.0?
So actually good question there. So basically the hacking and all does not be happen there. So this cloud platform, this the factory model what we are seeing just now, and the cloud will be both will be encrypted there. Okay, so we can, that is just like that data will not be goes there. Okay, so this will be encrypted there. So it does not have any hacking there. So this problem will not be there. Okay, so it will be encrypted and no problem with that.
Okay. Participants, do you have any more questions? Please feel free to ask question. You can unmute yourself and can ask the question. Okay. Since there is no more questions, so Balaji, I would like to thank you for this engaging and informative talk on behalf of Department of Electronics and Communication Engineering, SRM University. Thank you again for this wonderful talk. Thank you.
Okay, guys, now good morning to all of you. Welcome all of you for this session. And before that, I just want to introduce our session today, Dr. Ravindra, before starting off our talks. So Ravindra has done his PhD from IIT Kharagpur in 2017, and he's worked on transition metal based humanity and gas sensor. Then he moved to ECE, Center for Aeroscience and Engineering Group for postdoctoral university, and he explored advanced material sensing applications on equal and flexible platforms. Then he joined CSIR Center of Electronics Engineering Research Institute, London, as a scientist in Nano Biosensors Group, where he worked on industrial projects like on development of small gas. So now he is currently assistant professor in Electronics and Electrical Engineering Department and associate faculty in the Department of Design at IIT Kharagpur, where he established a sensor research group in 2021. So he will be developing the prototypes for gas and utility sensors for the benefit of Indian institutes. So he has published more than 35 articles in all major publication models like IEEE, ACS, RSC, Singer, Nature, IoT, and IoT, etc. So he will be editorial member for some of the journals. Also, he got the MRS Best Paper Award at 2019 in Boston. So he is the life member for Electron Microscope Society in India and IEEE. He is a senior member of IEEE and serving in the different responsibilities at various capacities. Okay, so with this introduction, I will start the session and I will be handing it over to you. Sir, please welcome. Okay, sir.
Yeah, thank you, Professor Reddy. So, as a chair of the session, I would like to invite Professor Samresh Das. We might not be knowing each other, but he is my senior from IIT Kharagpur, Professor SK Research Lab. Professor Samresh Das is the associate professor at the Center for Applied Research in Electronics Care at IIT Delhi. He received the MSc and PhD degree from IIT Kharagpur in 2005 and 11. At IIT Delhi, his research involved, at IIT Kharagpur, his research involved on germanium quantum dot based floating gates, light emitters, and photometers. He then worked as a researcher in the Ultimate Silicon Device Group, led by Professor Jean Collinge at Tyndall National Institute, Ireland. There he worked on our fabrication and characterization of junctionless nanowire tri-gate MOSFETs. He worked as a research scientist at Hitachi Cavendish lab, basically, the University of Cambridge, on water project for the development of scalable silicon charge qubits. In September 2014, he joined the Center for Applied Research in Electronics, at Delhi as assistant professor. His research group at IIT Delhi is working on development of efficient infrared photodetectors, generate electronic devices, quantum devices. He is a recipient of Early Career Faculty Research Award in 1990 IIT Delhi. Institute for Smart Structure and Systems, IISS, Young Scientist Award in 2019. Then INA Young Engineer Award in 2017. and Maitri Vishweshwaraya Young Faculty Research Fellow Award. So, Professor Das, I welcome you on behalf of the organization committee of EPIC 2022. You may start your talk. Audience are waiting for you.
Okay, thank you for the nice introduction, and I am also grateful to the organizing committee for inviting me for this talk. So today I will be talking about the transition metal dichalconide and group 4 semiconductor heterojunction photodetector for visible to near infrared. And the work mainly done by my two PhD students, one is Birendra Dhani and Akshay Mutlam, and this is my group. So in our group, we mostly work in different area. One is obviously the photodetectors, which is ranging from UV visible to infrared range. And it is mainly based on silicon or germanium substrate and then 2D materials integration on silicon germanium platform. Also, we are working on terahertz electronics devices, mostly terahertz detectors and modulators. Terahertz detectors, we are working on nano field effect transistor as well as 2D materials APT as a terahertz detectors, and modulator also we are working on 2D materials based terahertz modulator. And for the quantum devices, we are mostly working on the charge qubit based on quantum dot or nanowire quantum dot. Also, we are working some collaboration with the biotechnology group using the field effect transistor for biosensing application. So in today's talk, I'll mostly talk about these other things. First device is MOS2 silicon heterojunction photodetectors. There is scalable process development. And the second one is the MOS2 porous silicon to increase the efficiency of the photodetector in the near infrared range. So we use the porous silicon instead of silicon. And then integration of these 2D materials on silicon and insulator platform. All of you know silicon and insulator platform is a good technology for silicon photonics. So integration of these 2D materials on SY platform is a automatic choice. So we'll discuss here indium sunlight on silicon and insulator phototransistor for dual band, UV and visible band. And then last I'll talk about the integration of the 2D materials on germanium and insulator wafer for infrared detectors. And all of you know the optical detectors are used in many applications. And depending upon the application point of view, you have to choose the wavelength, speed, all these things parameter depends. So for the data center, like if you want to send data from one server to another server, you need to have a very high speed connection, and that mostly done by Photonics fiber connection from one to another. And there is a transducer and require and which can send the data 1 terabyte per second. Now it is available through fiber. And there are also a lot of detectors is requirement, and even in the interconnect. And when you talk about the free space communication, all these things, the wavelengths will change. Even for the military application like the infrared imaging, a light vision imaging system, there is mostly the infrared and those things. And what are the latest technology always going on? So like one is the transceiver. If you see here, you use like you have to convert the optical signal to electrical or reverse also. Like you have to convert the electrical to optical signal to send the data through the fiber. So there you need for the optical to electrical convert, you need a high-speed photodetector. And suppose this is one things like the photons are coming, and then you have mostly the photodetectors, and then you convert it into the digital signal, electric signal. So data is coming out. And similarly, other side you have a laser which will encode the data in the electric things, that way you can send. So for this like application, you need a high-speed on-chip photodetector. Mostly nowadays you use germanium avalanche photodiode for this type of application. But there is other application also currently is coming out, like Wi-Fi wireless communication, where you can send the data very high speed as well as very like in the both the visible ultraviolet and infrared spectrums, depending upon where you want to communicate. Like if you want to do short distance underwater communication using Wi-Fi, where ultraviolet wavelength light is more useful. Similarly, there is a application for the space like remote sensing. Like if you see the ISRO, what are the different image sensors they are using for different satellite, and you can see LISA 4, LISA 3, or recent one is the AWIFS, where you can they have also 1.6 micron, from 550 to 1.6 microns, because this wavelength will determine the image resolution and what are the things you are imaging. So that will be visible. So you have to go from not only the visible to near infrared, so you have to go from near infrared and infrared region for what you want to do imaging. And when you talk about the normal photodetector, so we know already silicon photodiodes are available, but they are limited due to their cutoff wavelength, like it can work nicely up to 1 micron, but above 1 micron it cannot work because of the bandwidth. Similarly, that's why the good photodetector for near infrared range are commercially germanium or gallium arsenide photodetector. But if you new class of materials came in 2D materials like the transition metal, chalconite, graphene, black phosphorus, all these things came, and you know all type of materials are available using this 2D material, from insulator to visible range wavelength gap material, then infrared, and graphene can, you know, that it is a direct material, so it can absorb any energy photons because of this relation. So by using these 2D materials, the advantage is that they have a good absorption coefficient depending upon obviously the material and to whom you are comparing. So if you compare this MOS2 or WAC2 with compared to silicon, they have a better absorption coefficient. Obviously the order is same as the 3.5. So depending upon the application, there is a lot of developments already done on this using these 2D materials. And if you can see, the responsivity goes up to 10 to the power 5 around. But the problem of these 2D materials photodetector is the speed. If you see the response time, they are not very fast. And where the response time is very fast, there you can see the responsivity is very low. So the challenge is there, how can you make the responsivity higher as well as the very fast photo response? Because if you want to use it as a modulator, imaging, or the other application or data communication, so you need to have very high speed photodetectors along with the responsivity. So keep in mind integration of this 2D material with this silicon and germanium is beneficial. So first one, I'll discuss about the integration of the MOS2 on silicon to make the high performance photodetectors in this visible to near infrared range. Now many of, hello?
Professor Das, we are interrupting you. Your voice is not very clear. So, I mean, do you have any microphone here? Because I think there is some issue from your point.
Let me check. Can you hear me now? Is it clear?
We are able to hear, but sound is not clear. So if a microphone would work, I think. So you see if you have
Actually, surrounding disturbance is
surrounding noise is coming. Not from us.
Okay, I'll try. Okay.
If possible, otherwise I think you can focus on your now.
Yeah, so currently because mostly I use this video cam and with these things sound, I don't have the headphone with me. Okay, sorry. I think I'll try to much more louder voice, so it will be good. Okay, so in this heterojunction photodetectors, what we develop the process for the scalable process. You know, many people are working on this MOS2 and this, they take the flake and then put on silicon wafer and make the devices. But our approach to how can you make the scalable photodetectors? So here what we have done, so you have to grow the wafer scale MOS2. So for that process, what we have done on a silicon wafer, and then we deposit the MO3 thin film by reactive sputtering with oxygen, and then we do the sulfurization process. So then the wafer scale MOS2 formation. But these are not MOS2, are the single layer MOS2. So this is a flake type nano structure, and this throughout the silicon it has formed. Now to create a scalable device on silicon and MOS2 heterojunction, on SI to wafer, we remove the SI to some part where the silicon will be making the contact with the MOS2, and then we do the deposition of MO3 and patterning, and then we do the sulfurization, and then we do the metallization, and then it makes the silicon and MOS2 heterojunction. And from the Raman's and XRT spectrum, it has confirmed the formation of the MOS2, but it is not the single layer MOS2, it is a multi-layer MOS2 from the Raman peak difference for the 2G and 1G peak. And then we did the photocurrent measurement of this MOS2 P silicon heterojunction, and you can see this is the for the MOS2 gold, only MOS2 film, and when you make the heterojunction, so this is the current, dark current, and this is the light current, and you can see the few order of current is increases, and MOS2 and silicon is showing good rectifying behavior. So they make a good heterojunction of N-type MOS2 and P-type silicon, and it has a very low dark current, and once photon is fall, the current is changing around 3 order of current. And we calculate the responsivity depending upon the wavelength. You can so how to calculate the, once we calculate the responsivity for MOS2 silicon and MOS2, and you can see the responsivity of the heterojunction in the near infrared range. This is very improved compared to the only MOS2, and detectivity also is very good. It is showing around 10 to the power 11 joules. And we calculate also the speed of the photodetector. Once we make the heterojunction, then we do the incident of the light in a modulated laser source, and then we measure the dynamic photo response of the photodetector, and you can see it is showing 10 microseconds rise time and 19 microsecond fall time, and we do the different frequency modulated, and you can see it is working fine up to around say 10 kilohertz. Then after that the IMAX it is decreasing sharply. So this photodetector can work up to maximum 10 kilohertz like that. To study the stability and the scalability of the process, that was our main approach, and we fabricate many devices, and you can see all the devices shows the similar performance like the responsivity and dark current of all the devices. So that is our main innovation, and we study the stability even after 90 days. This is showing the stable dark current and photocurrent of these devices. In the second one, I'll show how can you improve the performance of the photodetector in the near infrared range, because that has a lot of application in that. So we integrate this MOS2 on porous silicon to improve the performance further in the near infrared range. To fabricate the devices, first we fabricate the porous silicon using the electrochemical etching, and then top of that we deposit the MOS2 as previous case, and then we make the ITO metal contact, and then make the MOS2 and porous silicon heterojunction photodetector. And you can see that as all of you know, the porous silicon has a good emission in the near infrared range, and along with the MOS2 emission and this visible to near infrared range. And we also from the Raman it confirmed that the MOS2 is not single layer, it is a multi-layer MOS2. And then we do the optical characterization, and from the photocurrent characteristic, you can see compared to the MOS2 crystalline silicon, the off and on current ratio, the incident of the light, the MOS2 porous silicon is much higher. And this high distribution as well as the low dark current and also increment of the current of the MOS2 porous silicon is around 400 times in case of the MOS2 crystalline silicon, what is around 130 times photocurrent, dark current. And this is the responsivity of these devices, where you can clearly see for the MOS2 porous silicon, you have improved the performance in the near infrared range compared to the MOS2 crystalline silicon. So that was our aim, to improve the performance in the near infrared range, because that has a lot of application in the remote sensing and other application imaging system. And we So we have shown the responsive detectivity around 10 to the power 14 joules per 5 volt, and this highly detectivity and responsivity coming in this porous silicon, because once you make the porous silicon, the heterojunction barrier width between MOS2 and porous silicon is larger compared to the MOS2 porous silicon, as well as you make a lot of junction, because once you make a porous silicon, when you deposit the MOS2 on top of that, the effective junction area also increases. So that is the reason for the improve the performance of the porous silicon compared to crystalline silicon. Now I'll discuss is the another system, these 2D materials for the dual band application and their integration with the silicon on insulator wafer. This silicon on insulator wafer is a very good material for waveguide based photonic devices and integrated silicon photonics devices. So also these silicon on insulator devices are for the transistor application, they are very powerful because of the high frequency application like RF devices. Most of the now RF fountain module in our mobile phone are made of this silicon on insulator wafer. Also, you can couple the light in the silicon waveguide nicely. You can make the different types of waveguide structure, either rev or the silicon on insulator structure to make the field effect transistor. So this is the device structure. We have SRM device structure. We have a thin layer of silicon on insulator. On top of that, we have transfer the indium selenide, and then we do the reactive ion etching to remove the silicon rest of the and make the silicon and indium selenide heterojunction photodetectors. And this silicon substrate we use as a backgate bias for the transistor. And this is the structural properties which confirm the formation of the indium selenide as well as the in some phase of indium oxide also present in this indium selenide. And this is the phototransistor characterization, and you can see by using the backgate bias, you can control the current on the channel. So you can control, because by applying the backgate bias, you can deplete the silicon, so the current decreases, and this is the transistor performance. And you can see the on-off ratio is around 10 to the power 4 of this transistor. And so once light is fall, like depending upon the which wavelength 280 and 800 nanometer, the current is increases 2 order almost. And this is the similarly ID versus VD curve for the phototransistor. And this is the dark current. As I increase the light intensity, like the 280 nanometer or 800 nanometer, the current is increases sharply. Because this indium, it shows the, if we show the responsivity, you can say for the UV range, it is showing very high responsivity because of the presence of the indium selenide, whereas in the present, because of the SOI silicon, so it is shows the broad response from visible to near infrared. And it is showing dual band because the rejection ratio between the UV and this 480 nanometer, it is around 137. So it is a good rejection ratio between the UV and to 480 nanometer. So these detectors can be used as a dual band photo detection. And we also measure the speed of these photo detectors, and it is coming around 118 microsecond for the rise time and fall time around 22 microsecond. And from the rise time and fall time modeling, we find their trap assisted. There are different recombination mechanism of this charge carrier, photogenerated carrier in this phototransistor. And we also calculate the noise, because noise is a major part to find out what is the NEP, noise equivalent power, because that will ultimately determine the sensitivity of the photo detector. And here you can see the NEP value is 6.8 femtowatt. Why it is coming very low noise? Because of the low dark current. So we are using this photo detector in transistor mode. So by applying the gate bias, we can deplete the channel, and then we have a very low dark current. So the NEP value is very low. So the sensitivity of this photo transistor is very good compared to other reported value. So that is our major contribution of this heterojunction phototransistor. And the last system I'll discuss about the MOSE2 and germanium heterojunction for infrared detection, because the germanium is a good material for the infrared sensitivity. So integration of the 2D materials on germanium is a major things for improve the performance of this detector in the infrared range. And all of you know, just like the silicon or insulator wafer, germanium on insulator wafer is a good material for the mid-infrared to like in the SWIR, short wavelength infrared to mid-infrared wavelength, because if you see the refractive index, they are around 4 for compared to with the if you are using the claddings, calcium fluoride or titanium oxide, so they are a good waveguide properties in the mid-infrared range compared to the silicon. So for the infrared on-chip like the devices, the germanium is a preferred material compared to the silicon. So how to fabricate the device? Like first, we took the germanium on insulator wafer. It is purchased from outside, and then we transfer the MOSE to flake by Scotch tape method, and then we define the area of the heterojunction by reactive ion etching. We remove the rest of the material germanium as well as the MOS2, and then we make the germanium MOS2 heterojunction. So this is the MOSE2 germanium heterojunction devices, where you can see this is the germanium and this is the MOS2 plate, and this is the two metal contact of the source and drain. And this is the photo current characteristic of the device, and you can see this is heterojunction make a good rectifying behavior compared to the normal MOS2 photo detector. So this is the normal MOS2 photo and dark current, whereas the circular one, it is showing the MOS2 and germanium heterojunction photo detector in dark and light for infrared wave line incident, like 1.54 micron. And for this device, what we observe, even at the zero bias, in instant light of 1.5 micron, we can see the photocurrent. So this is happening because this heterojunction formation of this MOS2 and germanium, there is a inbuilt electric field which separate the charge carrier. So you see this zero bias photocurrent. So you can, this photodetector can work without applying any external bias. You can get some photocurrent, and it can work up to 1.7 micron. We have checked this device, what is the maximum wavelength it can go. And if you compare with the normal, this line shows the zero bias photocurrent responsivity, and you can see very ultra broadband photoresponse from 400 nanometer to 108 micron of device. And if you give the bias, so this black line shows the heterojunction photodetector. Whereas if you can see the performance of the only MOSE2 photodetector is fall around 1.2 micron, and only the germanium it is showing from 600 nanometer to 1.8 micron. So by forming the heterojunction, we can make the ultra broadband photodetector, as well as it can work as a zero bias photodetector. And responsivity, maximum responsivity, we have observed around 30 ampere per watt at room temperature. So this is a good candidate for the room temperature infrared photodetector. Also, we have measured the speed of this photodetector by dynamic photoresponse measurement from modulated light source, and it is showing very good response times. Like you can see, the rise time is around 14 microsecond, and fall time is very fast, 1 microsecond. So, and it can be work around, we have checked the around cutoff, like the modulation cutoff frequency, it can work up to around 40-50 kilohertz. So this detector is very fast compared to the previously what we have shown. So in summary, what I discussed, so the integration of these 2D materials with the silicon is a good way to increase the performance of this photodetector, and we developed the scalable process for fabrication of the silicon and MOS2 heterojunction photodetector. And then secondly, I have shown like you can improve the performance of this silicon MOS2 heterojunction photodetector in the infrared range, near infrared range, by using the porous silicon instead of crystalline silicon. And we have shown the integration of this MOSE2 with the germanium and insulator wafer to make high-speed ultra broadband photodetector like 400 nanometer to 1.8 micron at room temperature. And then lastly, also I have shown the integration of this indium selenide layer material with the silicon on insulator technology for dual band photodetector. Thank you. So I'll take now question. I'm thankful to the funding agency, DRDO, METI, as well as Imprint DST, and our IIT Delhi Nanoscale Research Facility and CRF Facility. I'm also thankful to our collaborator, Professor Samit Kumar Ray, IIT Kharagpur, and Professor Justin Som from University College Cork, Ireland.
Yeah. Thank you, Professor Das, for this nice talk. Any questions from audience? We will take only one or two questions, sir. We are already, any question? Okay, so audience is not posting any question. So I will have a small query. So we have discussed this high-speed heterojunction devices. So how do you deal with the contacts, sir? I mean, contacts will be slowing down your devices, no? So how you are dealing?
Which contact? The metal contact or the heterojunction junction?
Metal contact.
Metal contact. Yeah. So previously, like first you have to check, like you are making the metal contact, the ohmic contact. That is always a challenge using the 2D material. So we have checked with these devices, because if you are making the Schottky contact, that will create the RC contact. So that will decrease the speed of the detector. So you try to make the ohmic contact, then this capacitance will not come. So that is the challenge, obviously. So in this 2D material, so we make the contact with the gold, and it is showing very low barrier, right, around few hundred millielectron volt. So not very large. So that way.
Okay, okay. And this indium selenide devices, you have used this SOI substrate. Any specific purpose? I mean, for optical devices you are using, I can understand that. That's why you are using SOI.
Yeah, so SOI platform is a very rich platform for the silicon-based photonics. Like you integrate the detector, modulator, as well as the other demultiplexer. All these things are available. Like as I saw in the first figure, the transducer, which is currently used for the 1 terabyte data transfer, they are using the SOI platform with the laser also made on the silicon on insulator devices like so that is the major thing. Also, we for that devices, if we as you use the SOI platform, we decrease the dark current, because the top silicon layer is disconnected through the insulator. So your current of the transistor is very low. So the leakage current is very low. So that is the like the dark current you can go very low. So that is the major advantage.
Thank you, Professor, for explaining us about the two queries. So if anyone will have any question, you can directly email to sir. Okay. Thank you, sir.
Yeah, hello everyone. I'm Ranjit. I'm an undergrad student at BITS Pilani. Today I'm going to talk about investigation of a highly sensitive plasmatic device utilizing antimony for biosensing applications in the near infrared region. The contents of my presentation is going to be introduction, which is what is surface plasmon, how are they getting excited, the motivation behind the work, why I chose the material, the proposed plasmonic configuration, the effect of different 2D nanomaterials on the plasmonic configuration, which I propose, and their comparison, how the different number of layers are going to affect the performance of the device, and then we will compare our results with the results reported in the literature. After this, I will conclude my talk. When see the literature, normally the catchment configuration is used. In this configuration, we use a glass prism coated with a thin metal layer of any plasmonic material such as gold, aluminium, or silver. Upon that, there's an light. A TM polarized light under total reflection scheme takes place here. TIR means that the angle of incidence, when it's greater than the angle, when it's greater than the critical angle, we expect the whole light to be reflected back. But for a particular condition called phase margin, we know that under TIR, evanescent field gets produced. Under that evanescent field, we will get coupled with electrons in the metal anilite interface, and those electrons will start oscillating in the surface. This oscillation is called surface plasmon. The condition in which the photons will transfer the energy to the electrons is called phase matching condition. If you see the right-hand side of this particular equation, which is basically the wave vector of the incident light coming from the glass K0 is multiplied by NP, which is refractive index of the prism. And also there's theta, which is the angle of incidence. On the left-hand side is equal to the wave vector of the surface platform K0 multiplied by the average of the dielectric constant of the metal and the light. So in this particular condition, when the wave vector of the incident light is equal to the wave vector of the surface platform, we can say that the light transferred to the surface platform. In this particular equation, we know the dielectric constant of the metal, and also we know the dielectric constant of the metal. If we find out the angle at which the phenomenon takes place, we can find out epsilon A, which is of the light. In this manner, we are doing sensing. To rigorously understand this, we can look at this graph, which is the dispersion diagram, which is frequency versus K. We know that when light is coming in free space, omega by beta is C, basically the velocity of the light. But when the light is getting multiplied by the glass prism, it is going to get reduced, which is represented by the blue solid line. The red solid line is basically the left-hand side of this equation, which is a parabolic curve. In this diagram, the black and red line do not have any point of intersection, which means that they can't excite the surface platform when the light is coming from the air. To increase the momentum of the incident light, we use a glass prism in this particular work. Instead of a glass prism, we can also use 2D nanostructures to play around with the momentum of the light. But when the light is coming from the glass prism, there is an intersection point, which is called the phase matching condition. Which means the surface platform gets excited only after increasing the momentum of the light. This is just to give you an idea, because our configuration is on the basis of Kretschmann configuration. We are trying to modify the Kretschmann configuration with different intermediate layers. Here we have used antimony as a binding reagent. For biosensing processes, we need to attach the top surface of a device with biomolecules. This is why we have used antimony as a binding agent. Why aluminum? Aluminum, because it's very cheap compared to gold and silver, also has a wider spectral coverage. It can be used in deep UV to IR agents. Also, the narrow line width. Narrow lines give higher resolution to the sensor and high figure of merit. And NIR sensing is used as it provides non-destructive analysis when doing biosensing. And in vivo imaging also possible without any photo damage. Why antimony? People have already done these kind of studies with graphene, MOS2, black phosphorus, MXC. But we will show with our results that antimony-based plasmonic device offers high figure of merit and sensitivity, and we do not need to be very precise while depositing the number of antimony layers. The reason for which I will explain in the following slides. So starting off with the proposed configuration, we use a CaF2 glass prism. There are other kinds of glass prisms as well, but here CaF2 is used because at 1550 nanometer, there's very little change in the refractive index of the prism. The aluminum is used as its cost effective, and antimony here is used as a binding agent. So starting with how we optimize and engineered our design, we use a transfer for TMM, which is the transfer matrix method is used. This is generally used when there are multiple homogeneous layers in the device. There's an incident light and a reflected light, and the number of layers can be inputted. At each layer, we need to satisfy the tangential component of the electric and magnetic field. We satisfy the boundary condition using characteristic matrix method. We will use the characteristic matrix method for the whole structure, by which we calculate the reflection and transmission coefficient of a particular structure. Methodology. First, we need to specify the range of angle for which our simulation must run. Then we must define the dielectric constant, thickness, diffractive index of each layer. Then we optimize the layers keeping in mind three decisive parameters, which is the minimum resistance, that is minimum reflectivity that can be provided. We need to have high sensitivity and a high figure of merit. Figure of merit is basically sensitivity divided by full width at half maximum. After this, we can do biosensing operations, and the output can be observed in the terms of reflection dips that are observed. First, we start with a normal glass and aluminum with anlight. Here, as you can see, there is no antimony. This is done so that we can calculate the optimal thickness of the aluminum layer. We vary the thickness of aluminum layer from 10 nanometer all the way to 40 nanometer. And there are three parameters we should take into consideration. That is sensitivity, FWHM, FOM, and RMIN. As you can see from this table, TM, which is the thickness of the metal, should be 30 nanometer is the most optimal thickness, and we use 30 nanometer for further analysis. So coming to a proposed structure, now we add a layer of antimony for the binding agent. Now we can see how much the sensitivity and the figure of merit. If we change the analyte index from 1.33 to 1.34, we get decent sensitivity, which is 119 degrees per refractive index unit, and also a figure of merit, which is 425 refractive index unit inverse. Now we want to compare our results with graphene, amexine, and black phosphorus, which are other binding agents people use, and also a lot of work have been done on them. We have considered a single monolayer of graphene, amexine, and black phosphorus on an aluminum-based plasmonic device to compare results. So if we see a single monolayer of these 2D nanomaterials on an aluminum plasmonic device, we can compare the figure of merit. And over here, we can see that the figure of merit for antimony, which is our design, is considerably more than the other figure of merits. So next question is, how many layers do you need for these binding materials to see if it will increase efficiency of binding or not? So one by one, we tried increasing the number of layers from 1 to 20 to see its effect on sensitivity and figure of merit. We see that with increase in number of layers of graphene, the R-min deteriorates, which means it increases. And a similar characteristics is seen with MXE. Also, the FWHM increases on increasing the thickness of the layer, which means that this is very stringent condition on the thickness of these deposited materials. The trend is also observed in black phosphorus. However, in case of antimony, we see that the R-min is not deteriorated. It is almost constant. The FOM and line width are also almost constant. This is because the imaginary part of the dielectric constant is almost negligible at this wavelength, due to which the R-min does not change very much with the increase in number of layers. On the graph right here, we can see that the change in R-min and FOM, which is almost constant with the increase in number of layers. Hence, we get the failure to not take care of the number of layers deposited on the device, as they are not going to hamper my results. So it does not put any need on stringent control of fabrication of these layers. Now we can compare our results obtained from FOM and sensitivity. We can see that in case of antimony, the FOM is very high compared to the other configurations, and also it has a high sensitivity. And also there is no deterioration with the change in the number of layers. To demonstrate this structure, we can use that this structure can be used for sensing applications. We tried putting different concentrations of glucose. We can calculate the refractive index of these analytes with varying glucose concentrations. We can see clearly that there's a right shift with an increase in concentration of glucose. We can also see there's an angle shift with the increase in concentration of glucose. Finally, I would like to compare our results with the previous results in literature. People have used graphene, MOS2, MXene, and other substances. They are getting higher sensitivity and low figure of merit, or high sensitivity or low sensitivity and high figure of merit. But in our work, we are getting high sensitivity as well as high figure of merit. So let me conclude my talk. We basically analyze aluminum antimony-based plasmonic devices for sensing applications. We were able to achieve high FOM and sensitivity. We also were able to control the minimum reflectivity in the case of antimony, which did not deteriorate with increasing number of layers. Among the 4 nanomaterials, we found out that antimony to be the best option for binding material. We also detected minute changes in the glucose concentration with our device with the shift in SP. Thank you for your kind attention. And also I'm open for any questions.
Yeah. Thank you, Ranjit, for this interesting talk. I have a couple of questions for you. Okay.
Yes, sir.
Yeah. You have told that antimony works with better FOM and sensitivity, and you have shown 3-4 materials. Have you checked with MXene and other materials also? Because in the table in the last, when you compared with other works, they were also quite good, no?
Oh, can you repeat the question, please? I couldn't hear.
No, I was just wondering that why you have chosen antimony selectively, because you might be knowing that growing these materials are not easy. Okay, growing antimony, I mean for practical application. Okay.
So in the final table, if people got higher FOM, they got a low sensitivity. They got a high sensitivity, they got a low FOM. What we did was we got a high value of both FOM and sensitivity. And you were talking about deposition of these layers. The entire point of this study is that we do not need to be very stringent on deposition of these layers, which is why there is no deterioration in the Rmin values.
Okay. And why the sensitivity of all the four materials that you have shown are nearly equal, 119, 118? Is there, but others have shown very different sensitivity, like 94, 276, like that.
I believe because the real part of the dielectric constant is almost same for everything that we took. That's why the sensitivity is around 118, 119. The change comes in the imaginary part.
I understood. Yeah. And this TMM method that you have shown us, you have developed it or it is from literature?
Yeah, no, it is from literature. I just wrote the MATLAB code to simulate it.
Got it. Got it. Yeah. Thank you.
Okay, thanks a lot.
Yeah.
So today we will have our first talk on silicon photonics and imperative technology from communication to computing. And the talk will be given by Dr. Santa Kumar Selvaraja. He is from IST Bangalore. So I will just quickly introduce before I hand over the mic to him. Professor Santa Kumar Selvaraja is a professor of Ramakrishna Rao Chair Professor at the Center of Nanoscience and Engineering in the Indian Institute of Science, Bangalore. He is also the chair of National Nanofabrication Center, NNFC, at ISC. Before joining ISC, in 2014, he was in EPIC, Belgium. He received his PhD for his work on wafer scale fabrication technology for silicon photo integrated circuits from Ghent University, EPIC, Belgium. He is an alma mater of Bharatiya University, College of Engineering, Gunde at University of Twente, the Netherlands. He spent over 15 years in silicon and integrated photonics, developing state-of-the-art CMOS process and device technology for high-speed optical interconnect and sensing applications. He has published over 200 research articles and in international journals and conferences at 6 international patents. He is a recipient of BSc Early Career Research Award and Research Faculty Research Fellowship Award from the Ministry of Electronics and Information Technology. His current area of research includes silicon photonics IC, enabled high-speed optical connectivity technology, integrated photonics based on sensors, neuromorphic photonics, and quantum photonics. So, with this, I will hand over the mic to Professor Selvaraja. The floor is yours.
All right. Really, thank you very much for the kind introduction. I hope all of you can hear me.
Yes, sir.
Okay. Thank you. And a special thanks to Dr. Swagata and the organizing committee for this invitation and giving us this platform to share whatever we have done, here at SENS, particularly in my lab as well. Today, I restrict myself to few of the demonstrations that we have done. The whole idea of this talk is to demonstrate how photonics, in particular silicon photonics, could be exploited for various applications, from communication to computing, right? So this is for 30 minutes. Yeah, so I'll just keep a watch. Okay. So first of all, we all know what is the benefit of doing integration, particularly in electronics. So we have went from discrete components that are spread across a board, and we would like to put all this on a single chip. So when we say single chip, the chip is nothing but a thin substrate wherein we realize these functionalities. This is something we know and comprehend every day, and we see the benefit of doing that. Now the question is, what about photonic integrated circuits, right? We understand electronic ICs. What about photonic ICs, right? Photonic ICs come with slight complexity, right? Because we don't have a single device like a transistor, right? That will control the flow of electrons. Here we need to generate photons, we need to detect photons. So so you need to generate photon, detect photon. You should be able to couple the photon between an optical fiber and a chip. And if you are putting a circuit, you should be able to guide the wave, right? So like putting metal stripped to move the electrons wherever you want, you need to have such guides to move the photons. And then we should also have a way to, manipulate wavelengths, right? So we should be able to discriminate different wavelengths and put the wavelengths together. And we should be able to change the property of light, which is called light modulator. And here in my research lab, we work on all these domains. For light sources, we collaborate with material scientists to bring light sources on chip. I'll tell you why. So these are all some of the images that gives a representation of how they look, okay? So the whole idea of doing this is to bring this functionality, right? All the functionalities that I mentioned onto a single die. So what you see on the left side is a die that contains hundreds of functional photonic components. The whole idea of doing this integration is to integrate this functionality, make it very power efficient, and it can operate at very high speed because you know the speed of light, right? So it can operate at very high speeds, and it can be very compact. So we understand optics by looking at lens and so on, right? But now you can really realize a lens system, but much smaller, okay? And because of the speed, you have very low latency, right? And because you can confine a light into a very small volume, it can have very large light matter interaction. And again, you can operate at very different wavelengths as well. So that's the spread that you have. So in this particular talk, I will just give you, a few ideas about how you can use light for photonic ICs, for wired communication, and also how we can use it for wireless communication. And I will briefly touch on how you can do sensing with it, right? Not perhaps chemical, but mechanical sensing. So this is the group that does most of the work, or perhaps all the work that I'm going to present today. This is a old picture. This is from last year. So thanks to all my students and staff members who are doing this fantastic job. Let me give you a background of what we mean by silicon photonics. Silicon as a material we all know. So we all know silicon as a semiconductor material that we use for electronics. But what we are doing here is doing photonics with silicon. So we use silicon waveguides in order to make photonic ICs. And this technology is highly disruptive. And the reason for that is we are reusing the matured silicon CMOS technology and the power of high-speed photonics all on chip, right? And as we know, silicon technology is really scalable, it is mature, and you can integrate whatever material system that you want onto it. And photons, as we all know, can travel very fast, and different wavelengths can move together without crosstalk, unlike electronics, right? And then it is EMI, EMC free, so you don't have to do a lot of shielding when you talk about high frequency application. So you can do interconnects, very small chip level interconnects for next generation high performance computing. You can do it for wireless communication. You can also use the same platform for sensing and spectroscopy as well. Okay, so what is the problem with silicon, and why its operations are limited, right? As we know that silicon is a semiconductor, it's a great material, but there are some limitations as well, right? Limitations could be in terms of transparency. When you look at silicon, it is opaque. That means optically it is not transparent, right? And there are some undesirable properties like two-photon nonlinear absorption, right? And tuning and inefficiencies in tuning could also be a problem. So the way to do that is by bringing new material system into silicon. We'll talk about this, a little bit later, but then I just want to move to what is a photonic IC and how do we make this. Okay, so I already mentioned this. This is what we are going to discuss today, touching on a few of these things. The first problem is light coupling. So why coupling is a big issue? Our waveguides that we make are very tiny, right? So the silicon wire waveguides are about, sub-micron, 400, 500 nanometers, but the optical fiber is very large, right? How do we couple light between these two, right? I have to couple these two. So this is a usual problem that we face every day, and the way that we do this, large aperture to small aperture energy coupling, right, is through funnel. So you use here a very simple funnel, right? And can we use that technique to couple light? And the answer to that is we can do that, right? There are two ways of doing it. One, you have this thin waveguide, and you can come from the side and then you can inject light, or you can shine light from the top, right? So these are all two different ways of coupling light, and they have their own advantages and disadvantages. As you can see here in this particular top illumination, you can have a very large surface, and then you can couple from anywhere that you want. But then if you look at the left side, you need to have access to the sidewall, right? If I have a large substrate, I can only couple from the sides, right? So I have very limited access. So there are other issues in terms of polishing and having it, prepared for this, coupling and so on, right? So the surface coupling is much better in that sense. The way that we do coupling is by using braiding, as I mentioned. So we go through this, a simple case-based representation. As you can see here, we do this diffraction analysis, and based on this analysis, you will know what should be the period of the grading. Speed is nothing but one cycle, right? One tooth and teeth and a trench, right? So you will the sum of these two is called a period, right? So what should be that period, and what should be the fill factor? So those things we design, and based on the design, one can fabricate this device. As you can see here, this is something that's fabricated. You can see here very nice trenches, right, along with the teeth that you see, the diffraction teeth. And this is the top down, right? So you shine light on top, and then the light will be coupled in. You can see here, we can get efficiencies as close as 3.5 dB per coupler. Okay, so why it is 3.5 dB? Can we get it much better, right? Ideally, you want 0 dB loss, right? That means lossless. So the way to do that is by doing some engineering, because the light that comes in, right, can go either top and also bottom. So we put bottom substrate to reflect the light that is going down, and on the top we do what is called mode engineering. So if you can engineer the way that the light is getting diffracted, you can actually improve the efficiency. So this cartoon tells you how the fiber is kept on top, and it is guiding the light into this small channel, that is the waveguide that we have. And we have bottom mirror in order to reflect the light, right? By making all these changes, right, you can actually now improve the efficiency. So here you can see the coupling efficiency is now 1.2 dB, right? So this is over 70% of coupling that you have. out of this, very simple way of doing it, right? So you can have very efficient light coupling into your waveguide. So once you have light coupled into your waveguides, now you can do all kind of interesting things. So the first thing, for any communication, you want to change or put the electrical signal, right, onto the optical carrier, right? That's what modulation is all about. So all the signal that we generate today is all in electrical domain. So we want to convert that into optical carrier and then put it into the channel. The way that we can do it is rather simple. So we all studied about PN junction, right? So we are going back to PN junction. But now instead of just looking at, the charge transport, we are looking at charges along with photons, right? So we have electrons and holes in the junction, but also light is going to be sitting in this junction. So what you see on the left side is a resonator, right, where the light is captured. But then I have a PN junction. So on the right, at the center, you see a cartoon of this junction, how the junction is made, and the waveguide is at the center. So that is where the light is propagating through, and you have the junction here. And the cartoon that you see, the simulated version that you see on the right side, are the electric field when you have different bias, right? So how does this operate? This operate based on a simple charge principle that when you inject the charges into the system, right, into the junction, the charge carrier density goes up. So the charge carrier density is directly proportional to the density of the material itself, what we call refractive index of the material. So the material becomes denser because you put in so much charges, and when you extract it, it goes down. So the density of the material is getting modulated because of this charges, right? And when I change the charge by applying this reverse voltage, you can see here the response also shifts, right? So 20 picometer per volt. Picometer is the wavelength shift per volt that we apply. So when you apply a certain voltage, the response of the device also shifts. And we can shift this with very high speed. We can push and pull the carriers at very high speed. And that is what you see on the right side, that, we are operating this at 25 gigahertz, right? I'm pushing and pulling the charges at 25 gigahertz, and my output light also responds to that, okay? And the question is, okay, 25 gigahertz is good, but can we go even further? So that requires a little bit of engineering into, how this diode works. As you can see here, it's basically a capacitor with series resistance, and then one can look at it and improve this even beyond that, okay? So now I have a way to modulate the light, right? But I can communicate with this modulation very fine, right? It's all good. But now the question is, this is for communication. Can I use this kind of optical circuits for computation, right? So right now, the computation that we do is based on one architecture, where you have this CPU that is talking to memory, right? So what we just saw is a high-speed modulator that can modulate the light from CPU and then transfer it to memory. And then I can transfer it to memory and CPU, because that is what the bottleneck right now is, because that bandwidth is very low, right, between the CPU and the memory. We are trying to address that. But then that is not going to, radically change the way that we do computing. We have realized that this particular architecture, von Neumann architecture, is limited by the hardware and the speed at which that we can move the electrons. But then we also know that the best computer, right, is something that nature has made, right? So all of us and all the living fauna, they have what is called brain, right? Or organic processing unit, right, that takes in the information and it can process it based on neuronal activity. They do this work very efficiently, right, without complex hardware. It's just neurons, and the only thing is the interconnects, right? So the question here is, though we make this, photonics speed and then move the data at very high speed, you will never be able to, do computation as efficiently as, brain. So the idea is, can we build neuromorphic photonics, right? So the idea here is, can we do these kind of operations like we have in our memory, right? Which is non-volatile, by the way, right? Because that's how we remember. The only reason why we can do decisions and calculations is because we can remember things. But for photons, it's very difficult to, put memory in a photon, right? So it is very hard to make an optical memory, unlike electronics where you can store charges, right? So what we do here is to look at the material system that can help us to create non-volatile optical memories, for example, right? And here the material, one of the material systems that we looked at is vanadium dioxide, right? It can go between metallic and insulating phase with a very large change in this optical property, right? You can see here the refractive index of the material can change reasonably high speed. Reasonably at a very high extinction, right? But then you look at the bandwidth, right? The bandwidth is rather low, right? It's about 1.3 megahertz, right? But as I already said, we can operate, silicon and also graphene-based system at very high speeds, right? But these are all conventional speeds. We don't need, such high speed when it comes to, neuromorphic computing, because you are doing things in parallel. Okay, so we should be able to use this low speed of individual devices, but put together they can be highly parallel. Okay, so the way that we did this is by using a ring resonator, where we create a resonance, right? And putting a material on top of this resonator, right? And that material is going to change, right? As a function of an electrical pulse, for example, right? And that is going to affect the resonance of this. So you can see here, the lambda resonance depends on the 2 pi r, which is the circumference, and then N effective is the density of the material. So if there is no change in the absorption, you just move the resonance. So this movement in resonance can be measured as a, right? But if there is a presence of K, that means if it is absorption involved, you are going to not only change the peak, but also the extinction, right? And that is exactly what we did. You can see here, we took a ring cavity, and we have put a VO2 on top, and we activated with a micro heater, right? So when you heat this up, you can see here the extinction actually changes. And it is very clear from the left-hand side, the bottom one, you can see here, when you change the temperature of the material, the refractive index changes, the density of the material changes, right? And that is what we want. And on the right side, you can see the wavelength shift of this particular measurement, and how we can move from different states. And what can we do with this? I think we can do switching with it, right? And that is exactly what we did. This acts like a diode system, right? Where you have two different states, and then by switching it, you can go to different states, right? And these states can be maintained. These are all non-volatile states. So you can go up and down, and by doing that, you're accessing different, states of memory, if you want to. So those are all some of the specifications, and this is how we make it. Yeah. So you have this waveguide, and we put it on top of it. We do a CMP. We make it very flat, right? We first deposit oxide. We make it very flat, and then we put the material on top. Okay. And by doing that, you can see here, very nice shifting in the resonance. And you can see here, this is how we measure it. You have the chip there, and you come in with the optical light in, and then you take the optical out. And here we use wire bonded substrate, where we can feed the the electrical signal. You can nicely see here as the temperature increases, the wavelength shifts, but at the same time, the extinction also shifts. So this is the way to do computing. This is a building block for doing very simple, optical computing. It requires much larger integration, but this is a good demonstration of how we could exploit photonic circuits for this. Light sources. I mentioned that you can also integrate light sources on chip. So what you see here is a simulation of having a dipole, right? If I have an emitter sitting very close to the waveguide, in this case, silicon nitride as a material here, and you can actually capture the light emitted from the dipole into the waveguide, right? So I can, pull the light into the waveguide, and that enhancement is called Purcell enhancement, by using different structures. And in this case, we use waveguide as a resonator to pull in, right? And this strongly depends on the, orientation of your dipole, whether it is normal, whether it is tangential, whether it is parallel. It varies, right? And depending on the type of emitters that you have, one should be able to couple light into your waveguide by just having a quantum dot, for example. And in order to demonstrate this, we have made circuits to operate at 780 nanometer, right? Because that is where a lot of these quantum dots are very active, not just 780, but also 520 as well, where the excitation is. So these are all the waveguides that I talked about, and this is actually the grating where we can put the light in. So we measured the transmission first, so we should know whether the visible light can go through it. The previous demonstration, we showed 1550, which is telecom wavelength. Here we are talking about visible wavelengths, right, below 800, 700 nanometers. So you can see here, we push the light in, right, from the left side, and it travels across, and then it comes out, right? These are all bright spots, and you can see faint spot. This is because you are looking at different material systems. We have to screen the material first, and then check which one is going to be a better suited. And what we found is low pressure chemical vapor deposition as compared to plasma enhanced chemical vapor deposition is a much better option, right? And we did this emitter measurement here. You can see on the left side, we launched the light, and then it goes through, right? This is 520 excitation, and you can see here it is getting scattered, and then it goes through, and here we see, emission coming out, all right? So this emission is coming out because of the fluorescent dye that we have put, just to make sure that we were able to excite it. But on the right side, you can see here, once we excite these quantum dots, we were able to collect the light generated from the quantum dots, and we were able to couple it out. And that is something that you can see here on the left, where we were able to excite the light emitters, right? These are all light sources, coupling light through the waveguide and collecting it through the waveguide as well. So now you can have a source integrated circuit. And the next thing is to integrate a detector, right? So we can integrate a source, we can do all kind of modulation and so on. Now we should also have a detector. How do we integrate a detector? In this case, we use silicon nitride on silicon platform, where we can launch the light in, it travels through the silicon nitride waveguide, and it couples into a silicon photodetector that is sitting underneath, right? So this is your vertical cross section. You go from silicon to silicon nitride, right? And the silicon waveguide here has a PN junction. So we are going back to what we had earlier for the light modulation, right? So PN junction acts as a very good detector. So you generate the charges at the center, and you can pull the charges, by using this junction, right? And we want to understand how good the coupling is going to be, because you're going from nitride to silicon, and you can see here, this is a cross-section simulation where the silicon nitride waveguide is sitting there on top, the light is on the top, and the moment it sees the silicon, it tapers down, right? and then it couples into the silicon photodetector. And the photodetector has a PN junction, and we can take the light out. This is the demonstration of a DC measurement of these detectors. As you can see here, we were able to get about 0.5 amp per watt at 850 nanometers and 630 nanometers, so which are the lower wavelength range. The question is, okay, it works fine at as a DC, as a static device. How does it perform as a high-speed detector? For example, if you want to have processes that are chopped and doing time resolve measurement. So in order to do that, we did a pulsed measurement. As you can see here, it works amazingly well. We were able to demonstrate 0.4 amp per watt as a responsivity with the operating frequency band of 14 gigahertz, right? So these are reasonably high-speed detectors, right? But the only problem that I have with these detectors is long. They are reasonably long, right? Though they work at 14 gigahertz, these are all reasonably long, right? If I make it shorter, it should be able to operate much, faster. But then I might lose my responsivity, right? But then there is always a trade-off. So then we decided, okay, let us try to trade off frequency with responsivity. And what we did there is to put this whole detector in a cavity, right? Cavities are nothing but structures that can, capture the photons, right? So what you see here on the left side is a ring cavity. So I take this ring where I can capture the light that I put into this cavity, and then I put a silicon detector, and the silicon detectors can detect the photons out, right, that are circulating in this cavity. And what you see on the right side is a fabricated device. So you have two silicon, absorbers, and at the center you have silicon nitride waveguide. So we fabricated this in a slightly different way, right? Unlike the previous demonstration, we had PIN junction. Here we are using just MSM detector, that is metal semiconductor metal junction, right? And it works amazingly well. So this is how it looks like, right? So when we have a simple ring without a photodetector, it has very large extension, right? Because light is not absorbed. The moment you put the photodetector, which is absorbing, then the extinction goes down because you are absorbing now. So all those absorbed photons could be measured as a light current here, and you can see here the dark current. The dark currents, you can see here, they are very low, right? So you can see they are, sub 1 nanoamp. So this is lowest dark current you could find in literature. And then we looked at the responsivity for the same length. Initially, we saw about 100 micrometer long detector, right? But now I have only 6 micron. And if I don't have the cavity, this is called waveguide photodetector, just 6 micron long, the responsivity is 0.006 amp per watt. But the same detector, if I put it into a cavity, now I have 2 orders of magnitude improvement in the responsivity. I have about 0.8 amp per watt, which is massive increase in responsivity. Okay, all fair, fine. But how about the speed, right? And that is what you see on the top, the speed at which these diodes operate. So if you look at this waveguide coupled photodetector, these are all reasonably long time, right? So you have 300 picoseconds. It takes very long for the carriers to be collected. However, in a ring cavity, which is inside it, we are operating at sub 80 picoseconds. That comes to about 7.5 gigahertz, right? Electro-optic bandwidth. And with this demonstration, we were able to do first a on-chip high-speed waveguide integrated photodetectors. Okay, so I think I've already 1 minute over time. So I will quickly show you a demonstration of how you could use these these photonic ICs for sensor application, particularly with MEMS, right? It is easy to do optical sensing in a waveguide, but then how do you put 2 different worlds together? One is MEMS and other is photonic IC. Both are in substrate. but how are we going to put it together, right? So MEMS is something that we know that they are very sensitive, and it works with the principle of deflection. So if I put a cantilever, it's going to oscillate, right? And this oscillation depends on the stiffness, the mass of this structure, and also the structure of this cantilever, right? The best way to measure this is either electrical or optical. Electrical measurement is done by piezoelectricity, and optical measurement is done by laser reflection. Okay, so they got their own advantages and disadvantages. Electrical measurements are very easy to do. You just put a probe and then you will measure change in the current, right? Because the resistance changes, piezo-resistive element, but then the resolution is rather limited. However, optical, you have very large, resolution, right? You can measure picometer, shift, but then you need a large laser setup in order to do that. What we thought is, why don't we integrate this optical along with the mechanical structure, right? What you see here is a cantilever and put on top of the photonic IC. So I can put the light in, and this acts as an interferometer. So at the one end, I have this cantilever moving, right, up and down, reflecting the light. At the other end, I have a fixed substrate, right? So they both interfere, and then I can take a modulated output. So what you see on the bottom left is the transmission as a function of gap between this, right? So you can actually measure the motion of this cantilever by looking at the intensity of the light that I get at the output. Right. So we went through all these measurements, by fabricating this device here. This is the fabrication flow here, right? Reasonably a complex flow. We start with the waveguide. We make the bottom electrode. We do the sacrificial layer, and then we deposit cantilever material, and then remove the sacrificial layer. Now you have, a floating cantilever, right? And this is how it looks, right? You start off with the bottom grating, right? And then we process the cantilever on top, right? So this is actually a cantilever that is hanging on top of this grating. So after making this device, we go and measure this, right? So this is the cantilever. We put the light in and we take the light out, and then we measure the frequency response of the light that is coming out. So this is a continuous wave input. This is just a laser, and we modulate. You can see here, you can have resonant modes, excited here by signal generator, and we just put it through the photodetector and we do a lock-in measurement. You can see here, we can measure the mechanical resonance optically very nicely. So this is the first mode, fundamental mode, and you can see here the higher order mode, right? We can also measure the phase transition very nicely. So this is all mechanically oscillating structure integrated on a photonic IC. But this is more sort of monolithic integration. But then MEMS people, they want to do their own kind of evolution of the device, exploration of the device. You don't want to be restricted by the process integration and what you can do and what you cannot do. So what we thought is, maybe we should need a special kind of platform, what we call piezo-integrated, photonics integrated piezo MEMS, where we have photonic chip and then a piezo MEMS chip, right? They are processed in isolation, and then we can bring them together, right? We can put them on top of each other. Now you should be able to do all these mechanically, vibrating structure measured optically through this kind of structure, right? And we did that, right? What you see here at the center is a MEMS frame sitting on top of photonic IC, right? And we did the optical on-chip measurement, and we also did LDD measurement, right? This is laser dominant vibrometry measurement, which is a standard measurement with the MEMS people do. And you can see here a very excellent overlap between our measurement and the standard, benchmarking measurement, right? And we were reasonably happy with this, showing that we can do on-chip measurement with the accuracy that you get from other devices. So I'll quickly brush through this because I'll see how much I have. Yeah, I just have few slides. Okay, so we know that RF transmission is going to be very difficult, going beyond 10, 12 gigahertz, because the free space transmission is very, very lossy, right? So you have to transfer these high frequency signals through optical fiber. We are already doing that, right? So from the central office to the base station, you can use optical fiber, but the problem is, the RF power penalty, right? That what we mean by that is you have power fading, right? When you do double sideband signals, you have, out of phase signal generated because of the sidebands, right? So you have these two sidebands, and when it passes through the optical fiber, the sidebands are going to accumulate, pi phase shift. If they are opposite phase, they will cancel each other. And that is what you see this, all these dips here. If you send a single sideband signal, you should be able to have, fading free any frequency over the whole fiber length. And we came up with a device that can do that, right? We came up with this transfer function that can actually take the carrier and only one of the sidebands, right? And this is the device that you see here that we made, and you can do it tunable and so on. And with that device, we demonstrated, right, over 42 kilometer transmission without power fading over 20 gigahertz, right? So you can see without compensation beyond 9 gigahertz, we are unable to recover the signal. But with compensation, even with 20 gigahertz signal, we were able to send it across a 42 kilometer fiber without any corrections and so on. And you can actually send the data through this. This is just a demonstration of the high-speed data transmission. And finally, I'll stop with this, where all these elements can be put together in order to make the next generation integrated quantum photonic chip. Because we talked about quantum dots, quantum emitters that can be integrated. We talked about how to control the phase and how to control the state by using different material systems, and you can modulate. We talked about how to handle light, right? And then we also looked at how you can detect light. But this was all technology demonstration, but we are looking for new material system integration in order to realize quantum photonic IC. Okay, so with that, I would like to thank everyone for listening. Sorry to say that I went with lower time, because I just want to show what we can do with the platform, right, that can helpful for students who are not aware of the technology.
Thank you, Salvador, sir. This is really a intriguing talk, and time flies by in such talks. So definitely we could understand. We can take a few questions quickly.
Sure.
Anyone from the audience or producers? Yeah, even from online we can take two. So, you can just ask your question. Okay, if there are no questions from the audience, I can ask from my side two queries I have. Sir, the thing is, we talk about the web guides and all. It's all nice, but why can't we integrate the source and the detector itself on the chip, like a system on chip system for a photonic detected circuit? Because detectors for optical is far superior than any electronic detector. They do not require much of a photon to detect nowadays, and sources then cannot, may not be much efficient. They can be sub-efficient lasers. Can they be integrated?
Yeah, so that's what photonic integration is all about. So you want all these functionalities to be integrated on chip, and that is what I was trying to rationalize, that you could integrate photodetectors on chip that can work at multiple gigahertz, right? You can also integrate source on chip, but then it comes down to what kind of material platform that you are using, because for source you need a direct bandgap material that can generate light. But however, for detection, you may not need that, right? Even that's what I showed. Even a silicon is good enough. In principle, you can detect it, but then the source becomes an interesting problem, right? So if you are looking at conventional laser source integration, things are happening. People are doing, printing of transfer printing and bonding of laser sources on top of silicon photonic IC, and also you can do the same for detector as well. We can also make monolithically integrated germanium detectors, which are right now available. So in principle, you can do it. It becomes a little bit integration challenge, but this is very well doable. And there are products out in the market that uses this integrated detectors. Source, perhaps we expect it to come in a couple of years from now. So you will have fully integrated silicon photonic IC that has both source and detector inbuilt. But then there are other applications where you don't need all these things to be integrated. For example, I don't need light source to be integrated. I just need photodetector. In some cases, I don't need detector and source. I want those to be out, and I just want the processing unit to be on chip. So, just to answer your question, it is very well possible. It depends on the material platform that you're choosing. For example, 3-5 based platform, you can realize both detector, waveguides, amplifiers, detectors, all on a single chip. But the only thing is, the circuits are reasonably large, and you need to have a lot of amplification, because the absorption loss is also very high in this direct bandgap materials.
Okay, just one more question. So like we talk about the losses in optical systems, so they mostly come from the metal losses. But when we move to this doped systems, so then the free electrons will also, I guess, interact.
You're absolutely right. I had an equation there, when I talked about the diodes, right? So when you're doing carrier injection, you get two kind of effect, yeah. So both your refractive index changes here, and also the absorption loss also increases. So you don't get a pure phase modulator. So you have phase along with amplitude. You can see here, the extinction is decreasing. So that means there is some absorption loss, right? So if you want a pure phase modulator, silicon is not the best platform. You need to look at other material system and other processes for that. But places where you can accommodate this intensity fluctuation or intensity or amplitude modulation along with phase modulation, you can still use it. I mean, people are using it already. So you're right. It comes with absorption loss along with phase.
Yeah, okay. So thank you. Definitely would have interacted more, but the time is short. So I would like to thank on the behalf of the organizing committee, Mr. Selvaraja, for his time to spare with us for EPIC 2022, and we definitely would look forward for a physical interaction sometime later. We'd like to definitely host you in our university, and we might collaborate with students if they are interested. Definitely.
Sure. I planned to come there, but I couldn't do it because yesterday we were hosting G20 delegation, so I had to be here reasonably late, so I couldn't travel.
You are very busy, so definitely in future, definitely we'd like to host you.
Thank you very much.
Now with this, I would like to hand over the mic to Professor Selvaraja as session chair, so he conduct the session.
Thank you. All right. So I'm done with my talk, so I become tired now. Let me just pull out the schedule. Yeah. So the next talk is an invited talk by Dr. Shamal Mandal from DIAT, Defense Institute of Advanced Technology. He's going to talk about terahertz photonics for futuristic application. Terahertz photonics is really catching up these days, and there are interesting ways of realizing and utilizing various, learning both from the RF side and the photonic side. But this is a dark space in the past, but now it's getting lightened up. And let me give the floor to Dr. Shamal Mandal to share his thoughts and views on terahertz photonics for futuristic applications. Please.
Thank you, Dr. Silvaraja. I hope I'm audible.
You are. You are.
Yeah, thank you. Thank you for this nice introduction. I'd like to share my screen. So my topic is terahertz photonics for futuristic application. I'm Dr. Shamal Mandal, assistant professor at DIIT, Pune. So thank you. I'd like to gratitude my thanks to the organizer for inviting me to give a talk in this conference. So this is my presentation plan. So how much time I have? Sorry.
30 minutes. So you have 30 minutes. I will ping you, when you have 10 minutes and 5 minutes. Yeah.
Okay. Okay.
Please.
Thank you. So this is my presentation plan. What is terahertz? Actually, it is a very nice domain that people are working now in terahertz. So I'd like to quickly go through in this progress of terahertz, application opportunities and challenges with terahertz, and what are the terahertz sources are available, what is the approach for the people to make the terahertz radiation, and then I'd like to focus on these terahertz photoconductive antennas and terahertz tag. This is another application of terahertz. Nowadays it is coming up, and I'd like to take some questions and give my summary there. Okay, so what is terahertz? Terahertz waves are the electromagnetic wave whose frequency range is from 100 gigahertz to 10 terahertz. So you can say that it is 6G communication that will take up with this terahertz. So we know these basics, that from where this electromagnetic spectrum is coming and where is the terahertz band is lying. So it is lying in between the microwaves and IR infrared waves. So you can say that the wavelength is between 30 micrometer to 3 millimeter. So we can, there are many approaches. We can come from the electronics. We know that radio waves, microwaves, people are working with 4Gs, 5G, that in gigahertz range, that is in electronics. And we know that the frequency and wavelength of the visible and infrared waves, it is the photonic side, we can say, and terahertz band is lies in between these two things. So again, what is terahertz? We can say that it is a non-ionizing radiation. It is very safe to the health, not only human but also animal health. And you can say that it can penetrate some non-polar, non-metallic materials. It is very sensitive to the water content. Somewhere this sensitivity to the water content is the, you can say, it is advantage, or somewhere it is disadvantage. So it depends how we are applying this terahertz wave for our application. And this unique, it has very unique amplitude and phase characteristics. That's why it's very popular. So if you compare with the other technology like millimeter wave and infrared or visible light communication or ultraviolet light, so it has the frequency range like this, 100 to 10, 100 gigahertz to 10 terahertz range in short and medium range. And power consumption is medium. Network topology is point-to-point or multi-point communication we can do. And this source, noise source, maybe all thermal noise source, they're generating the terahertz. So terahertz is not a new thing. It has started a long ago. You can say maybe 100 years ago, people have realized the existence of terahertz. But you can say after 1980s, the field is catching up with the advent of laser technology and semiconductor technology. So you can say that people are trying to develop some terahertz detector, terahertz sources, free electron lasers, terahertz systems, terahertz detector arrays, and very low cost and fast component in future. So the terahertz market is really booming. You can say that in 2022, it is almost 350 million euros, and the CAGR with 26%. So it is a very nice field. A very lot of applications are there. You can see it has application in different field like industrial and non-destructive testing, defense and security, biomedical application, and other applications are as well. So people are doing the terahertz communication, terahertz spectroscopy, terahertz imaging, identification, and detection of the things. Please come on. So a few examples I just want to tell you that it can do different kind of industrial application. One of these is that chocolate control, quality control of the chocolate products with terahertz imaging. It's a very non-destructive terahertz imaging. You can identify where the flaws are there and where the chips are there, stone chips, if stone chips are there, or some metal screws are there, or some glass splinters are there. So you can identify all these things at a glance. You can early monitor the mechanical degradation of ancient paper. So there are you can see this. You can check the morphology of the paper, molecular structure of the paper. So every molecules and every element have different characteristics, different signature in terahertz regime. And not only the amplitude, you can also check the phase of that, and it is very useful for different application. So there are applications in crystallinity on terahertz spectra of different kind of drugs. You can say if the crystalline material is there, you have different absorption in terahertz. If it is amorphous, you have different absorption. So there are a lot of opportunities in terahertz regime. So it has a rapid expansion of sensor network and high definition of video streaming. It is possible with the terahertz radiation in daily life. People are going for virtual reality and augmented reality, and which is 20-fold between 2016 to 2021 globally. And according to the report of Cisco, you can say that the total IP traffic reaches 2.3 zettabytes, and 63% of the current traffic will be wireless mobile device. So where terahertz can be a very good platform to transfer the very high speed data. So wireless data rates are expected to be around 10 Gbps or even more in the upcoming decade. And we need that miniaturized antenna. We need this terahertz frequency for this wireless communication nano devices, chip to chip, on chip, security oriented communication, body area network to utilize this terahertz band. We can also do the stealth communication with terahertz tag. That I'll give you some brief idea how that terahertz tag is working, and selectivity of the high data rate links. And it has unique, as I told you, unique molecular and molecular signature in amplitude and phase. So there are a lot of challenges as well, because people are saying this is a terahertz gap. So a lot of challenges are there. So the high atmospheric absorption loss is there. There are spreading loss, mismatch with the classical physical layer and medium across the control layer method. And it has difficulties in the processing of data in terabyte level, terabits level, and design hardware. We need to develop new kind of transducers, transceivers, and antennas, amplifiers, filters, in order to produce this kind of high frequency data signals. You can see it has frequency versus the frequency over frequency. It has different attenuation lines in terahertz regime, And there are disadvantage of advantage with different kind of materials like graphene. The in terahertz regime, people have also used horn antenna, planar antenna for this terahertz band. So I'll come quickly in that. So some more challenges are there, like achievable power. So terahertz power is really low with the previously designed terahertz sources, and conversion efficiency is really low. Tunability is another feature that people want. Spectral and spatial properties in terahertz, compactness, robustness, reasonably priced, because this terahertz technology is new. So people, for this R&D, people are asking for it is a very price things now. And the room temperature operation is another issue with the terahertz generation. So there are different classification we can do that terahertz, how we can generate the terahertz. Incoherent terahertz thermal sources, it's a very very you can say these things are everywhere. These incoherent terahertz thermal sources are generating the terahertz. Spectrally very broad black body radiation is there, which can generate this terahertz. For coherent continuous wave, that is also generating the terahertz, which is a very narrow band terahertz sources. So we can classify like this terahertz sources for long narrow band and terahertz pulses, sources for short wide band terahertz pulses. So according to the kind of physics involved, we can say that terahertz having the classical sources and quantum mechanical sources, terahertz currents, terahertz fields. When we are discussing with this, these things are terahertz classical sources. And when the terahertz photons, we are saying we are generating the terahertz radiation with by the ultrafast lasers, we can say this is a quantum mechanical terahertz source. We can also define it electrons in the vacuum, if it is generating electrons in the vacuum, or molecules in the gases, polarization in the dielectrics, electrons and holes in the semiconductor. According to that, we also divide the terahertz sources. And there are two approaches people are coming from the electronic side and from the optical side. So electronic side, we know that there are different kind of terahertz sources like terahertz semiconductors, electronic sources, Josephson junction, free electron lasers. So from the semiconductor electronic sources, they have this GaN diodes, tunneling diodes, HEMT. All these things are coming from the electronic approach, but photonic approach as well. There are nonlinear frequency mixing processes like difference frequency generation, optical rectification, frequency beating. So those things are coming under photonic approach. Quantum cascade laser is also there, which can generate now this terahertz radiation, and optically pumped molecular gases also giving the terahertz sources. So as you can see here, so this is a map of how the terahertz radiation is coming with the power. So amplifiers are like this here, which is giving you the terahertz frequency around the less than 100 gigahertz, you can say. So if we are going over maybe 1 terahertz, there are very few sources are there. So you can see only the lasers, the ultrafast lasers that has been used to generate the terahertz sources. So we can see here. So these are the quantum cascade lasers, and this is the this is the lasers, and this is the quantum cascade lasers. But this quantum cascade laser is operating in the cryogenic atmosphere. So how we can generate the terahertz from the electronics? You can say it's a bottom-up approach and top-down approach. There are two approaches are there. One is we are generating with the microwave side, from the microwave side and from the optical side. Okay, so from bottom-up approach, we can say that Schottky diode, HF multiplexer, HBT, HEMT antennas are there to generate the terahertz sources, but I'd say that these sources are really low power device. So the moment we are going for this frequency multiplication, the power is getting very low. So it's not that efficient devices, but people still they are using for integrated circuits like a heterojunction bipolar transistors. Here you can see that it's a very nice, very small device, and it can generate the terahertz. You can say it's a classical terahertz generation, and terahertz is propagating through the waveguide. Okay, so high electron mobility devices is as well. So it's like we know that how the MOSFET is working, it is also working similar condition, but it is generating the terahertz radiation due to this electronic motion in the device. So you can compare these kind of materials are there, what are the advantages and disadvantages. So these materials are very popular when we are developing some device in the electronic side. So you can see that this gallium nitride, indium phosphide, graphene, and quantum cascade laser as well, which has there are several advantages and disadvantages as well, because terahertz QCL, it has very low operating temperature and a large in size. If you are going with the graphene based terahertz generator, it is more research required. It's not that mature till now. And indium phosphide, you know that frequency is up to 1.2 terahertz. It cannot go beyond that. And gallium nitride, it has low breakdown voltage in some applications. So these are the disadvantages. How we can cover up this disadvantage? So a terahertz antenna, it's a new thing. People are working with this. They are using a graphene layer in between the two electrodes, you can say, and they are doing the photo mixing there. Okay, so terahertz photo mixing there, and they are generating means sub terahertz radiation with that. So terahertz photoconductive antenna, it's you can say that it is taking the advantage from the electronic and photonic side, and when the high electric field femtosecond laser optical pulse is falling in the gap of some anode and cathode, it is creating the electron hole pair, and due to the undulation from the optical source, optical pulse, it is it is running those electron and holes, generated electron and holes are running towards the cathode and anode, and due to this the charge displacement, you can say the drift of this charge, it is giving you the terahertz radiation. So this terahertz radiation, it is very coherent terahertz radiation, you can say, and this the bandwidth of these terahertz pulses are very high. So we can do some theoretical study with this terahertz PCA, because we are working with terahertz PCA. We can give you some idea how how it is happening. So it is generating the electron hole pair, and then photoexcited carriers with the bias voltage. It is generates that electron hole field, and due to this extra field, it creates that photocurrent and giving you the terahertz radiation. So from one side, if the femtosecond laser pulses are hitting this gap terahertz, you can say that photoconductive antenna gap, and other side the terahertz radiation is coming up. So there are different kind of terahertz PCAs. You can see we have worked with a few of them, like interdigitated photoconductive antenna, slot kind of photoconductive antenna, and fractal photoconductive antenna. So we can give you some idea about that. So we can make some kind of this kind of array here, and we can have some kind of detector, a large aperture size detector with this PCA array. So we have analyzed these things, this interdigitated photoconductive antenna, and it has several advantages over the other the sources of terahertz generation and detection, like increase in intensity of the terahertz waves. It has reduced air substrate in interface reflections, and this high carrier mobility, high electric field amplitude, less screening effect, and reduced drift length of the carriers. So like that, we analyzed that equivalence.
Dr. 10 minutes.
So there are different results are there. You can see that the bandwidth of this terahertz is more than 18 terahertz. So it's a very large bandwidth you can get, and very high electric field you can get with this. And we have summarized these results. I'm not going to the detail. So another terahertz antenna is called short-tooth PCA and fractal antenna. So here you can see that when we have this fractality in this, so that terahertz generation and terahertz radiation is very wide, and we can also tune the terahertz radiation. So the results I have not shown here. And there is another thing, it is called terahertz tag. We know that there are different kind of tags that are present in the market, like barcode, QR code, radio frequency, ID, RFID. So these tags are there, but you know that it has some disadvantages, like you know that they're difficult to use these tags as unique tags, because it can be copied easily, this barcode or QR code. And you know that the RFID, this is really big RFID chips are there. So and you have to put these things in a many number of chipless RFID tags have been focused on the price reduction. So we know that it has a little bit priced, and these RFID readers are still expensive, and you can say very complicated, owing for diffraction problems. So these things we can overcome with the terahertz tag. So you can see there are different kind of RFID chipless tags on different methods. So TDR method and a spectral signature based method, and amplitude, phase, and modulation methods are there. So what is the advantage of a terahertz tag? So that terahertz tag, you can do some packaged form, and it is a physical structure. You can put these things inside your package, inside your packet. So because terahertz can propagate through several materials like cardboard, like paper, clothes. So, and it's a very small chip that people can carry in their body, and it can create some body area network. You can see that terahertz tag in indoor and outdoor communication, it can be used. So next generation wireless network is coming with this terahertz tag. So it is equipped with sensors and can form a wireless network through which an information can be easily accessible and can be delivered very fast to the right person with security when it is needed. And 6G network based on this millimeter wave and terahertz frequency, it can give you the very better accuracy from this conventional GPS and then localized techniques that is provided. So we can have this kind of mini network with terahertz Wi-Fi, Tera IoT, or Tera IAB, or Tera Spacecom. So we can create. So another application with terahertz tag is that localization and identification of desired object personal through this hidden tag. So if a secured item is passing through that gate, and if thousands of packets are similar, so we can identify clearly what is the material there if we put the terahertz tag with this. The advantage of this terahertz tag, it is a volumetric information you can give. So it's like a book. In every page you can store different kind of information in that, and it's a very small thing. So it's a volumetric tag, and you can put it inside. So we can do the scanning. So if a terahertz you can say robot is there, which is carrying that terahertz radiation, terahertz generation and detection, with the reflection geometry, you can identify all these boxes, what are the things are there. But it cannot be accessed at a very far region. So it is in that sense, it is very secure, and you can get the identification as well. So there are some possibilities how we can sort out thousands of DVD, but the required information is in one. So how can we identify that? So there are thousands of boxes. How can we identify quickly inside that where without any tampering on those? Our personnel are involved in some geopolitical movement, how we can identify and share some correct information. So durable tags, it's a very durable, we can do with the polymer material, and it have the data retention ratio than more than other tags, and it can also be remain in the key in research in near future. So people are working with different kind of terahertz tag. So you can see some papers here recently with this terahertz tag. It's a volumetric tag, as I told you, and we can store that information for a longer time in this kind of tags. So so I have 5 minutes, right? So terahertz spectroscopy
you
and
have
image.
about 4 minutes, yeah.
Yeah. So terahertz spectroscopy and imaging we are doing here in DIIT, and we are using either this photoconductive antennas or the ZNT crystal and other gallium phosphide crystal here at DIIT, and measuring some non-linearity and the terahertz spectroscopy, time domain spectroscopy, and terahertz imaging as well. So those things we are doing here. These things we have done at Daresbury Laboratory, UK, where we are involved in the high power terahertz generation and detection setup with this high power Tisafer amplifier and this petawatt laser. So we are doing this for this electron beam acceleration. It's a tabletop accelerator when this terahertz beam is accelerating the electron bunch. So it's a very nice experiment, and in summary, we can say that terahertz technology is the future technology, and it is for the future generation. People are working on that, and it has a lot of promises in this domain. So it has a great impact in sensing and detection and imaging, and there is no competitor till now in terahertz using this terahertz technology for the sensing and detection, because it can detect the plastic explosive which other metal detector and other X-ray detectors those cannot detect. So there are also challenges in development of this stable high power terahertz sources. People are working on that, as well as DIIT. And terahertz PCAs, it's a very compact terahertz sources and detectors. We are trying to implement some of those at the DIIT, and we know that now what is the utilities and usefulness of this terahertz tag, and the more application, many more application will come in future with terahertz tag, and this superiority in sensitivity, fast response, and ease of integration makes this terahertz technology inevitable. and you can say that upcoming communication, remote sensing, unique identification will be based on terahertz. So with that, I would like to acknowledge my funding agencies, DIIT, DRDO, and UGC, etc. And I'd like to thank my students who are helping me in developing these setups here. And we are doing also some simulation work with different softwares, and my students are doing that. And I would also like to thank my colleagues and collaborators for doing the very good research in this field. So there are opportunities to the MTech and PhD student to work in DIIT with DRDO projects, and always these collaborative projects in these kind of topics are welcome, with high power ultrafast fiber laser and solid state lasers. If you want to measure some nonlinearities and optical processes, if you want to work with terahertz photonics, you are welcome. So you can visit always this DIIT physics department website, and this is my website. You can visit. There are some references, and thank you for your attention. So I'd be happy to accept.
Yeah, thank you, Dr. Manal, for a very interesting overview about terahertz generation detection, and primarily covering what are all the challenges and so on. We have time for one quick question before we go into the contributor talks. Are there any questions here for Dr. Manal? I don't see anything on the chat yet. So
Yeah, I have a question.
Yeah, please go ahead.
Yes, so thank you, Dr. Samuel. It's a really nice talk. Just one quick question, like you were showing gallium arsenide PCAs with LT-gas PCAs with a bandwidth around 10-50 terahertz with your experimental results. But I'm just curious how it is overcoming the photonic absorption bands of gallium arsenide around 6 terahertz.
Sorry.
So the photon absorption bands for gallium arsenide is around 6 terahertz. So how your results are overcoming that? Because we also did a lot of work on that, and we always used to get stuck up with that.
So we did some experiment as well, and we are getting the more than 10 terahertz with a different kind of thing. And if you go into the nanometer level, like we have simulated these structures, this interdigitated photoconductive antenna, and that 20 nanometer of this teeth width, it will give you more than 15 terahertz radiation, that bandwidth. But the problem is that you need a very good facility to fabricate those kind of structure, like electron beam lithography, and we are trying, but we didn't achieve that till now. But up to 10 terahertz we have achieved, means experimentally as well. Yeah. So okay. This photonic, what is your concern?
Gallium arsenide, the lattice absorption, photon absorption.
Yeah, lattice absorption.
So his question is about the loss. If you look at the generation spectrum, you should be able to see an absorption dip at around 6 because of phonons and gallium arsenide. So that is the question, I believe.
Absorption dip is always there in between gap, but apart from that, after that absorption dip, you can have more terahertz radiation. So it's not like that it is propagating over the terahertz band. There are some dips at 6 terahertz, but after that as well it is continuous there. So you can utilize that band, and if you tune that terahertz gap, the interdigitated gap as well, or fractal gap, so you can utilize the other part of the terahertz radiation band.
Okay.
I hope I answered this question.
Thank you.
Yeah. Good.
Keep in touch.
Yes.
Thank you very much for the talk, Dr. Mandal. Very interesting. We will move on to the contributed talk section. So the first talk is, design of multi-band stepped antenna for 5G applications. And the talk is going to be delivered by A. Jansi Rani. I'm not sure this is online or.
Are you available? Jansi Rani, are you available? Anyone?
Yes, sir.
Okay. So it is Vandana.
Yes, sir.
Okay, I'll allow you to share the screen. Just wait.
Share the screen.
Okay, sir.
Yes, so you can now share the screen. Yeah, you are allowed to share your screen. Yes, you are visible.
Is it visible, sir?
It is visible. Could you put it to presentation mode, please?
Okay, sir.
Okay. Thank you very much. So you have 10 minutes, please.
Yes, sir. Good afternoon, sir. We are from Velagud Ramakrishna Siddhartha Engineering College, sir. So our design is basically of a 5G application based design of a multi-band stepped antenna. As we are all aware of that 5G applications were the emerging technology nowadays. So we have decided to go through with the 5G application. Apart from this, we have also decided to have a simple design that could operate at various bands and providing multi applications. So coming to the design, our design is basically a step design having an elliptical slot, and this design got operated at KU and K bands at 14 and 25 gigahertz, having a proper VSWR and return loss of minus 21 dB and minus 16 dB. On considering with the base design, we have made certain modifications. And here we have this the figure 3 denoting the base design, as they have made few steps and a circular slot. Coming to our design, we have made the similar structure but varying in different parameters. We have made all the steps as the rectangular steps in the rectangular shape, and we considered an elliptical structure evolving from a square, a circular, and some other shapes. Coming to the proper design, the modifications we have done where we have reduced the size, and also the purpose of having this elliptical slot and the steps were to operate the structure at multiple bands. Upon simulation, we have got the results as for the elliptical slot, we have got the resonating frequencies as 14 gigahertz and 25.7 gigahertz. And we have also simulated other structures for reference in the process of evolution. We have placed the comparison in this slide, sir. The first parameter denoting the resonating frequencies of the base design, they have considered very low frequencies. So the major modification we had done is to operate the design at higher frequencies for 5G applications. So the operating frequency was considered as 25 gigahertz, and we have the written laws and VSWR as placed in these slides. As the design size decreases, we can increase the frequency in order to operate this at higher frequencies. We have reduced the size for approximately half of the base design that we have considered. These were the comparisons between the various designs that we had simulated. So that's all about our design, sir. Upon various trial and error method analysis, we have decided that elliptical slot in the stepped structure of the antenna.
Good. Thank you. I have a quick question. So you have designed this different elliptical, square, and so on, right? So how do you decide where to put the, the defect? So basically, for filter, you need to have that. So, so my first question is, where do you put it? And also, have you thought about? Let's first start with that. I mean, how do you decide where to put this ring, elliptical ring or square? How do you decide?
We didn't discuss on placing that slot at a particular location, sir, but we would like to place that in the structure where it can operate in the multiple bands. So when we got placed that in the center, it got resonated in multiple bands. So we finalized that, sir.
Okay. And have you looked at doing multiple such cavities? So instead of a single oval or a single rectangle, have you looked at bifurcating it and then see how the field evolves?
Sorry, sir, we can't get you. Can you repeat the question?
No, if you have right now you have a single cavity, right? So you have either a rectangle or a single ellipse. Yes. Have you thought about putting two rectangles or two ellipses in proximity?
No, sir. We haven't gone through that.
Okay, fine. So now you in your conclusion, you mentioned that you're looking at these K-band and Q-band for operating, right? Then your interest, can you go back, is to operate these resonators at a larger band or very narrow band, because you did have multi-band, right? So one of the reasons in multi-band is you will always have band crosstalks, right? Have you looked at crosstalk? Band to band crosstalks?
No, sir.
Okay, fine, good. I don't have any other questions. Are there questions from the participants here, online, offline?
Yeah, one quick question from my side too. So you showed a stepped design. So instead of a step design, why can't we have a slant direct trapezoid design?
Or the photograph in your scripts. Again, this is Vasudev, and this is
okay, sir. Then I think we can.
Yeah, we can move on. Thank you very much.
Thank you.
Thank you. We'll move to the next talk. So the next talk is microwave differential CSRR sensor for liquid permittivity measurement. And the presenter here is Gauri Shankar Das. I can see. So could you please share your screen?
Yes, sir. Please allow me to share my screen, sir. Now it is visible. Yeah. Yeah. Okay. Okay, sir. I hope my screen is visible, sir.
Yes.
Okay. So I'm Gauri Shankar Das, and my presentation is basically about microwave differential sensors, and I'm from Dibrugarh University, Assam. And my outlook. Yes,
can I make a small request? If you are having all right, you can turn on your video.
Hello, video. Yeah. Okay.
Yes, thank you.
Okay. So yes, so this is the outline of my presentation. So the presentation is basically divided into these parts. First, I will discuss about the material characterization in terms of the permittivity. Then I will discuss about some methods of permittivity measurement. And then I will go to the microwave ring resonator and complementary split ring resonators. And finally, about the differential microwave sensors and the conclusion. So the basic idea, sorry, the screen is not changing actually. Let me see. Okay, now it's changing. Okay, so yeah, I hope it is changing.
Yes.
Okay, sir, thank you. So the basic idea about this work is that we are basically targeting the material property permittivity, and we all know that how permittivity is important when we are dealing with material under an electric field, and it basically tells us with what ease or difficulty a material can be polarized. So that is why the permittivity can be a very important parameter in many kind of assessment. And especially we are talking about the biomedical application, food and agri industries, and applications like non-invasive glucose monitoring systems, like adulteration systems, like to determine the amount of water contents in different types of food items. So all in these places now, the permittivity measurement techniques has been adopted. Now in permittivity measurement, there are different ways with the help of which permittivity can be measured or assessed. But here we are targeting again the microwave techniques, because this techniques has emerged as one of the most prominent and good amount of work is going in this particular field. And in the microwave domain also, in fact, there are many different kind of methods, but again, we will be discussing mostly about one type of methods. But some of the advantages of the microwave techniques are like, they can be very smaller in size. The sensor may be smaller in size. It is a non-invasive process and low sample preparations requirement. And also the amount of volume of sample that is required can be also very low in comparison to other methods. Now here I'm showing some of the methods in the microwave domain, different types of microwave methods that are being used for the measurement of the permittivity, the complex permittivity of the materials. As you can see in the table, there are different types of methods like transmission line method, like free space method, the open-ended coaxial probe method. In fact, the open-ended coaxial probe methods are available as a commercial sensor in the market. And also we can see what are the basic parameters like the S11 or S21s, because some of them are relying on the return loss and some of them are relying on the transmission coefficient, and also the properties or the parameters that can be measured with the help of the different method. So we are trying here the resonant method, which can be used for solid and liquid, both the samples, and basically the transmission coefficients are used, and with the help of this the complex permittivity as well as the permeability can be measured. And under the resonant method, we are basically proposing or doing the work in the field by using dielectric resonator planar sensors, using the ring structure because of its very simple design and low cost. So now when it comes to the ring resonator methods, this is some kind of history. I will not read out basic things. So basically, we all know that the copper layers having the dielectric, something like the FR4 boards that we use in this microwave planar sensors. So basically they are replacing the waveguides in some sense. And If we go to the papers of Trafton et al., we have seen that they have introduced the idea of some kind of ring structures on the surface of the FFO boards or planar sensors, and this kind of rings can basically behave as a resonator, and that was the basic idea. And after that, many researchers have gone, and developments like the split ring resonators and complementary split ring resonators have been proposed over the years. Now, the split ring resonators and complementary split ring resonator both are basically resonator circuits which can be designed to resonate at a particular frequency. The complementary split ring resonator will be have been adopted by us because from literature work as well as from our own work, we have seen that this has been able to deliver a higher quality factors and more sensitivity in comparison to the splitting resonators. And the basic underlying principle behind this sensing is that when we introduce the material or the specimen with the sensor, then there is a change in the what I call is the overall permittivity of the system, and because of that permittivity, there is a change in the resonant frequency of the system. And through the change in the resonant frequency, we can determine the unknown or the permittivity of the sample. So this is basically the idea. And on the right side, you can see a figure where we are showing some kind of electric field distribution. This is basically an SFHS MS. I will explain why we are using this figure in a later part. So basically, the idea is that we are going to use some kind of ring structures as a resonator, and the ring structure and the resonator will be used for sensing or finding out the permittivity of different kind of materials. Here we are using liquids, and as I have already mentioned, solids can be also used as a specimen. Now, this is the basic layout. We can see here some design parameters, not parameters, actually the theory of the CSS are given. And on the side by side, we have also shown the equivalent circuit. So it is a complementary split ring resonator. That's why the feed line is on the other side. And we can see some rings are there, and the sample holder is placed at the appropriate position. Now, this is going to behave as a parallel resonance circuit, parallel LCS circuit, going to absorb the microwave signal launched into the sensor. And since we are using ASFSs for designing all this process, so this is an ASFSs interface, and ADS interface has been used. Advanced design system by Keysight has been used to produce the equivalent circuit. Now, these are some of the fabricated sensors. I will discuss about this later. So these are some of the fabricated sensors, and now, basically, main discussion or the things that we are going to highlight in this presentation is about the differential sensor, not the regular sensors. The reason behind is that, first of all, as you can see in the figure, the differential sensors have got two sensing elements, which is symmetrically placed on one side of the planar resonator sensor. So the idea behind the differential sensor is that what happens to the regular sensor is that whenever there is a environmental fluctuations like very high change in temperature and other factors, during the experimentation, because we always consider one reference as the reference when there is no specimen or material is loaded into the sensor. So whenever there is a big fluctuation in temperature, there may be errors in the calculation or in the result or assessment process. So that's why this differential sensors has been proposed. And in the differential sensor, the good thing is that even if there is an environmental changes during the experimental process, the reference level also shift with the change in the temperature of other parameters. So this basically eliminates or minimizes the possible errors due to the environmental changes. Now, what you can see on the figure you can see there are, I have shown here the result for air and water first. So what you see here is that you can see, as far if I consider the red line, which is the air. So air means we are not placing any kind of specimen. In basically one of the sensing element is loaded with the material under test. And suppose we are not loading or it is an unloaded condition, then there will be only a single notch. And you can see the red one, which is for air, it has got only single notch. But when I have introduced water in one of the sensing element where my sample holder is present, then I can immediately see there are two notches, one green at the original position and one green on the left side. So it basically referring that the undisturbed position is because of the reference value, and the new shifted position is because of the specimen or the material under test loaded into the sensor. So what happens if suppose during the experimentation, the temperature changes or any other parameters that can influence the measurement changes, then this red or the green line will also shift. And since we basically use the separation between this or shift between this with the original reference position. So any possible errors can be eliminated with the help of this differential sensor. Now, this is the proposed differential sensor. It basically employs two complementary split ring resonators, as you can see from the figure. The green one here represents the sample holder where we are going to place the sample. For our case, it is a liquid sample. And you can see the backside where the feed lines are used, microstrip feed lines are used. And on the other side, we have also shown the equivalent circuit, which is again developed through the ADS. And on the right-hand side, we can see the electric field intensity distribution for the differential sensor. The red zones basically indicates the places where the electric field is high. That means if we place the sensor at this position, we can expect a higher level of interaction with the field because of the specimen. And that's why, accordingly, what we do is that we place this sample holder at positions which is close to the red positions. And that's why you can see it is centrally located. Now, the dimension that we have used for this differential sensors are given here. I will not read out all the statements. It is a 1.6 millimeter FR4 board, and the external dimension is 52 into 30 mm. So it's not a very big in size. In fact, it can be reduced with further optimization. And some other parameters are given here. So I will not read out all this information. Now, this is an important part that since it is a sensor, and most important parameter that can be assessed for a sensor is the sensitivity. And how we measure the sensitivity, this is the standard relation for measuring the sensitivity. So what we can see, the sensitivity is basically nothing but change in the resonant frequency, as you can see delta F, with respect to change in the dielectric constant. And how it is obtained, we are using the unloaded condition, that means air as the reference with the specimen under test. So this is how we measure the sensitivity. And below the sensitivity, you can see the normalized sensitivity is given. This is another important parameter or factor, which is used because if we go through the literatures, we see that many researchers have proposed a sensor at different frequencies. There is no standardization of microwave sensors. So when we try to compare the sensors with one another, then it's difficult to compare the sensitivity because at different frequency level, you can experience different levels of shift for the same amount of change in dielectric constant. So to normalize that, what we do is that we basically divide the frequency by resonant frequency, and we get the normalized sensitivity. And through the normalized sensitivity, we can compare the different types of sensors which are working at different temperatures. Yeah, now I'm coming to the results and analysis part. So what we have done, the tests, the sensor that we have shown there have been loaded with 4 different types of liquid. The reason of selecting these liquids is very random. This was basically easily available liquids. That's why they have been taken. And also we try to cover a wider range. So you can see that's why that acetonitrile, then hydrogen peroxide, water, formamide, all have been taken. And these materials have got very high level of dielectric constants, and that's why we have taken so that it can cover a wider ranges. And also now the frequencies can be seen here in the table, and the corresponding shift in the frequencies can be seen. So what we see that the undisturbed position, that means the reference position due to the unloaded condition, and this on the left side, the shifts are due to the specimen loaded into sample. And on the basis of this, we can calculate the sensitivity, and the sensitivity is found to be 11.675 megahertz per unit dielectric constant, and the normalized sensitivity is found to be 0.496%. Now, on the basis of this data that we have obtained from this table, we can also say that we have, in one sense, tried to calibrate the sensor. And after getting all this data, the four samples in the air sample, we have fitted them the values against the dielectric constant, and we obtain this particular equation. Now, the good thing about this equation is that if we substitute, suppose now I take a unknown sample and just insert it into a liquid holder or sample holder, and I get a shift in the resonant frequency. And then on the basis of the resonant frequency information from this equation, we can calculate the dielectric constant of the unknown sample. So basically, this is how the differential sensor is going to operate. And these are my conclusion. So basically, we have designed a complementary split ring differential sensor, and the sensor has been optimized to give better sensitivity. Then we found an sensitivity of around 11.675 megahertz per unit dielectric constant. The normalized sensitivity is 0.496%. The Q factor is quite high, 200, if we compare with other literatures. Then we have developed a fit equation, and on the basis of the fit equations, this sensor can be used to find the permittivity of different unknown samples. And once the sample is fabricated, it is likely to be a good alternative to other expensive commercial sensors. So now at present, the sensor has not been fabricated because a little more maybe what I call testing and optimization may be still required, I believe, because we have to cover almost the entire range starting from 1 to 111 dielectric constant, and to see how it's going to deliver on that, on that all the tests. So these are my references, or some of the references, of course, not including all the references. So thank you. So this is my presentation.
Thank you very much. Very interesting. So now the paper is open for any questions. So offline and online participant, any questions to the speaker?
Okay, so I have a question.
Yes, sir.
Yeah, it's great. First of all, I'll congratulate on nice work. Thing is, first question is how much deviation you are measuring when you are doing the prediction from a simulation to experimental results and measured result.
Yes, sir.
Deviation you are expecting. And
okay.
How are you modeling the liquid? Are you measuring the liquid's permittivity beforehand, before the experiment? What you are using?
Okay, sir.
What is the purity of the liquid you are using?
Yes, sir. So the first question is that when we have designed the sensor, basically the differential sensor is the new part. So first we have designed the complementary splitting resonator, that means in non-differential form. And when we have obtained the unknown values, in fact we have used 2-3 samples to find out that how good enough this sensor is. Then we have found that basically the error was limited to less than 4%, with comparison to literature values and commercial sensor values. So it was basically consistently delivering an error less than 4% in comparison to the literature value as well as with the commercial value. But this is not for the differential sensor, because as I have already seen, it is in the intermediate stage. But the single element commercial sensor was delivering less than 4% error. That was the first thing. Then as far as the selection of different types of liquids are concerned, so liquids were first selected on the basis of easy availability and on the basis of different values of dielectric constant, because we are only targeting to scale the sensor on values which is widespread, and it can cover from starting from 1,4 and going up to formamide 111 and like that. And regarding purity and other facts are considered. So it basically, it's whatever the basic level is available in the market. That means I'm not saying it's a highly pure or the 100% pure. So we are using that material, and the cross verification has been done by using commercial sensors, and then the standard literature values has been used for the anti-fabrication process. So it's not about the, there is no specification or there is no specialty about the liquids that I have selected. These are basically on the basis of availability. And I believe that this is going to deliver the same result for any kind of liquids we can use. In fact, if we go through the literature, we can see that people are doing works. They simply takes ethanol or methanol and then add water with them, and they vary the concentration and they note the different kind of resonant frequency shift. So it can be, the idea can be extended for all different kinds of liquids. So it is not restricted by any, that kind of things. So that is what I believe. Yeah.
Can you then model your device in such a way that you can predict the different concentrations of the mixing of different liquids? So let's start with two liquids. You need different concentration, and can you predict it back with your sensing data?
Yes, actually, we have not done that work, but when we go through the literature, and we believe that we can also do that, because right now we are only targeting different unknown samples. Unknown samples means that are known, but we are assuming that to be unknown. But what you are saying, that different concentration, that can be done, because we have seen that by using different concentrations. Suppose, as I have already given you the example, that I take suppose ethanol, methanol, or any other one, then I take different concentration. I add water at 10%, 20%, 30%. Then this sensor is going to give the corresponding shift. The shift is going to change accordingly. The concentration is changing. So although we have not experimented that, but I believe that it is going to, going to do it properly, and different concentration can be identified easily on the basis of the change in permittivity. Yes, sir.
Thank you.
Good. Thank you very much. In the interest of time, I think we will move on to the
Thank you, sir. Thank
next
you, sir.
very interesting talk. Mr. Das.
You can answer.
Yes, sir.
So the next talk is on comparative analysis of indium phosphide dielectric based plasmonic sensors in the optical communication band. So the presenter, the first author is K. Santi, who I'm not sure I can see. Shambhavi Shukla, I presume another author here. So you're going to present?
Yes, sir. So, sir, good afternoon, sir. Actually, Kshitij, the presenting student. So, actually, sir, he's not keeping well, so I'll be
okay, fine, fair enough. No issues. At least someone can present the paper.
I'll share the screen,
so
sir.
Please share the screen. Yes, go ahead. And may I request Dr. Rana to take over because I have to leave right now. It's already one. So thank you very much. And
before you leave, so thank you on behalf of the organizing committee to be part and spend your valuable time with us. Definitely, we'd like some time later physical.
I'll definitely try to do that because Swamita was very keen. I'll definitely make it sure. All right. Good. Thank you very much. I don't want to hold any more time. Thank you.
Thanks.
So, shall I start, sir?
Yes, please.
Okay. So, good afternoon to all. Myself, Shambhavi from BITS Pilani. So, today in this talk, I'm going to talk about the comparative analysis of indium phosphide dielectric based plasmonic sensors in the optical communication band. So, in the beginning, first, let me introduce you to the world of surface plasmons in the introduction part, and then we'll be moving to like what motivated us to moving towards indium phosphide based sensors, and then moving towards our proposed plasmonic configurations and its effect on different 2D nanomaterials. Finally, the performance sensing analysis, and we'll be comparing our work with the previously reported work, and then I'll conclude my talk. So beginning with what is surface plasmon resonance, that is SPR, or the conventional Kretschmann configuration, that is the story where all the surface plasmon resonance phenomena started. So in this conventional Kretschmann configuration, we have a glass prism above, over which we have a thin metal film and an analyte. And this comprises of a Kretschmann configuration which deals with the phenomena of total internal reflection. So when a TM polarized light strikes the metal analyte interface, so as I said, TIR condition, so as with the angle greater than the critical angle, we expect that almost all the light to be reflected. So as we know that it's a TIR condition, so we have some evanescence also generated. So as soon as the wave matching condition occurs at the interface, we will see that our surface plasmons are generated. So what are actually surface plasmons? So surface plasmons are nothing that they are just that as soon as the phase matching condition occurs at the interface, then the energy gets transferred from the incident light photons to the conduction electrons of the metals. And thereafter, the continuous oscillation of those conduction electrons gives rise to an entity called as surface plasma. So when I talk about the phase matching condition, this is the one that we have mentioned here. That is when the wave vector of free space wave vector multiplied by the prism refractive index NP multiplied with the tangential component of the incident light, when it is equated to the surface plasmon wave vector. That is the free space wave vector multiplied by the average refractive index of the metal analyte interface. So as soon as this phase matching condition occurs, we see that the surface plasmon resonance is generated. According to the dispersion diagram also, you can see that when we talk about the light line, that is the black line, here, since it is not intersecting with the red line, that is the surface plasmon line. So if it is not intersecting, but as soon as I introduce this prism, then this black line it reduces to this blue line, and it is intersecting, and it is this point where the phase matching and hence the SPR phenomena occurs. So what is the motivation? So as we know that now the need of the hour is to produce high quality biosensors in order to have better fabrication techniques. When I talk about high quality biosensors, so I'm talking about better detection accuracy and better signal contrast, higher sensitivity and higher line width. So that I'll be discussing subsequently. Now gold, silver and aluminum are some of the plasmonic metals. They are the famous plasmonic metals that initiate the plasmonic activity. And with their optimal thicknesses, we'll be considering our plasmonic configurations. Thirdly, in the NIR region. So till now, or I would rather say that over the past few years, people have started working in the NIR region also. But so far, our exclusive work on plasmonic sensors is being done in the visible region. And why to go into the NIR region? Because when we talk about the near infrared region, it deals with non-destructive analysis and in vivo imaging. So when I say in vivo imaging means when I'm going inside the components of the cell, when I want to see the nucleus or the cytoplasm of the cell, that is in vivo imaging. And non-destructive analysis is like the biosamples are not having any kind of photo damage when it comes to the NIR region. And lastly, when I talk about indium phosphide, as compared to the other dielectrics, it is giving us better performance sensing parameters. So this entire simulation that we have done, it is according to the transfer matrix method that we have followed for the angle interrogation part. So transfer matrix method is basically a kind of modeling that is used for homogeneous layers. So as I showed previously, that our configuration is based on homogeneous layers. So that's why in this kind of modeling, we use the transfer matrix method, wherein for an n-layer matrix, we consider it along the z direction. We have the tangential components of electric and magnetic field. So these electric and magnetic field tangential components are converted to the characteristic matrix method. And according to the characteristic matrix method, certain mathematics is followed, which leads to finally we have some eigenvalues. So those eigenvalues are given in form of reflection and transmission coefficient. So this is how, as soon as we obtain the reflection and transmission coefficient, we're able to get our optical output in terms of reflectivity spectra or transmittivity spectra, depending upon our requirement. So this is the sequence of steps that we follow in our entire code while simulating our devices. That is, firstly, we specify the range of angles, like from if I have to see my optical output from from 70 degree to 90 degree, or what is the range of angles. Then I define what are my dielectric constants and the thicknesses of the intermediate layers from the metal to the analyte. Then optimizing the parameters, like the parameters, when I say, I talk about optimizing the sensitivity and the figure of merit and the line width. And then finally, we'll be studying our output in terms of the reflection dips. So beginning with the gold-based configuration. So firstly, we took simple gold-based plasmonic device. So one by one, we'll be optimizing gold, aluminum, and silver. So firstly, in a gold-based crystalline configuration, we are trying to optimize our the thickness of the gold on the basis of two parameters. Like you can see that this is our optical. As soon as I keep on varying my resonant angle and I keep on changing the thicknesses of the layers, my resonant angle is changing. But as I see that if on reducing, like at reduced thicknesses, like suppose at 25 nanometer, the even the reflection minimized burst and also the line width is also very high. So there has to be, we are trying to come at a compromise where both our reflection minima is also maximum, and at the same time our line width, that is the full width half maximum, because if the line width is lesser will be, better will be the detection accuracy, or rather I'll say better will be the signal contrast. So from this graph you can see that 35 nanometer comes out to be the optimal thickness for the gold based Frenchman configuration. Similarly, we follow the similar procedure for silver as well as aluminum. For silver, you can see 50 nanometer, the pink one gives us minimum reflection. So minimum reflection means maximum absorption, or you can say maximum coupling took place at this resonant, this particular resonant angle. So that's why we have 50 nanometer on the optimized one for silver and 30 nanometer for aluminum based configuration. So as of now, we have just optimized the metal plasmonic metal layer. Now above which I will be inserting my dielectric in between the metal and the analyte. So now one by one we'll be seeing that how the analyte, how the dielectric based gold indium phosphide based plasmonic devices, how are we trying to optimize the thickness of indium phosphide. So we just had a trade-off between sensitivity and figure of merit. Why we needed a trade-off? Because as soon as I was increasing my thickness of indium phosphide, although my sensitivity was increasing, but at the same time my figure of merit was reducing. So let me just pause here and tell you that figure of merit is the ratio of the line sensitivity and the line width. So at the same time, you can't say that why not to have a trade-off between sensitivity and line width, because at one time either the sensitivity is going to increase or my line width is also at the same time deteriorating. So I have to take care of both. So that's why sensitivity and figure of merit. So all the sensitivity is increasing, but figure of merit is decreasing. So I needed to have a a trade-off, like where I can get an optimum thickness. So at 7 nanometer of indium phosphide layer over thin gold film provided an optimum sensitivity and the figure of merit as compared to our conventional gold-based Richmond configuration. Similar analysis was done for silver as well as aluminum-based. So in silver, our optimum thickness came out to be 8 nanometer for indium phosphide, and again 8 nanometer in the case of aluminum indium phosphide-based plasmonic device. Now we have come up with a comparative analysis on gold indium phosphide based plasmonic devices and how different 2D nanomaterials on monolayer, on different 2D nanomaterials monolayer when they are applied above the dielectric. So why are we inserting the biorecognition elements of the 2D nanomaterials over here? Because they biofunctionalize our plasmonic dielectric interface. So with each different 2D nanomaterials and the optimized thickness of gold as before, and 7 nanometer of indium phosphide in the case of gold, we see that in the case of fluorinated graphene, so FG stands for fluorinated graphene, black phosphorus, and molybdenum disulfide. So among the three, fluorinated graphene gave us the best figure of merit, as well as the sensitivity was almost like comparable. So similar cases are observed in the case of silver as well as in aluminum. In the case of silver also, you see that figure of merit is very high as well as sensitivity. And again in the case of aluminum. So among the three, if we compare the gold, silver and aluminum in the vicinity of different 2D nanomaterials, you can see that fluorinated graphene is coming out to be the best one. And among all of the three, the silver indium phosphide fluorinated graphene, if you compare indium phosphide with silver in the different 2D nanomaterials, you can see that fluorinated graphene is giving us the best one. So now we compared our results with the previously reported works, and we saw that if we are, right now we inculcated indium phosphide. So like people have done before, they have taken dielectric as silicon. Silicon is one of the famous dielectrics considered so far. And then people have even worked on BATIO3, BFO, that is BEFIO3. So people have worked on so far in the visible region, or they have taken different dielectrics in comparison to indium phosphide. You can say that we have produced a much better figure of merit as well as an appreciable 3-digit sensitivity. So concluding my presentation, we can say that we tried to analyze and numerically simulate a highly sensitive gold, silver, and aluminum-based dielectric with indium phosphide and different 2D nanomaterials in the NIR region. We demonstrated a better configuration for silver, indium phosphide, and fluorinated graphene, and we proposed with a monolayer as of fluorinated graphene can be a powerful tool for enhancing the biosensing activity. So that is all from our side. So, any questions?
Yes, so thank you, Sambhavi. Yeah, really a nice talk. The floor is open for questions. Is there any? Okay, so I'll have a few very basic questions on behalf of the audience. So first of all, yeah, really nice work. So I can see there is, can you go back to your 17th slide? Slide number 17. Yes, so the figure of merit in that gold one is quite high compared to the other one. And you are well beyond. So the thing is this theoretical work or practically, experimentally demonstrated?
Sir, these are my, like right now, as of now, these are simulated results, and the work that I have compared with, these reports are also the simulated ones. So,
okay. So one more thing, then fluorinated graphene you are talking about. So the thickness you are talking about around 8 nanometer, I can see, in that similar range. The thickness of the fluorinated graphene.
It's 0.34 nanometers, sir, mono layer of fluorinated graphene.
Nanometer. So, so how are you proposing graphene fluorination uniformity and also the indium phosphide layer? I think 8 nanometer.
How am I proposing, sir? Can you come again? How am I proposing?
The indium phosphide layer is around 8 nanometer. You are proposing. Is
yes,
it correct? For this merit?
Sir, sir, we proposed indium phosphide 8 nanometer according to the trade-offs between the performance parameters.
Around 8 nanometer. So roughly, okay. What is the area over which your indium phosphide will be has to be coated uniformly?
What is the area?
Yes, well, because that this is, I guess, is you are coating on a prism.
Yes, sir.
So do you have a rough idea what is?
I think 100 micrometers, maybe roughly.
So, what kind of a tool you think should be useful for this kind of a practical?
What kind of fabrication technique are you asking?
No, fabrication, not fabrication. I'm coating tool, thinking coating tool, which can provide you 8 nanometer of uniform layer. Nanometer is very small.
Yes, sir. But like, what kind of tool you are asking?
Yes, what kind of tool can give you an 8 nanometer thin layer with a uniformity over 100 micron?
Okay, sir, I don't have any knowledge regarding this, so I'll have to see.
Okay, not an issue. And yeah, so you were saying that your figure of merit is coming due to the WHM being in the denominator.
Yes, sir.
Yes, so you are working with a very data figure of merit will be directly relating to a lower bandwidth.
Very narrow line width of the resonant curves.
Yes, so the chromatic aberrations, how will it going to affect the material then? Because the surface roughness and all will be coming into effect in the. So how?
Sir, so sir, I would like to say here that like this is basically right now, as of now, this is a very preliminary stage. It's an ideal model, I will say, ideal configuration. I haven't in my code, we haven't like right now we haven't added any real time scenario, like when temperature comes, when surface roughness comes into picture, and other environmental factors that come into the picture. So at this point of time, I am trying to convey to my research fraternity that such kind of design is also feasible. That considering silver and with indium phosphide in the NIR region.
I do apologize because from my perspective as an experimental scientist, I do come with this kind of questions. So it's all right. So definitely this looks very promising. So with this, so I'll thank you. If there are no more questions, so I'll thank you from the on behalf of organizers for attending the talks, and their conference is still going on, so you can attend the other sessions too. Online links are, I guess, available to all the participants. Yeah, so thank you, and so we'll end over here this session. So I thank from on behalf of the organizer, everyone who attended this talk, invited and contributed, and the participants. Okay, so thank you all.
We have 10 minutes, followed by 5 minutes.
From SRM University, AP Amaravati. And now I'm going to talk about machine learning based low scale dipole antenna optimization. So in the following research project, basically we worked upon utilizing the machine learning techniques in order to optimize the parameters of the dipole antenna. For example, we have some of the important parameters such as field length, dipole radius, and so on. But as this is a preliminary study, we only selected a few of the parameters, and with the help of machine learning, we are trying to find the optimal parameters. And here, if we observe some of the previous papers which actually illustrated the processes and all. So first, we have the implementation of machine learning in order to identify what's going to be the trend with respect to each and every stage during the antenna modeling. And next, we have the second paper, which was actually presented during the year 2021. Which talks about implementation of machine learning in order to optimize the parameters of antenna array. And the third paper basically talks about printed patch, so on. We have many other examples talking about the implementation of machine learning. And however, if we see the paper which is presented by Reddy et al. In the year 2021, it basically talks about accelerated antenna design with the help of automation and the implementation of machine learning algorithms. And by taking the following papers as reference, we actually came up with aggregation of multiple machine learning algorithms. For example, let us take 3 or 4 different models which are actually running in parallel. They actually work upon the same set of data, but still they give the result in such a way that it is actually the aggregated version of the decisions taken by individual models. So now let us look at the methodology and how we proceed in a step-by-step manner. So the first step actually involves the data collection. So for the following study, the data was actually acquired through simulation through CST Studio, which is actually taken by the help of iteration or some other kind of thing. So initially we will be doing the parametric tree, after which we will be taking the Excel kind of file. So here is a simulation of the dipole antenna model in the CST Studio, and the later part comes when we are actually trying to talk about what's going to be the parameter which is the quality of the antenna. So for this, we are actually taking the parameters of S11, directivity, efficiency. So these parameters will actually tell what's going to be the performance of the antenna. So reflection coefficient is nothing but is the amount of energy being radiated backward from the transmitter side to the receiver, and this actually causes some of the fluctuations because we have energy coming back, and this is not efficient. So the reflection coefficient should be as low as possible. Directivity talks about the range to which particular wave is actually traveling. And next, we have the efficiency, which talks about the input power and also the percentage within that. So after acquiring the data, the later process involves working on different algorithms. So we have linear regression, support vector regression, and decision tree, which are actually utilized. Apart from the 3 algorithms which are actually used, we have a 4th algorithm, which is nothing but the combination of all the 3 algorithms. So here the same data is actually provided to all the algorithms so that there is actually uniformity between the decisions taken. And each model is actually concatenated at the last in order to verify the accuracy. So how is accuracy going to change? So when I use decision tree, support vector regression, and linear regression, as a standalone technique, I would be getting an accuracy, let us say, A. And now, if I actually concatenate them and create a bootstrap algorithm, then I might get an accuracy B. So, is the accuracy B better than A is something which we are looking at. So, going into detail, as I said, first we will be having the data in this particular format. So, this actually contains feed length, dipole radius, dipole length, the operating frequency. S11 is nothing but the reflection coefficient, directivity, and efficiency. So here the first three parameters are actually the dimensions. And now as we are moving towards an optimization paradigm, we will be having the outputs as the inputs, right? Because depending upon the user specifications, we need to change the dimensions. So efficiency, directivity, S11 and output frequency are going to be the inputs. Feed length, dipole radius, and dipole length are going to be the outputs in this particular problem statement. And we will be mapping all the inputs with the output parameters. So if we observe here, the last three parameters are actually selected from the data such that they are the best possible situations. So the best possible situations here are actually taken as S11 directivity and efficiency. So suppose if we generate the data further, and if there is an instance where we have better efficiency, better S11 and better directivity, then they will be replaced with these values. Corresponding to that, we will be having the operating frequency from the user side. So this actually changes according to the user specifications and etc. So going into a detailed procedure, we will be having all the four parameters as the input, as I said, and the fourth parameter is actually going to be the user input. We will be creating three different models. So it could be like all the three could be decision tree, all the three could be SVM, and next we have the linear regression. But the fourth model is actually going to be aggregation of them. So each model actually maps all the four parameters to the three individual outputs which we are actually trying to find. So this is the entire model in brief. So this bootstrap aggregation is a combination of all these three, and after that we will be getting the optimal value depending upon each and every mapping that we are going to generate. And the final decision would be the average of the individual decisions provided by linear regression, support vector regression, and decision tree in case of bootstrap aggregation model. So here are some of the scores which actually validate the particular model. For example, the R squared score, which basically talks about the best fit line, then we can tell that the value of bootstrap aggregation is closer to 1, which is actually identified to be good in case of regression analysis. And when we talk about the residuals or the root mean square error, then we can identify that the bootstrap aggregation also has least amount of residual value in comparison to the linear regression or some other techniques. So the basic idea is to identify how the trends are actually varying with respect to the standalone technique and in combination of all these three. So in the future, other authors can also work upon identifying what other parameters could be considered in order to increase the accuracy. And on the other hand, we can also see how the trends are actually varying with respect to some other parameters coming to the semiconductor devices, like the concentration of holes and electrons. And still algorithms, the number of algorithms can be increased so that we can actually improve the accuracy further. So with this, I thank you all for giving me the opportunity, and I would be happy to have your discussion.
Thank you, Paul, for a wonderful presentation. So, are there any questions? Audience.
So parameters is the last difference. So for the simulation, we have the dipole radius. For feeding length, for now we are actually going for 0.5 centimeters. For here we actually the one which actually is the cylinder in the conductor is ideal one. We just did that
So these three are three different. This bootstrap radiation is nothing but it combines all these three techniques. It's the average and it's the so sir, dipole is actually about customizing compared to batch and here is section after if we actually decreasing the complexity because of super analysis, because as Adler we should also take care about how the parameters are actually changing. So, sir.
See all the pictures. I'm saying the model 1 predicts the field length, model 2 predicts the dipole length, model 3 predicts the dipole radius. Why not change the order? But what you have anything specific like why you are actually feeding the field length with respect to maybe support vector or like the dipole length with respect to how like change from one thing to other thing? Does that matter?
Yes, sir. That can actually increase the accuracy to identify which particular algorithm is trying to find.
Yeah. So then how can you generalize that? Like, how can you generalize your result stating that the dipole antenna, you are claiming that you are optimizing the low scale dipole antenna, right? So how it will be done?
Sir, so one problem we might be having, sir, though accuracy if we actually try for every direction, see the effect in every direction, and of course the accuracy will be there, but this is time consuming, sir, and also if the data volume is increasing, then it might take days to come up with the decision. So what we can do is that instead of that, we can keep all the algorithms in the same set. So even some of the algorithms are their own disadvantages, other algorithms can supplement. So we can use them in parallel and try to identify them.
Are you facing any problem with the concatenation now? Like you are combining three different algorithms, right? Are you facing?
Yes, of course, because some algorithms actually have some of the things, like I said, the accuracy linear regression is not performing in some of the cases. So that time of course.
Any other questions? If not, thank you very much.
So, good morning. I'm Vijay Prabhashan, I'm faculty at SRM University. So, my team of students presenting this paper. So, we have Pranav here in person. And the title of the paper is Real-Time Risk Force Data Acquisition from a collaborative robot for cutting and recognition of the vegetable type using some heuristic techniques. So the authors are Pranav, who is with me, and Janvi Jasti, who is a mechanical engineering student, and Sai Santosh is also a mechanical engineering student, and Askar is an electronics student. So it's a good interdisciplinary team of students. So mechanical engineers, the authors take care of programming, and electronics engineering authors take care of interfacing and data acquisition. So this is the robot we have in the lab. It's a class of robot called collaborative robot. So it is an industrial robot, but optimized for collaborating with human. Usually industrial robots work high speed and they carry very heavy loads So for the purpose of safety, they are usually kept in an enclosure, usually where human operators are not allowed doing operation. Whereas in this case, this is one of the fast selling robots in the world. This class of robots are called collaborative robots, where the human operators may share the workspace during the operation. So that means the robot should have a little bit more intelligence, but you cannot call it fully intelligent. The intelligence comes from additional sensors. So these robots comes with inbuilt BIST force sensor, which will do 6-component force sensor. So because of that, any obstacle can be easily identified even without a camera. So that is one advantage. The other one is overload detection for voltage and current. So these two provide limited intelligence and then make it possible for human operators to share the workspace with the robot. In fact, Bajaj in Pune has installed 100 of these robots, and Eye Hospital in Madurai, they are using it for assembly of contact lenses, assembly of contact lenses. And ITC here is also planning to purchase these robots. These are all lightweight operations where human and robot interaction happen. So that is about this robot. I will briefly give the problem statement of this paper and technical specifications, then literature methodology, and then how we design simple attachments to make this work possible. So in fact, recently we presented first phase of this project. We developed a digital twin for that. We presented it in another conference last month. So I already discussed about collaborative robot. The one we are using is called manufactured by Universal Robots Denmark. It is model UR5E. It can carry 5 kilograms of payload at the specified maximum acceleration and velocity. It has a wrist force sensor inbuilt. So this is the typical one. We thought if this robot has a force sensor, can we use it for the cutting of vegetables? Okay. So this we have applications in agriculture and industry, but we also want to gain some experience using these experiments and then finally apply it for robotic surgery. So the technical specifications, I told you, 5 kilogram payload at maximum accelerations. It has got very good force and torque sensor accuracy. It can rotate almost 360 degrees, and at the speed of 180 degrees per second, which half a rotation is possible in just a second. So repeatability is 30 microns. Usually industrial robots may have repeatability up to 10 microns. CNC machines may go up to 0.5 micron. This robot is optimized more for sharing the workspace with human operators and even force sharing with the human operators. So the repeatability is relatively designed to be less, but then collaboration is important. It has got a sensor, the robot sensors can be read, and the robot can also be controlled from custom built software at the sampling rate of 500 hertz. So this is what we are also trying to use, and otherwise programming can be done on the machine. Usually it's called online programming, but now the concept of online offline are changed. So I use the term on machine. Otherwise the literature is used online until 2 years ago, and it can also be done offline programming or offline coding is off machine coding is possible using a separate software not connected to the robot. After the code is tested and simulated, and the program can be transferred to the robot. So these are the interface. And in addition, using the data transfer, we will be able to control the robot using custom-made software or even specialized packages like MATLAB. So the main thing is, we have done solid modeling and 3D printed tool holder for experimentation with experimentation specifically for vegetable cutting. And then using the data transfer feature, we'll be able to measure the cutting force at 500 Hertz. And then, it is demonstrated for cutting a couple of vegetables. So these authors, they've designed a vegetable cutter and slicer for automatic operation. And then Sharma et al. They have demonstrated latent embedding states for online slicing task planning. Then, Jamdagni, Iowa State University. So they have actually, I think the photograph earlier that was taken from this paper. So they have characterized the cutting forces for different types of vegetables and different type of cutting operations. So there are several authors who have already published work in this area. So this is a typical operation of this robot, though not related to the project, related to the paper. So, but what you see here, these two pictures are actually Polyscope. Polyscope is the trade name of the company. It is basically, it is called teach pendant in robotics literature. It's basically from the robot controller. This acts like a keyboard as well as display device. So it's a touch sensitive smart screen. So this is where we can insert the robot code here using on-machine programming. But on-machine programming, you cannot write too many lines, so it's useful for actually testing of you are sure that the code is okay. And so this uses a gripper, and this gripper is from the company On Robot. So this can hold a variety of shapes and sizes, but still we found that to cut the vegetable we need to hold the knife, and so it was slipping. So we had to design. I'll come back to this later. We had to design a holder. So we 3D printed a simple holder. So that prevents tilting of the knife when cutting happens. So the knife is inserted in the holder, and the holder is handled by the two-fingered gripper. And this is how the experiments are conducted. And these are initial experiments, so it's primarily held because we just want to characterize the data acquisition. So later on, even holding process may have to be automated. So, coming back to this, how the sensor data acquisition happens and how the sensor measures. So the wrist force sensor can measure 6-component force sensor. This is actually located at the wrist, whereas the actual task is happening somewhere on the tool. Okay, the tool tip, if you are injecting acceleration, maybe tool tip. If you are cutting, so it may be somewhere on a single point of a knife or on a larger area of the knife. So, let's say this is where the sensor is located. Sensor is located at the wrist. So wrist has its own coordinate frame. Sensor has its own coordinate frame. And let's say this is the tool. In this case, it's a knife. And we have to register TCP for the knife, tool coordinate point or tool center point or tool coordinate. So XT, YT, ZT are the tool coordinate frame, and XY
ZW or the sensor coordinate frame. So the sensor measures Fx, Fy, Fz in its own coordinate frame, but the robot software can send us the data either in the base coordinate frame or in the specific tool coordinate frame. That way, we don't have to bother much about the coordinate frame. Otherwise, the theory is there is something called force transformation matrix that you see here. Charger is like this. Force transformation matrix. So it's a 6 by 6 unique matrix. So unique this sensor measurement and tool and the force data, the tool can be uniquely identified. So you see here the data provided either on the polyscope itself or through our own program we get this data. This is the force data. So there are the first three elements are Fx, Fy, Fz, force vector components, and next three are torque vector components, moment vector components. So these 6 data is available. So very often we are measuring either in 0 frame theoretically or wrist frame theoretically, then we may have to convert. But luckily, this robot provides data directly on the tool frame. So I already discussed about the experiment, and I leave the floor for now to discuss more on how the data is acquired and how they have.
Basically, what this data needs to be collected for now and put into a data sheet for calculation. So first for data collection, we've first written a code where we use RTT protocol that was defined by them, and collected the data using the Python code that was written. But still, the code is not present. But basically, the data has been collected in the 3 frames, and the magnitude has been collected and converted into the 2 coordinate frame before graphing it using macro. So as you can see here, first now, this is the span of data, but this is when cutting a capsicum. You can see that at the beginning there is a peak because there is the capsicum skin before we cut, and then slowly the force decreases because as you can imagine a capsicum. At the beginning there is the skin that takes the highest force to cut through. Then there is the inner flesh, which is mostly hollow. So as you can see, there is a sudden drop here. That is the capsicum. Ignoring extra jitter here, this is the actual data collected when cutting through a tomato. So as you can see that here, when cutting the tomato, there is not much of much force collected except for the peak that is collected when cutting through the skin, because inside most of it is just the flesh of it, so it sharply drops through the graphs. So
peak value is 50 newtons per tomato and 100 plus 140.
Here, as you can see, it is like 60 for a capsicum, and then a bit lesser, around 50 for a tomato.
And the peak is experimental defect because the knife hit the table, because we cut it very quickly. So that was not that was done by manual programming.
So our work here is basically converting whatever forces or torques each of the motors assigns, and then getting those forces and converting it into two coordinates, so that each our values correspond to what the sensor actually feels if there is a force sensor at the end of the tooltip, basically. So moving up, these are the references that we use. So thank you. I'm open to any questions.
Yeah, specific advantage is we can collect data very fast. Data.
So this allows, we can prevent the knife from hitting further. So the robot can identify obstacle by itself. So maybe it can come fast the moment it touches an object like vegetable. So it can go at a programmed speed. So that is possible because of force sensor available. So even without vision, we will be able to. We are also working on vision to identify the orientation. For example, if we have to cut, say, carrot, then we need to know the orientation. So, and if we need to cut lady's finger, we need to know what is it and take. So there is another team of students working on vision part of it. Then we have to interface the camera to the feature scope. So eventually we will have a sensor fusion of force data as well as vision data for a more intelligent handling. Can you talk louder? And control the robot using IR sensors. IR sensor are very low technology. So right now you can other than the internal software, we have written external software that can communicate with the robot using Python. So you can communicate the IR sensor with the Python code. You can obviously connect anything that. The robot controller has a provision for interfacing, I think, 24 inputs and 24 outputs. So out of I think 14 plus 4. So 7 digital inputs, 7 analog, and 7 digital inputs, 7 analog inputs, 7 digital outputs, 7 analog outputs. So this provision is available in the controller. So if you are talking about IR sensor used for high projects, so actually there is a protocol you have to convert it to a 24 volts voltage and then otherwise the voltage you get from hobby IR sensor is very low. So that is one thing. If you are talking about IR technology in general, there's something called LiDAR which is used for driverless car. That is also a infrared laser. So infrared is a very loose term. So you can use it, you can interface. So the point is you can directly interface the sensors to the robot controller itself, and that status will be available on your custom program. Or you have your custom program running on your laptop, and you can connect as many of the sensors to your laptop. For example, camera I cannot connect to the robot controller. It has to be connected to the laptop. And then computer vision algorithm should process it, and then concise commands only should be given to the controller. So infrared can be used that way, but very loose definition. Yeah, thank you. Welcome.
Yeah, very interesting work. Like talk about capsicum, right? When you try to cut the capsicum, first part is like really hard. So that's why you are getting the force, and then there will be a follow up between. At the end of it, it will be really hard, right? And again, the peak.
As you can see, like once the peak is hit, you can see the skin. Like once the skin is broken, there will be the pulp will slowly spread out. So that is why there is slow rate reduction in the amount of forces.
And again, you are cutting the another layer, right? Another layer, then follow last layer. So when it cuts,
we only right at the end, we will still get again a peak because we will still be getting the peak. But then I do not feel we will get as much peak as the first one because once the skin is already pierced, we will not
have so much force.
Like, we tested that before, but then the graph was not as clear. So it's a long way to go.
Yes, as you said, start working with the camera and this. So I think
even in the force acquisition itself, the paper is only real-time data acquisition, but we are able to acquire data, but we will not analyze the data. So, when we analyze data, then whether you are cutting on the surface, whether you are cutting on the core, and then to what depth you have to go. So those characterization has to be done. So that's one way to go.
Very interesting.
These are very first few results.
Very interesting work. Thank you. Today we have a keynote speaker that are presenting Rangoli, IIT Kharagpur. So before going to start, let me introduce P. Gangoli. So P. Gangoli graduated from Scottish Church College, Kolkata University with physics honors in 1990 and received MSc Technology in Optics and Optoelectronics from Department of Applied Physics, Kolkata University in 1993. After that, he worked on Fourier Optics, same department as a research fellow for a couple of months, and in June 1994, he joined the Indian Institute of Technology, Kharagpur, as a mission engineer and initiated research on integrated optics. He earned his PhD in 2000 from Department of Electronics and Electrical Communications Engineering, IIT Kharagpur. Currently, is working as a senior scientist officer in Advanced Technology Development Center of the Institute, where he has leading the Microphotonics Research Group. Apart from integrated optics, his current research interest includes fiber optics, optical metrology, MEMS, MOMS, and micro-nanophotonics. Dr. Gangoli has published around 100 plus research papers in journals and conferences, co-authored one book on photonic waveguides, components on silicon substrate, modeling and experiments, and has 2 operated software and 1 patent in field of guided wave optics. He is Life Fellow of Optical Society of India and was a Royal Society visiting scientist in Optoelectronics Research Center, University of London, UK in 2008 to 2009. So with this brief introduction, I welcome you, sir. Please, sir, please hand over to this. Thank you.
Morning, everybody. I think I am audible.
Yeah. Please go ahead.
Okay. So greetings from IIT Kharagpur. I am Pranavendu Ganguly, speaking from Advanced Technology Development Center of the Institute. Before I start my presentation, let me tell a few words about our center. In ATDC, or Advanced Technology Development Center, we are working on 5 interdisciplinary areas. First, the sensors, actuators, and devices, then technologies for IoT and IoE, then drives and automated systems, then human-machine interaction, and integrated photonics and quantum computing, the group which I belong. So as you understand, we do optics, that is optical waveguide-based devices, both theory as well as experiments. Now for today's talk, the title is Characterization Methods of Integrated Optic Waveguides. So here I will discuss different fabrication techniques of optical waveguides, then 3 characterization methods. First, the loss measurement. Second, the spectral analysis of the waveguide. And third, the simultaneous determination of mode index and absolute refractive index profile from measured near field intensity distribution of single mode waveguides. Different kinds of waveguides we have taken into account. All are channel waveguides, budded, strip, rib, or diffused. According to mode structure, we basically use single mode waveguides because for device application, single mode waveguide is mostly needed. Then according to refractive index distribution, we use step index and graded index, both for different applications. And according to material, we are using semiconductor, silicon waveguide, polymer, SU 8 waveguide, and of course, lithium niobate waveguide. Since lithium niobate is very attractive, it has very attractive material properties. So let me give a little bit of material properties of lithium niobate in brief. It's a ferroelectric negative uniaxial crystal. Curie temperature is quite high, 1144 degrees Celsius. Then congruent lithium niobate we are using. That means lithium and niobium concentration ratio is of the order of 0.94. And the transmission window of this crystal is approximately from 350 nanometer to 5 micron, except an appreciable dip around 2870 nanometer for the presence of OH hydroxyl group of the crystal. The crystal is highly electro-optic, nonlinear optic, and acousto-optic in nature, so it can be used for different device applications, optical devices, of course. The most stable waveguide in lithium niobate is titanium indifused lithium niobate waveguide. Here, titanium metal is diffused within the crystal to increase both ordinary and extraordinary refractive indices. I have told in the previous slide that this is a negative uniaxial crystal. So both ordinary and extraordinary refractive index of the crystal will increase, and it can guide light by total internal reflection. The fabrication steps, most of the fabrication steps are crystal cleaning, deposition of titanium film, then fabrication of titanium strip lines by photolithography, high temperature diffusion of titanium into the crystal, and finally edge polishing. All these fabrication steps are different technological process steps are to be followed for each of them. Lithium niobate handling is, or the processing is not that easy as that of silicon, so you have to take care of that. Titanium film deposition we are doing on this ultra high vacuum electron beam evaporation system. So the specialty of the system is that it can go up to 10 to the power -9 millibar. Okay, so typical deposition pressure is 10 to the power -7 millibar. It contains three kinds of pump. One is Vaxog pump or cryo pump, which we can operate with liquid nitrogen, then ion pump and titanium sublimation pump. You just note down that this contains no oil pump, rotary pump or diffusion pump. So why these are not used? Because for rotary pumps or oil pumps, different kinds of oil pumps, a little bit of oil vapor in contamination can occur, and we can avoid that contamination for this particular film thickness. Okay, so film thickness, what we are using is from 800 to 950 angstrom for waveguiding application, and deposition rate we are maintaining 2 angstrom per second. So it contains all the control parameters. That means you can measure in situ the crystal thickness or whatever thickness of titanium is going to be diffused by using a quartz crystal, and thermocouple is also there. You can heat the substrate during titanium film deposition. So the next step is the photolithography. So for mask fabrication, we use our in-house direct laser lighting system, and we are using positive photoresist S1813 from Shipley. So this photoresist is quite sensitive, and we can go up to 1 micrometer feature size by using this particular photoresist. Titanium etchant, we use TFTN as our titanium etchant from Transient company, where the etch rate what we have got is approximately 10 angstrom per second at 70 degrees Celsius. So then after titanium photolithography, we have to diffuse that titanium strip line within the crystal. So for that, we are using an open tube diffusion furnace. So for furnace temperature, we are using it's nearly 150 degrees Celsius. So I will discuss that a little bit afterwards. So during the diffusion process, oxygen gas is flowing through the crystal, and it flows through a bubbler heated at some temperature, and this critical humid condition inside the crystal is very much needed to suppress lithium out diffusion from the crystal, as well as low surface roughness of the waveguide. So this is the furnace temperature versus length of the furnace tube. So we can see that flat zone temperature used is 1048 plus minus 3 degrees Celsius. So lithium niobate is very brittle. It cannot withstand a sudden temperature change. So we use a ramp up rate of the order of 5 degrees Celsius per minute and ramp down rate of the order of 10 degrees Celsius per minute. The oxygen gas flow rate is 0.5 liter per minute and bubbler temperature is optimized at 60 degrees Celsius so that we can have a good quality waveguide, titanium infused lithium niobate waveguide. Now the diffusion coefficient for Z direction of the waveguide, that means the crystal axis, the Z direction of the waveguide is 0.7884 micrometers per square hour. And for lateral direction along X, it is 0.612 micrometers square per hour. This we have measured in our laboratory. Now the final stage is edge polishing. This is very important. There are instances where people can fabricate good quality waveguide, but fail to couple light into it because of bad edges. So here, before polishing, the crystal cutter with diamond wheel is used to dicing the edges of the waveguide, and then it is polished by using different polishing sheets embedded with different alumina particle size, 15 micron, 9 micron, 6 micron, 1 micron, etc., for different intervals of time. So these are the fabricated waveguides, photomicrograph from microscope, what we are having at our lab. This is the polished waveguide edge. You see how polished it is. This is the waveguide, titanium infused lithium niobate waveguide of with 6.5 micron. And this is, compare this with this, where we have used just unpolished substrate edge. Okay, you cannot, if you have a waveguide over there, you cannot couple light into it because the light scatters out. So this is the top view of the waveguide, and this is the near field intensity distribution at the end of the waveguide. The wavelength used is 1.55 micrometer. Now the second process to fabricate waveguides in lithium niobate, what we have used is annealed proton exchange waveguide. Here, partial replacement of lithium ion with hydrogen ion increases the refractive index of the crystal. This can be done by putting the crystal in benzoic acid melt, where titanium is used as a masking layer in this case, and proton exchange temperature and time were 210 degrees Celsius and 5 hours for our experimental purpose. And finally, after proton exchange, we remove the titanium mask and the crystal is annealed for 2 hours at 320 degrees Celsius. Now, since only extraordinary refractive index increases by this annealed proton exchange, APE waveguide, then this waveguide can be used as a polarizer. So by the process, whatever process I have just narrated here, only extraordinary refractive index will increase. Now, only proton exchange, before annealing, only proton exchange reduces the electro-optic property of the waveguide. So to retrieve electro-optic property, one has to use annealing. Now annealing process is, I have just told, it is 2 hours for 320 degrees Celsius. And this process, this proton exchange process, can also be used for surface micromachining of lithium niobate, where you can make different kinds of MEMS or MOEM structures. The third process, what we have used is direct UV-written waveguides in lithium niobate. This is a maskless process where continuous wave laser light is used to write the waveguides. This particular process of writing the waveguide was discovered in University of Southampton, UK, in Optoelectronic Research Center. So I am lucky to be there at that time and use this particular waveguide for different characterization purposes. Here, the laser light used are 244, 275, 300, 302, and 305 nanometer, and the substrate used is plus Z congruent crystal. Then laser light, since this laser light is slightly lower than the transmission window of the crystal, so this laser light gets absorbed and the local temperature increases. So as the local temperature increases, so lithium out diffusion or side diffusion takes place. Both can take place. Out diffusion as well as side diffusion, which increases Again, the extraordinary refractive index. Thus, the graded index waveguides can be fabricated by this maskless process. And here you see one of the experimental result of the near field intensity distribution of the output of a direct UV written waveguide, where the writing wavelength is 275 nanometer, power 45 milliwatt, spot diameter 3 micron, scan speed 1 millimeter per second, and the output or the laser light what we use to characterize the waveguide is 0.63 to 8 micron. It's in visible wavelength, and the polarization is of course the TM polarization, since we are using Z transistor. Other than lithium niobate, we have also gained some experience with polymer waveguides. SU8 is used as a polymer. So it's a negative tone photoresist. It's the main process or main features of polymer waveguides is that it is low cost process, relatively high refractive index contrast you can achieve. That means what? In titanium doped lithium niobate or any other lithium niobate waveguides, what we have discussed today, there the refractive index contrast is 0.01, say. So the substrate or superstrate and the core region, the refractive index difference between them is of the order of 0.01. But for polymer waveguides, for SU8 waveguide, the refractive index contrast will be a little bit larger. It can be fabricated on oxidized silicon or on glass. Now, due to low refractive index, SU8 refractive index is of the order of 1.57 at 1.55 micron wavelength of light, whereas the lithium niobate or silicon refractive index is quite high. So since the low refractive index, faster distribution of optical signals at different nodes of the chip is possible. So that is one very important observation for of the waveguide, which can be harnessed for optical interconnect applications. Fabrication of SU8 waveguides, standard photolithography process we have followed. I have just told that in most of the cases, oxidized silicon is used for our substrate. In some of the waveguides, PECVD grown thicker oxide layer, 3 micron oxide layer is used for low propagation loss. You can write this waveguide on SU8 coated sample by using a 375 nanometer wavelength of light, or you can use a mask pattern for fabrication to write the SU8 waveguide structure. These are the fabricated waveguides. Here for SU8, since it's very soft material, so we prefer to clip silicon to get the end facets. So this is the clipped end facets of the SU8 waveguide. This part is the SU8 waveguide of width 3 micron. And the height of the waveguide is, you can see here, it's a tilted photomicro one. Here, the height of the waveguide is of the order of 1.65 micron. So after coupling light, 1.55 micron, we are seeing this. This is a single mode waveguide output. Okay. So this is a single mode waveguide output. If you misalign slightly, then the diffraction pattern will come, and you will see that some loss will occur because of this diffraction of light. Now, the silicon waveguide, it's mostly used for high refractive index contrast. Why high refractive index contrast? If the refractive index contrast is high, in that case, you can use tight bending of the silicon, so you can fabricate micro ring resonators and all those cases. So the footprint of the device will come down. And another advantage is that electronic photonic integration can be performed, and these silicon waveguides are transparent at fiber optic communication window that is at 1.55 micrometer. Fabrication of silicon waveguide, silicon reeve waveguide we have done because for silicon wire waveguide we have to use electron beam lithography system, which we have not used. Here, only optical lithography we have performed, and by dry etching process, reactive ion etching process, we can fabricate the deep waveguide. So our RIE process, reactive ion etching process parameters are pressure 100 millitorr, then flow rate SF6, 5, and oxygen 1. So we are using fluorine chemistry, sulfur hexafluoride as our agent. Then power is 50 watt and time 85 minutes. So you can see at 85 minutes, the etch depth is of the order of 1.8, 1.9 micrometer. So these are some of the photos of silicon rib waveguides what we have fabricated. This is the near field pattern, and this is the design data what we have tried to fabricate, and this is the fabricated data what we have achieved. Now the characterization process. Now first characterization process should be the propagation loss and fiber waveguide coupling loss measurement. For that, initially we tried with cutback method. Okay, we call it modified cutback method. And why we call it modified, that I will tell later. So this is the experimental setup what we are using. We have to measure the fiber output and we have to measure the waveguide output using a chopper detector locking amplifier arrangement so that we can increase the signal to noise ratio even for low intensity of the light. So if we measure P in and P out, then the total insertion loss of the waveguide of that chip is of the order of -10 log 10 P0 by Pi. So if we use different lengths of the waveguide and total insertion loss is measured in this way, so we can plot that in total loss versus waveguide length, and you can fit it with a straight line where M will give us the propagation loss. So that means it is of the order of dB per centimeter or dB per millimeter, and C, the fit equation, straight line equation, the C will give us the coupling loss, fiber waveguide coupling loss. So we measured the titanium diffused lithium niobate waveguide losses, and we see that the loss parameter is around 0.3 dB per centimeter, and coupling loss is 4.11 dB per centimeter, a little bit on the higher side, coupling loss, because of several reasons, because your fiber mode dia and the waveguide mode dia to be matched, it was not matched properly. So, and these measurements were performed at 1.55 micron wavelength of light. Now, in a sense, this particular method is very useful. If you have multi-mode waveguide, if you have single mode waveguide, if you have reach, wear, or any type of waveguide, you can use this method. But the main disadvantage of this method is that it is destructive in nature. Destructive in the sense you have to use a number of waveguides of different lengths, or you can fabricate a waveguide and cut into several pieces to get this type of graph. So people are not that much interested in modified cutback method. They are using the Fabry-Perot cavity method, where there are two approaches are used. At the input, they are using either a tunable high-cost tunable laser source, DFB laser source, for example, and a standard photodetector at the end, or a very costly optical spectrum analyzer, OSA, of resolution less than 0.02 nanometer at the output, with the input with any laser source or broadband laser source. So in both cases, this measurement of the cavity or measurement of the waveguide loss and fiber waveguide coupling loss is very costly. That means you have to use very costly instrument for measurement in one shot by using the Fabry-Perot cavity of the two sides of the waveguide. So in our method, what we call the spectral analysis, here we have used a low-cost broadband light source, AAC source, for example, and a low-resolution monochromator. So the cost of the measurement equipments are very low compared to these two, and we can measure accurately, as accurate as that of these two processes, the propagation loss and fiber waveguide coupling loss. So this is our experimental setup. And you can see that the monochromator is placed here and chopper, then this is polarizer. Glenn Thompson prism is used in this polarization experiment at 1.55 micrometer. And this is the objective. So we have to measure the fiber output for different wavelength of the light available with the laser source. And so we have to have a calibration graph. So initially this waveguide under test was not there within the setup. We measure the fiber output through rest of the things. And we will take that value as our calibration trace. And then we place this waveguide under test within the setup, and waveguide output is measured. So this is the experimental experiment. This is the near field pattern of the titanium doped lithium niobate waveguide. This is the fiber output, which is our calibration graph. And this is the waveguide output. Now, if you take a ratio of that waveguide output by fiber output throughout the length or throughout the wavelengths, what is available within your laser source, you can get an interference pattern like that. So FSR, or free spectral range of this interference pattern, is 26 nanometer, which corresponds to a cavity length of 46.61 micron. So 46.61 micron is actually the cavity between the fiber output and waveguide input. So you can get we can calculate the coupling loss because we know the contrast. So coupling loss we can calculate, and it came around 2.18 dB. Also, since the total insertion loss is known for a particular wavelength, so we can also calculate the propagation loss if we know the total length of the waveguide. So this is an alternative method. Here we have used only monochromator and a broadband laser source, instead of using either a very high-fi DFB laser or an optical spectrum analyzer of high resolution. Next is our white light spectral analysis. White light spectral analysis, a white light source is coupled within the waveguide and the output is coupled to the optical spectrum analyzer, or even you can use a monochromator in this case. So white light source, we have used a phenium supercontinuum laser source, fiber laser from 408 to 1800 nanometer, or a quartz tungsten halogen lamp 600 to 1850 nanometer, depending on your need, where actually you want to measure or you want to perform the experiment. So initially, we have to characterize this laser source. We have to remove this waveguide under test from the setup, and the spectra can be saved in the optical spectrum analyzer. And then waveguide under test is inserted within the setup. And again, we measure the spectrum analysis or spectral data. And if we take the ratio of that, intensity waveguide divided by intensity reference, we are getting a graph somewhat like this. So in region 1, the waveguide supports 2 lowest order modes. Okay. In region 2, the second mode is approaching cutoff. Okay. And second mode is approaching cutoff, and the first mode is propagating. In region 3, again, this is a single mode region where there is no second mode. And in region 4, the fundamental mode cutoff is approached. So by doing proper spectral analysis, you can determine whether the wavelength range where your waveguide is actually a single mode in nature, and where from it starts your second mode, and where up to what wavelength you can use that waveguide before cutoff. Now the third one is the measurement of mode index and absolute refractive index profile of the waveguide. Here, this is our experimental setup, where a helium neon source is coupled with the waveguide under test, and the output is measured. Here, helium neon laser source can be replaced by any other laser source, what you are actually interested in. So estimation of refractive index profile and mode index were done from the measured near field intensity profile of single mode waveguide by inversion of scalar wave equation. So this is the output of a titanium diffused lithium niobate waveguide, and this mode profile is at 1.55 micrometer. So this is your lateral profile, which is perfectly Gaussian, the black one, and the blue one is actually your depth profile, which is Hermite Gaussian in nature. So if we use the scalar wave equation for the fundamental mode, so your waveguide, one of the assumption is that your waveguide has to be single mode in nature. So for single mode waveguide, the fundamental, if we consider the fundamental mode only, so this is the scalar wave equation. And from that wave equation, and here A is the measured amplitude, K is 2 pi by lambda, N is the refractive index distribution, beta is propagation constant. So from this equation, we can get that refractive index change within the core of the waveguide is equal to beta square by k square minus 1 by k square del square A by A to the power half minus ns, where ns is the substrate index. So if you solve this equation, the right-hand side, all data are known mostly. And if you solve this equation, you can calculate the refractive index change within the waveguide from the intensity distribution of the waveguide at the output. Now for that, we use central finite difference formula like that, where I and j are the pixel numbers along y and z direction respectively. Now there are, it looks very straightforward, but there are some limitations. First limitation, the extraction of refractive index by this procedure is very, very sensitive to spatial frequency noise. Okay. Moreover, the Laplacian operator del square A by A amplifies that noise. So there is a big issue in noise. So we will see how it affects. And second one is that you see the right-hand side of this equation, this beta square by k square is called effective refractive index or mode index. This is an important parameter for the design of a device using a particular fabricated waveguide. So this beta square by k square, people are approximating it's similar to the substrate refractive index. So as the difference between the mode index and substrate refractive index is in general a small quantity, mode index may be approximated by the substrate index. So most of the researchers have taken beta square by k square is equal to ns. Okay, so in that case, this incorporates an error in absolute values of the refractive index changes. Okay, if you apply this equation for calculation of the refractive index change, then you have to do something with beta square by k square. So there are, before doing anything, these are the results what we have obtained without any filtering process or your approximate values of the effective refractive index. So you see the blue one is actually the measured amplitude profile and red one is the estimated refractive index profile. You see, you cannot, the refractive index distribution is fully submerged in the noise. You cannot calculate anything about the refractive index distribution. Same thing happens for depth also, but this is the depth profile, this is the lateral profile. So noise is a big issue. So the remedies what we have applied is first, a digital low-pass third-order Butterworth filter is used to smooth the measured amplitude profile, that means A, and its double derivative, del square A, without loss of accuracy. Okay, so this is the transfer function of the Butterworth filter, where omega c corresponds to 3 dB cutoff. So this takes into account the noise part. Okay, so in the second case, the other remedy is that the value of mode index was increased slowly, allowing or following an algorithm until the minimum refractive index change becomes 0. So this is our flowchart. What we are doing first, in the first step, we are applying filtering process so that the noise is, we can obstruct the noise and we can extract the actual refractive index profile. And in the second case, we start our calculation with mode index is equal to the subset refractive index value. And if we increase from that, then you will see the minimum refractive index change outside the waveguide region has to be 0. Only in that case, it is acceptable. And we have to see at which value of the subset or the mode index this is occurring. So that one is your actual effective refractive index. The computation has been done in this way. This is the measured titanium diffused lithium niobate near field pattern. Okay, A is nothing but root over of intensity if we consider the fundamental mode only. This is the first Fourier transform of that amplitude profile, and this is the filtered data. And this is again, this figure D is again the filtered A, filtered amplitude. Then we calculated D2A dx square, okay, along X. So this is the data. Here again, we are filtering it. So after filtration, this figure F you are getting. And finally, the refractive index change data, you can get somewhat like that. So you see the refractive index change, if you take the absolute value, then the refractive index minimum value of the refractive index is in the minus side. Okay, so that is not physically acceptable. So you can get the profile well, but the absolute values of the refractive index change are erroneous. So what we have to do, we increase the refractive index, effective refractive index value in our computation so that at the outside of the waveguide or the minimum value of the refractive index change, what we can obtain is 0. So at that particular mode index value, we can take the effective refractive index. So the measurement of this process is for ordinary refractive index change. It can be performed for any other refractive index process. And one important thing is that you have to choose the cutoff frequency in such a way so that the signal power in the passband has to be more than 95%. The result is applied for UV-written waveguides also. The blue one is the amplitude profile, the red one is your index profile. Now compare this with what previously people are getting without using the noise, without using the filtering process, as well as the exact values of the effective refractive index. So this is the depth one. We have also applied this for SU8 waveguides. This is the horizontal or a lateral profile, and this is the vertical profile. You see the mode index values are very close because this is the fundamental mode. Ideally, this mode index should be equal, okay? But it's not equal, but very near to that. So that makes us confident about our computation process. And the cutoff frequency, what we have used for this calculation is 310 millimeter. So in the conclusion, the loss measurement by using a low finesse interference pattern due to fiber output and waveguide input is presented. The measurement process is cost effective but accurate. White light spectral analysis is introduced to identify multi-mode, single mode, and cutoff wavelength zones of a waveguide. And third, simultaneous estimation of mode index and absolute refractive index profiles of the waveguides were done from measured near field intensity distribution. Thank you. Now, any questions?
Thank you, sir.
Okay.
Thank you, Dr. P. Ganguly. It was a nice talk on characterization methods of integrated optic waveguides. So now we have questionnaire section. So please ask any questions. You can come and ask any questions. Any questions? Sir, I have one question.
Yeah.
So you have fabricated SU8 waveguides, right?
Yeah.
So I want to know which SU8 polymer solution, like that is what is the resistivity and what is the series of SU8 polymer solution we have used it for?
Actually, yeah. So we are using SU8-5 and SU8-2 for our application. And
pardon,
since
sir?
SU8-5, SU8-5, yeah, it's only one company is fabricating or preparing this particular photoresist. It is Microchem from USA. So,
okay, sir.
so they are supplying a series of SU8, SU8-2, SU8-5, SU8-10, etc. So for waveguiding application, we have used SU8-5.
And one more thing, sir, is it that height of that waveguides, is it required dimensions is there? Like you have chosen, you said like 2005, I think. So that 5, it means it will use 5 micrometer height.
2005, no, it may not be. 5 will, you can, depending on the spin speed, when you are coating photoresist, depending on the spin speed, the thickness will depend. Okay, you can also add some solute within the solute, decrease the viscosity of the SU8 by using some other chemicals, so that the height is reduced. Because for single mode application, you cannot go for 5 micron, 10 micron, etc. In that case, it will be a multi-mode waveguide.
Okay. And one more thing, sir, I want to know, you mentioned it is CMOS compatibility. Can you explain a little bit that?
CMOS compatibility means same fabrication process we can use as we are using for making microelectronic applications. So if you are going for a chip in silicon, what the fabrication process, either diffusion technique or implantation, lithography, thin film deposition, doping, these are all CMOS compatible process.
Okay. Thank you, sir. Thank you very much. So we have after this session 3 research articles presentations. So if you are interested, can you join with us? There is a next section I'm going to conduct online 3 talks.
No, I have told Dr. Shagota Samanto regarding that, because I have to.
If you have time, you can join with us, or else you can leave it now. I am going to conduct that research.
Okay. Thank you. So if you have any other questions or queries, you can contact me over email.
Sure, sir. Thank you, sir. Thank you very much.
Okay. Yeah.
Fine.
Yeah.
So we have total 15 minutes. Out of 15 minutes, the presentation time is 12 minutes, followed by 3 minutes questionnaires.
Yeah. Okay.
Please
Yeah.
go ahead.
Hello all, my name is Aniket Dhongde. I am a PhD student from University of Glasgow, Scotland. So today I am giving you the presentation on DC and the RF characteristics of buffer-free AlGaN HEM and MESHEMs using the silicon nitride passivated MESA side balls. So the GaN device application. So where mostly the GaN devices are used, they are used mostly for the wireless communication, military and the radar system, satellite and the space application because of their high frequency and higher band gap, as well as the higher power. So the question is why we use GaN. So there is many reasons, but the important reasons are the GaN has the higher band gap. Due to the higher band gap, it needs a higher breakdown, means it's provide us the higher breakdown strength. Also the higher mobility and the saturation velocity, we got the higher carrier higher carrier density. So we got the higher drain current, and so because of the higher drain current, we got the higher transconductance as well. And also the high breakdown voltage, so we can operate the GaN devices at the higher operating temperatures. So this is the okay. for the basics of the GAN HEMS, so you can see on your left-hand side, the typical GAN HEM structure, the source, gate, and the drain. And you can see the barrier layer is aluminum gallium nitride and the buffer layer is gallium nitride. Because of the polarization effect is spontaneous and the piezoelectric polarization, the two electron density gas is formed. We call it as the 2-deck. So my device fabrication flow is start with the alignment markers. We use for positive photoresist for making all the fabrication process and photolithography. So the another step is the MESA isolation. So we use the borium trichloride and the chlorine plasma gas, which is dry gas, to isolate the device from each other. Then we deposit the ohmic contacts. So here we use the titanium, aluminum, molybdenum, and gold metal stack. And after depositing, we anneal at 800 degrees for 30 seconds for getting the good contact resistance. Then we deposit that very thin 10 nanometers of silicon nitride by using the PECVD as a gate dielectric layer, which is cover all the gate region in between the source and the drain, and also the MESA side walls you can see in the figure. And after that, we deposit the gate contacts is in nickel and the gold, and then the bond pads which using the for the metal is titanium and gold. And finally, we deposit the blanket layer of the 100 nanometers of silicon nitride as a passivation layer. So on the left hand side is figure number A. You can see this is the HEMT structure, and on your right hand side is the MESHEMT structure. So here we use the epi layer of GaN on silicon carbide. So the GaN cap thickness is 2 nanometers, and the aluminum gallium nitride, the barrier thickness is very thin, like 14 nanometers, and the aluminum content is 30%. And here is no buffer, is only the GaN channel, which is very, very thin, like 250 nanometers. It's on the aluminum nitride as a nucleation on the nucleation layer. So in the MESHEMT, only the difference is that we deposit the 10 nanometers of silicon nitride is a gate dielectric before putting the gate metal. And in figure C, you can see the SEM image of the 200 micron wide devices. So here is the contact resistance measurement. So we use the two different wafer, one wafer for the HEMT and one wafer for the MESHEMT. So we use the CTLMs for measurement, the contact resistance, and we got 0.65 and 0.59 ohm millimeters of millimeter of contact resistance in HEMT and the MESHEMT. On both the wafers have mobility, and the sheet resistance is about 200 centimeters square per volt second, and the sheet resistance is nearly 330 ohm per square. In IV measurement, so we sweep on your left hand side, you can see we sweep the drain voltage from 0 to 15 volts, and the VGS is the gate voltage is the VGS at highest as 1 volt. So we got the higher drain saturation drain current, which is 728 milliamps per millimeter in the MESHEMT, and in the HEMT you can see here we got like 460 milliamps per millimeter. Also, you can see that the R-on resistance is significantly low in MESHEMT as compared to the HEMTs. On your right hand side, so we sweep the drain voltage from 0 to 40 volts to see the self-heating effect in both in the HEMTs and the MESHEMT, and it shows like the significantly the maximum current drops is 20 and 90%, 19% in both like HEMTs and the MESHEMTs. So here is the transconductance and the threshold voltage of device. So in the blue color, you can see the the drain current and the transconductance characteristic. So the threshold voltage of the HEMS is nearly around 2.6 volts. And you can see in the red color one, the the threshold voltage of the MESHEMS is nearly minus 6.5. So the higher the MESHEMS has got the more negative threshold voltage, because of we deposit the 10 nanometers of silicon nitride. So we need the higher bias to control the channel. So that's why it shifted to more negative side. And also we got the higher tran conductance is in MESHEMS as compared to the HEMS. In leakage current, so you can see that in the blue color, the leakage current is quite high in the HEMS, like the Schottky gate HEMS, as compared to the MESHEMS, which is around like 10 order of magnitude is less, because we use the after like the dry edge, we passivate the sidewalls of the device with very thin, like 10 nanometers of silicon nitride. So that's why it help us to reduce the gate leakage current. And we can also say that like the silicon nitride dielectric thin film act as a efficient gate insulator. Also here, we like, as I said, we use the silicon nitride gate dielectric to decrease the leakage current is also connected to the high breakdown voltage. So the drain current is increases over the drain voltage, which is sweep from 0 to 200, because our measurement lab, if we made maximum compliance is 200 volts. So you can see that the HEMT current is rising, but it's not doesn't break to 200 volt. But the current is rising, like the drain current is rising, but in MESHEMS is still the current is in nanoamps. So we can say that like the MESHEMS has maybe the higher breakdown voltage as compared to the HEMS. Also, we calculate the FT and the Fmax of the devices. So you can see that the HEMS and the MESHEMS, the cutoff frequency is 4.7 and 6.3 for the HEMT and the MESHEMS, and the maximum oscillation frequency is 9.4 and the 15.7 gigahertz. So in a conclusion, I can say like the MESHEMS device has a higher drain current and the higher transconductance as compared to the HEMS. Also, the MESA sidewalls help us to reduce the leakage current, and further is enhance the breakdown voltage in MESHEMS as compared to the HEMS. Also, maybe we can use the HEMS structure is a good choice for application for the high power and the high frequency devices. Thank you. Yes, any question? Yeah.
So thank you, Aniket. Once again, it's a wonderful, nice talk on DC and RF characteristics of buffer-free aluminum gallium nitride, MIS HEMT using silicon nitride passivated meta sidewall research article on this presentation. So any questions, audience? Any questions? My side, I have one question, Aniket.
Yeah.
So you have fabricated this MIS transistor. What is the aluminum nitride, right, material? How you have deposited that? How you have what type of? The 60 nanometer
is a nucleation layer.
Yeah.
Yeah, it's the 60 nanometers of nucleation layer, which is very pure quality, and it acts as a back barrier for the buffer free structure. Because usually if you see is the typical HEMT structure, the GaN has the thick buffer, like 500 nanometers to roughly 4 microns up to that thickness. But this is the new kind of EP layer structure. Here is no buffer. They use the very pure quality of the gallium nitride channel and the aluminum nitride, the nucleation layer.
So the aluminum, this nucleation method means, is it any difference you will get it with this what we call the method atomic layer deposition? Same way.
Actually, we use this layer to minimize the friction between the GaN channel and the silicon carbide.
Achha.
Yeah.
So it's not the ALD process.
Yeah.
It's not ALD.
It's not the ALD, it's the MOCVD.
MOCVD. Okay.
Yeah, MOCVD process.
Okay. Can you little bit explain about how you have characterized in one and which tools you have used for IV characteristics and
okay, so we use a B1500 analyzer to measurement for the DC, all the DC measurement.
Which one?
Is 1500, B1500, Agilent.
Agilent, okay. Semiconductor characterization system.
Yeah, yeah. So
Okay.
to characterize like all the DC and the RF measurements.
Okay, fine.
Yeah.
Thank you. Thank you once again, Ankit.
Thank you, sir.
You can stop your screen sharing. So next we have another research article on enhancing performance in full adder circuit with novel gate diffusion input techniques. So I think the authors are ready here. Saurabh Kumar and B. Avinash.
Yes, sir.
Yeah. Please, who is presenting?
Saurabh Kumar, sir.
Okay. I'm giving as a co-host to you. Please share your presentation and then you can start.
So, good morning, sir. Good morning, everyone.
Yeah. Please.
I am Saurabh Kumar from NIT Kurukshetra, and my paper title is Enhancing Performance in Full Adder Circuit.
Sorry for the interpretation. So let me tell about this instruction for this presentation. So you have total 15 minutes. Out of 15 minutes, 12 minutes presentation, followed by 3 minutes questions. Okay. Please
okay, sir. So the topic is enhancing performance in full adder circuit with the novel gate diffusion input technique. So the contents are like that: introduction, objective work done, circuit design, simulation, and conclusion. So while designing high performance digital logic circuit, the critical parameters are power consumption, power delay product, area occupied, and the propagation delay, which are the most critical parameter which defines the efficiency of any digital logic circuit. So adders are one of the digital circuit that are widely used in VLSI application, including microprocessor, DSP processor, and it serves as a foundation for operation like addition, subtraction, multiplication, like Booth multiplier, sequential multiplier. So several approaches can be used to lower the power consumption of full adder circuit. Like we can reduce the number of transistor, which in turn reduces the power consumption. With reducing the number of transistor with different design technique, we can reduce the power consumption. We can reduce the static power and short circuit power by avoiding the direct path from supply to ground in full adder circuit, or varying the gate sizing of the transistor, the power consumption and delay can be optimized. And other way is like realizing the full adder circuit using XOR, ignore gates and 2:1 mux. This way the power consumption can be reduced. So objective is to improve the performance parameter of full adder circuits like power consumption, power delay product, area, and propagation delay through different design technique. And gate diffusion input technique approach helps to achieve the lower power consumption as compared to the other design techniques like footed domino approach and conventional 2080 full adder. And the design circuit simulation are carried out using cadence tool with a supply voltage of 1.8 volt. So this is the conventional CMOS 2080 full adder where we have pull down network and pull up network. And
Hello? Hello? Saurabh?
hello, hello, hello.
Yeah, Saurabh Kumar.
Yeah, am I audible, sir?
Audible, but your screen is disconnected. Can you check once again?
Okay, sir.
Yeah, go
Yes,
for
sir.
Yeah. Now, okay. Please go ahead.
So the dynamic logic suffers from that output degradation in pre-charge mode, and so we go for domino logic approach where we use inverter followed by a keeper transistor. So here from this we can minimize the degradation, output degradation. So this is the footed domino full adder where it can be realized using 22 transistor, and we are using one keeper transistor that is emit. The transistor named is emit, which is used to keep the logic high value in pre-charge mode, and the same carry and sum will be realized using this circuit, and it reduces the leakage power dissipation, as we are using the stacking method to reduce the leakage power dissipation in footed domino logic. Now comes the GDI approach, where you can a low power digital circuit can be designed using GDI approach, and the GDI cell consists of only two transistors, that is NMOS and PMOS, and gate are connected to both NMOS and PMOS, and we give input to all three terminals and get a different function like mux, and, or, not, and you can design adder using this approach. So the GDI full adder shown below enables to achieve even less power, and the XOR gates can be designed using 4 transistor, that is A and B we are using to make XOR gate, and further it is going to inverter, and then 2x1 mux to generate the sum and carry output. So this is the simulated design of conventional 2080 adder, and this is the output and power analysis graph. So the average power consumption I got with this approach is 27.8 microwatt, and with the footed domino approach I got this is the simulated output graph, and the average power which we got is 13.1 microwatt, and we can even get less power with the GDI technique. And this is the simulated design of GDI adder, and the outputs are shown here, and the average power is 11.9 microwatt. So the comparison of various performance parameter, including power consumption, number of transistor used, power delay product, are shown below, where in CMOS logic approach we are using 28 transistor, footed domino 22, and GDI logic 10 transistor to realize the circuit, and we got that in GDI logic we got 11.9 microwatt, which is less than the above 2 approach, and the power delay product is also less for GDI logic. So we conclude that the GDI full adder approach consumes 56.9% less power as compared to conventional 2080 full adder, and 8.47% less power when compared to 22T domino full adder without delay degradation. And the power delay product is also least amongst all the full adder, which implies that it has better performance among other design techniques. So that's all for it, sir. Thank you.
Yeah. Thank you, Saurabh Kumar.
Thank you, sir.
Any questions? Take student. I would. Yes. You have any? Saurabh Kumar, I want to ask you on the title of your research article.
Yes.
So you have mentioned a novel gate diffusion input techniques, right?
Yes, sir.
So like in cadence tool, like you have designed in cadence tool the fully adder circuit with the novel gate diffusion input technique, right?
Yes, sir.
What are the parameters you have optimized in the cadence tool with equating or equivalent circuit of a novel gate diffusion transistor?
Yes, sir. Sir, we have optimized the power consumption and power delay product of the GDI full adder circuit, and we have compared the same using conventional and footed domino approach.
Okay, logic is fine. Okay, I'm asking about like you in the last you have mentioned the comparison table with CMOS as well as this footed domino logic, right? With
Yes,
GDA logic you have compared. So
yes.
what I'm asking, GDA logic, like you have used 10 transistor, 10 number of transistors, right? Per
Yes.
ladder circuit, right?
Yes, sir.
So can you explain what is the performance characteristics you got for one transistor, a GDA logic?
For like, sir, I got for all the transistor. I have calculated for all the transistor.
Based on what is the performance characteristics with that you have implemented this fully adder using the GDA logic?
Performance characteristics of like power consumption, sir, and that delay and power delay product, and the area occupied.
No, what I'm asking, so you have total 10 number of transistors in full adders, right? Using GDA logic.
Yes, sir.
So I'm asking about in the device point of view, one transistor, what is the performance characteristics of one performance of GDA logic?
Sir, like when we are using 10 transistor, the resistance and the capacitance value will decrease, which will decrease the power consumption of the circuit. So the load capacitance which we will get using this GDI approach will be less than that of the two adders design technique, and even the resistance value will be also less.
Okay. Okay, thank you. Thank you once again.
Thank you, sir.
Okay, stop your screen sharing. So next we have another research article, design and simulation of reversible logic gate using HCS micro model. So who is there authors for this paper? Mr. Chaudhary. Hello? Can you disconnect? Can you log out once and you log in once again? Snigdha. Yeah, perfect.
Myself, Snigdha Chaudhary Kola, and
Yeah. 1 minute. 1 minute. So you are the now host for this session. Welcome to this talk. The design and simulation of reversible logic gate using HCS micro model, presenting by Snigdha Chaudhary.
yes, sir. So my screen is visible to all of you.
Yeah. Please share your presentation. I give you an. Please share your PPT. Fine. Make it full screen now.
Yes, sir.
Perfect.
Okay. Thank you, sir. Good
Yeah,
afternoon,
please.
everybody. Myself,
Yeah.
Snigdha Chaudhary Kola, and I am a PhD student of National Institute of Technical Teachers Training and Research, Kolkata, West Bengal. Today, I am here to present my paper, which is based on the design and simulation of reversible logic gate using HCS macro model. In this presentation, the contents are journey of CMOS technology, limitations of CMOS devices, emerging post-CMOS nano devices, ACT, hybrid ACT, CMOS macro modeling, HCS realization of reversible logic gates, conclusion and references. In this PPT, we can show that first figure shows us the single NAND gate, and the second figure shows us a CMOS NAND gate with 4 transistors on a silicon, and the last figure shows us a processor with 55 million of transistors on a single chip. So we can realize how the electronics are going on in their advanced stage. So many chips are integrated on a single chip in a processor. And Sir Gordon Moore has also said that the number of transistors or number of components are getting doubled on a single chip in every 18 months. But this scaling down of CMOS technology cannot continue forever. It will hardly go beyond few nanometers as it suffers some physical limitations such as minimum allowable channel length, random doping placement effect, depletion depth and junction depth, minimum gate oxide thickness, and minimum supply voltage like drawbacks. And in this figure, we can see that the leakage power is a severe drawback of this scaling down of CMOS. In this figure, we can also see that the modern processor chip consumes almost 100 watts of power, of which about 20% is wasted as a leakage through the transistor gates. So there are so many questions. Is this the end of electronic industry? Can Moore's law still continue further? To solve this, thus a new device principle of operation is required. As a consequence, the search of new principle of operation of the small size device is becoming more and more important. And the emerging post-CMOS nano devices are like quantum electronic, carbon nanotubes, resonant tunneling diode, rapid scaling quantum flux, rapid single quantum flux, and the most important, that is the single electron transistor, which is known as ACT. This is the structure of a single electron transistor. In this single electron transistor, we can control the single electron or a few number of electrons. The single electron transistor is a new type of switching device that uses controlled electron channeling to amplify the current which is flowing through it. It implies also the possibility to control the movement and position of a single electron or a small number of electrons. But CMOS has some advantages which are the drawbacks of ACT. The main drawbacks of ACTs are low current deliverability, small voltage gain, and low temperature operation, which are again the advantages for CMOS, such as high speed current driven, high gain, and room temperature operation. So, Professor Shantanu Mohapatra and his co-researchers has made a new device by amalgamating this CMOS and ACT, which is known as the MIB model. But for simulating this MIB model, there are some drawbacks because CMOS can be operated by using SPICE, whereas ACT needs the simulators like COSEC, MOSEC, Silvaco, and Simon to operate. To overcome this problem, YU has made a new model that is known as the macro model of ACT. This is the basic macro model of ACT by which we can simulate the hybrid CMOS ACT by using a single software like CMOS, like MATLAB. Again, the reversible logic gates have many advantages in these electronic industries. The gate or circuit that does not lose information is known as the reversible logic gate. Reversible are circuits in which the number of inputs is equal to the number of outputs and there is one-to-one mapping between the inputs and outputs. So we can get the inputs from the outputs also. That is the main advantage of reversible logic gate. And there are some other advantages such as lossless information processing, low power consumption, low power dissipation, high speed of computing, and least garbage value generation. And in my paper, there are so many reversible logic gates like Feynman gate, Toffoli gate, double Feynman gate, Fredkin gate, Perez gate, and so on. But in my paper, I have simulated two reversible gates such as Feynman gate and double Feynman gate by using this HCS macro model, and I have also simulated it by using the Simscape of MATLAB. The first figure shows the conventional figure of the Feynman gate. It has two inputs A and B and two outputs P and Q. P equal to A and Q output gives the XOR operation of inputs A and B. You can see this figure. This second figure shows the CMOS design of Feynman gate by using CMOS. Here two PMOS and two NMOS are there. In my investigation, I have kept this PMOS as itself and we have replaced these NMOSs by using the two HCS macro model and also simulated it by using the Simscape of MATLAB. And this is the truth table of the Feynman gate, and this is the output of the Feynman gate by using the HCS macro model, and you can see that the output is as it is the normal Feynman gate, but the main advantage is that it can operate in very low voltage. I have applied here at 0.05 volt and it also operates in this low voltage. And this is the double Feynman gate. In double Feynman gate, there are three inputs A, B, and C, and the corresponding three outputs are P, Q, and R, where P equal to A, Q equal to A XOR B, and R equal to A XOR C. And this gives the CMOS, the design of double Feynman gate by using CMOS, where there are three PMOSs and three NMOSs, and I have replaced these NMOSs by HCS macro model, and PMOSs are given as it is, and we get the output by using Simscape of MATLAB. And this is the truth table of double Feynman gate by using the three inputs A, B, and C, and outputs are P, Q, and R. And as usual, we have got the outputs which is dependent on the inputs A and A, B, and C, and outputs shows the same characteristics as it gives by using the CMOS. Now, the conclusion is that in present days, the macro modeling of ACT has become very popular in nanoscale research work as it uses very low voltage and the power dissipation is very less. The proposed model can be the key features of the advanced computing in single electron topology and accompanies the post-CMOS era. By replacing the NMOS by ACT macro model also offers ultra low power dissipation, nanoscale size, and also perform very well in low voltage region also. On the other hand, new proposed models also offers high speed of response, high output gain, high current driven capability, compact fabrication like features as PMOSs are used here, which makes it satisfactory result in different designing technology. Above all, as all the simulation have been done by using a single simulator, SimScape in MATLAB, as it is easy to debug, easy to symbolic computation, and can call external libraries, can interface with different hardware, and so on, which make it highly acceptable by the researchers in different VLSI design and so on. Here I have used the MATLAB only, but in future I will design, here I have also designed only Feynman gate and double Feynman gate, but in future I will design the Fredkin, Perez and Toffoli gate also. And here I have used only the MATLAB as a simulator, but I thought in future I will use the PSpice also to simulate these circuits. And this is the future scope of my work. And these are the different references. Thank you.
Yeah. Thank you, Snigdha Chaudhary.
Yes,
It's a nice talk on design and simulation of a reversible logic gate ECE micro model. So now I'm going to ask you any questions from audience? Come forward and ask.
Ma'am, good afternoon.
Yes.
Can you go through that previous logic and explain, ma'am?
Okay.
I can't understand that.
This one?
Yes, ma'am. But before that logic, ma'am. Before that logic.
This one?
Ma'am, that one. How to P is equal to A, ma'am?
This is the reversible gate. This is the conventional reversible gate, and which is made by the scientist Feynman, and he has made this logic gate. It is already in market, and I have just designed this Feynman gate by use, and researchers have already made this Feynman gate by CMOS. Here I have designed this Feynman gate by using the CMOS with ACT macro model. And the normal nature of this Feynman gate, it has two inputs and two outputs, P equal to A and Q equal to A XOR B. Now, you may ask one question, that is, why the reversible logic gates are important? We have the normal gates, but why these reversible gates? It is that in reversible logic gates, what is the advantages? Suppose you have normal XOR gate. In normal XOR gate, just a minute, you look this figure. In normal XOR gate, what is happening? For if input A is 0, B is 0, then the output Q equal to A XOR B, that is 0. And if input A is 1, B is 1, then also it gives the output Q equal to 0. But how could you find out? If you get the output 0, then how could you find out A and B is 0 or 1? Is it possible for the normal XOR gate? No, That's why the reversible logic gate is important. By using these reversible logic gates, as the Feynman gate has two outputs such as P equal to A and Q equal to A XOR B, by finding out this P output, you can find out the inputs also. That means from the output, you can find out the inputs also. That is the main advantage of this reversible logic gate. If for Q, for both inputs A equal to 0, B equal to 0, the Q equal to 0 for normal XOR. For A equal to 1, B equal to 1, Q equal to also 0 for normal XOR. But if you find out this value of the P, then if P equal to 0, then you can say that A, B both are 0. And if P equal to 1, then you can say that A and B both are 1. So in this way, from the outputs, you can get the inputs. So that is the main advantage of the reversible gate. And your question, how this P equal to A, it is the normal nature of this Feynman gate, Feynman reversible gate.
Okay, ma'am. Thank you.
Most welcome. Any more questions?
Any other questions?
One more thing, madam. In real-time application, where we use reversible logic gates, tell me one more example.
So, sorry, sir, I can't hear.
1 minute, 1 minute.
In real-time applications, where we use this reversible logic gate, can you please give me an example? Hello, am I audible?
Sorry, your voice is so low, I can't hear.
I'll tell you the part of
Yes,
from
yes,
our
yes,
audience.
yes,
So she's asking what is the real-time applications for reversible logic gate?
Real-time application is that I have told you that you can't find out the inputs. You can't get any information about the inputs from the outputs of the in case of normal. In case of normal gates, but you can find out the you can get a concrete information about the inputs from the outputs by using these reversible logic gates.
Thank you, ma'am, once again. So my side, I have one question.
Yes, sir.
Can you go back to that micro model, HCS micro model?
Just a minute. Yes, sir. ECS macro model.
So this is a basic SCT model and micro model of SCT.
Yes.
So I want to ask one basic question. What is the difference between ternary logic and reversible logic?
Actually, sir, in reversible logic means we get the outputs, we get the inputs from the outputs also.
Okay.
That is the main advantage of this reversible gate. But it is the only macro model, reversible, and it is, I have applied this one in the reversible gate.
Okay. So this entire circuit
This is the another model. Yes,
set
sir?
model. Am I right?
Yes, sir.
You have implemented with set model.
Yes, yes, yes. Actually, this model has invented by the YU et al.
Okay. Okay. Thanks, ma'am.
Thank you, sir.
Okay. So next we have one more talk in this session, last talk. So I don't have any details for this talk. I think Renuka can turn on your video and I'm going to give you just a minute access to post for your presentation. Please share your So now in the last talk, we have design insight into NC fit based energy efficient circuit. So please go ahead, Renpa.
Good morning to everyone. This is Renuka Chaudhary. Today I am going to present about design insights into NC fit based energy efficient circuits.
Renuka, your audio voice is not clear. Can you please check it?
How is it?
No, audio. Make it full screen.
Now
Okay,
is-
fine. Video is okay. Audio.
Now you can hear, sir.
Yeah. Please go ahead.
My title of my presentation is Design Insights into NCFET-based energy efficient circuits. Outline of my presentation is scope of steep slope devices for energy efficient circuit designs with VDD scaling. And next about NCFET device structure and its operation, and design insights into NCFET device characteristics and circuit characteristics, conclusion and its differences. Here is the steep slope devices. If the threshold voltage increases, then the on current doesn't change. The off current is reduces. If the off current is reduces, then ion die-off will be reduces. If it depends on the subthreshold slope. If the steep slopes curve will be dependence on the off current. To make it clear that subthreshold swing of the short channel MOSFETs and NCFETs, to overcome the limitations, more researchers are investigating on this. In this, NC layers are suppressors for the short channel effects, including the subthreshold voltages, and that is difficult to the NC to help the maintaining of the hysteresis-free circuits. In this, the C oxide, C source, and C depletion and C drain are acting as a mass capacitance, and CFE is the ferroelectric capacitance. When we are applying some internal voltage amplification for the mass capacitance, we are getting the same, but whereas in the ferroelectric capacitance, we have some amplification at 0.4 volts, and there are two key improvements with the high performance and low power applications. This NCFET circuits operates at a lower voltages, reducing the VDD in the MOSFET. The total power consumption will be reduces. These are the NCFET device structure and operation. Here, the ferroelectric layer is sandwiched. This model was proposed by Suman Datta and Salahuddin. And here, the ferroelectric material is sandwiched between the two metallic layers. These metal layers are suppressed with the non-uniformity coming from the domain formation of the ferroelectric material. This is the equivalent capacitor model of the NCFET. Here, CFE represents the equivalent ferroelectric material of the resistance RFE. These are the design insights into device characteristics. Here we are comparing the NCFET with the baseline MOSFET. For comparing the NCFET with the baseline MOSFET, we are achieving the better on current compared to the baseline MOSFET at TFE of 1 nanometer. We are comparing baseline MOSFET with the TFE of 1 nanometer, and we are getting the lower leakage current and the lower subthreshold swing for the NCFET. We will achieve the subthreshold swing of 50 millivolts per decade. These are the device characteristics with the TFE variation. We have analysis that device characteristics from 0 nanometers to 10 nanometer. Among that 10 nanometer, we are achieving the optimal device performance at 3 nanometer to 5 nanometer. And we are getting the lower leakage current and achieving the higher on current from this. These are the design performance and benchmarking with this is the basic inverter circuit. Static CMOS inverter. From this inverter, we have done the VTC characteristics and the noise margins and the differential gains. We are achieving the better performance at 3 nanometer to 5 nanometer. If we are beyonding that nanometers, this enters into the hysteresis. These are the NCFET inverter noise margins. In this noise margin, at a 0.5 supply voltage, at a TFE of 3 nanometer, we are achieving the optimum noise margins at TFE of 3 nanometer. Here we are achieving optimum at TFE of 4 nanometer. These NCPET operations. These are the noise margins depicted with the NCPET. These are the NCPET differential gain. In this differential gain, we are achieving the maximum gain at TFE of 3 nanometer at a 0.5 supply voltage and TFE of 4 nanometer at a 0.2 supply voltages. This NCPET demonstrates it exhibits the better characteristics from the logic devices with the ferroelectric thickness ranging from 3 nanometer to 5 nanometer, and it has optimum device performance. Inverter and noise margins get the optimum values at a TFE of 3 nanometer. Finally, these NCPET characteristics are suitable to the hardware implementation through the hardware security implementation and the side channel attacks. These are the references. Thank you.
Yeah, thank you, Renuka. Any questions? Can you show me the circuit diagram of NCPET differential amplifier? NCPET inverter differential amplifier circuit diagram.
These are the differential
characteristics, right? These are the characteristics. I want to see NCPET inverter differential amplifier.
This is the inverter circuit, sir.
Yeah, this is, I agree. This is inverter. Okay. I want to see NCPET inverter differential amplifier.
I did not design the differential amplifier.
But I have seen the characteristics.
I did not mention here, sir.
Next slide. This is inverter noise margins.
Noise margins.
Okay, fine. According to the circuit simulation, you got the inverter noise margins, these characteristics. Okay, fine. Next.
These are the differential gains.
Inverter differential gain. Okay.
Yes, sir.
There is no circuit diagram. It is inverter.
From this, from the inverter characteristics, we can, from the analysis, we will get these noise margins and differential gains. Sir.
You have calculated from the inverter, right?
Yes, sir.
But why you are saying no circuit diagram?
From the inverter.
Okay. One more question. Can you go back? Go back to slides. Go back. Here. This is a device characteristics with.
These are on current, off current, and ion by off ratios.
Can you explain device characteristics with the T?
TFE, ferroelectric thicknesses.
Is it
We can vary the parameter of the
notation is correct. X-axis.
Yes, sir. Ferroelectric thicknesses.
Ferroelectric thickness.
Thickness. We can vary the thickness, and we can measure the on current and off current. And
varying the different ferroelectric thickness from 0 to 10 nanometers.
Yes, sir.
On current and off current. So what is the ratio you got it? Do you have any value?
This is the ion by off ratio, sir. I mentioned only for the optimum performances.
What is the first one is
153 into 10 power 3.
That is on and off ratio.
Yes, sir.
On and off ratio. What is okay? And next one?
429.
So apart from which one you are choosing, like optimum devices performance you mentioned in this window, right? Which ratio is good for your application point of view?
153 is good for our applications, sir. For future designs, we are proceeding with the security applications.
Okay. Okay, good. Any questions from audience? Okay, thank you. We can stop sharing and log out.
Good morning to everyone. I am Naren Naik from Department of Electrical Engineering and the Center for Lasers and Photonics at IIT Kanpur. So my like the talk which I thought I should speak, which I would be presenting now, is basically on fluorescence-based biomedical tomographic imaging. And the aspect is, as we have written in the title, functional, static, and dynamic tomographic imaging, and the use of optical fluorescence for that. So this is something which I'll be talking about. This is work done with my PhD students, Nishigandha, Om Prakash, and Prabodh. And Professor Gambhir is the from SGPGI Lucknow, and he's our medical collaborator in our work. So challenge of early diagnosis is, sorry. So we have, if you want to choose, if you want to get information about a pathology in a tissue, early cancer, for example, you have, these are the stages. You have a normal cell, then you have a metabolic, you have these structural changes, which you see, which would be called, say, a cancerous growth. So these, on the right side, what you see is, it denotes only morphological or structural changes. On the left side, you have the metabolic changes before these structural changes. Now, the only early cancer functional or physiological way of evaluating presence of cancer is using positron emission tomography or SPECT, PET or SPECT, mainly PET, and the remaining CT, MRI, ultrasound, they look at structural changes. So physiologically speaking, the current gold standard, as I mentioned, is positron emission tomography, and the optical or the non-radioactive option is basically only with optical fluorescence. So this is one of our main motives, to try to replace as many modalities as possible of nuclear medicine with non-radioactive optical fluorescence. So why are we now, the notion of what is tomography? I'm sure many of you are aware, so some of you may not be. So tomography is about reconstructing, seeing inside an object without cutting it open. But yes, you are seeing the insides. In MRI, you're getting data from, you're seeing inside the body as well. So it's a data-rich problem, whereas computer tomography, you only collect X-rays outside the body. So you can work with ultrasound, with microwaves, with optics, and that is what we do. We work with non-X-rays, non-MRIs, what is our main objective. And you have, the notion is quantitative. So when we talk quantitative imaging, that means at each point inside the domain, we need to associate a certain number, which tells us, which should help us in deciding whether is that part of the is that part of the object, is it a good tissue or a bad tissue? Okay. For example, CT scanners use so-called Hounsfield number, which is a normalized version of the absorption coefficient, normalized with respect to absorption, with attenuation or absorption in water. So the difference of any physical quantity of interest or electromagnetic property of interest between a pathology change over the normal. That's the whole idea. Optical, so you can use absorption, scattering. These are conventional issues which, I mean, physical aspects which come in when you have light interacting with tissue. Notion of fluorescence becomes crucial because there are sometimes you have some molecules which absorb light at a certain wavelength, and some gets excited and emits light at typically a longer wavelength. So this fluorescence it has very powerful capabilities of diagnosis, because also there are intrinsic fluorophores which develop, like as I mentioned, NDHFT, which have long full forms, but they are basically intrinsic fluorophores which get generated inside a tissue before the onset of full cancer. So this is basically pre-cancer we are talking about. And these are intrinsic fluorophores which the body generates. Then you have the extrinsic fluorophores which work as tags to certain molecules which represent the pathology. So these fluorophores, they basically and they have the property of giving out fluorescence. Okay, so that's why, so basically seeing the fluorescent light is as good as knowing as seeing where the pathology is. So motivation is, as I mentioned, one main motivation is to replace nuclear medicine modalities with optical fluorescence ones. Cancer detection, metabolic imaging, drug exploration. These are the basic applications that we have in mind. And mainly a point of care treatment can also be used in ICU treatments. Say metabolic imaging, issue is that sometimes everyone's metabolism or physiology is different. So the charts that a doctor sees in the ICU for a certain drug as to how long it should stay in which part of the body and how much time it takes for certain drug to be flushed out of the system, those aspects are entirely coming from data sheets which have been developed. Most of the time, the doctors are functioning on a kind of intuition based on their experience as to how quickly which drug gets flushed out of whose system. Now, if you want to change from intuition and experience, if you want to quantify things a little more, then there are these methods which we are looking at. You can, in principle, do it with nuclear medicine, so studies. So, but then that is hard to shift a whole CT, like a PET, CT or MRI machine to an ICU. It's pretty hard. So we have the optical alternative, which should be in a handheld mode, much more compact. Okay, so the modalities that we have worked on over the last decade or so, where we have breakthroughs with respect to system development, are with respect to fluorescence optical tomography, where we measure the fluorescent light. Yes, I'm sorry. Am I audible?
Yeah.
Okay. And also fluorescence photoacoustic tomography, because just optical tomography where you measure the scattered light from a tissue and try to get back the absorption coefficient inside of the objects of the tissue concerned. It has issues of stability of reconstructions. I'll come briefly to it. And also it has light decays very fast inside the medium, so you can't penetrate very deep. So there are resolution and depth of penetration issues, in addition to stability issues of the algorithm. in case of just optic-based tomography. So to keep the contrast of optical tomography, that means absorption coefficient of the pathology being significantly different from the absorption coefficient of the normal tissue. That is the essence, that is the contrast aspect of the optical property. We want to retain that, but we don't want the extra scattering that happens due to the light scattering. So we connect it with acoustics. So photoacoustic, basically you send a laser, illuminates the object of interest. The light creates heat. The heat generates, the heat in the specific region generates an ultrasonic wave that propagates out. And what is measured on the boundary of the object is basically a propagating pressure wave. So if you have phenomena of fluorescence as well, in this, that means you have light which is impinged on a tissue, absorbed, and you have a fluorophore sitting there, so it generates fluorescent light as well. So that adds to the heat, and in turn adds to the pressure wave that is being generated. Okay. And fluorescence photoacoustics is a very recent kind of modality, and becoming more important now because you have markers which have low toxicity. I'll briefly come to it later. Fine. If you want to work out a system, so finally, what we talk about a tomographic system is an algorithm-driven instrumentation. So you need instruments to measure the data. At the same time, what do you measure? How do you use that data is decided by your algorithm. So we need an accurate model. So it's a combination of physics and the signal processing required to extract the information from the data. And first is to model the data. So we need an accurate model for light in general and fluorescent light propagation through tissue. Appropriate choice of modality. That means fluorescence or with acoustics or some other combination of different modalities. We have even combined electrical impedance with acoustics. So we can use this any combination to get the best contrast and the best resolution with a good depth of penetration. So these are the aspects that we complement. So if you're talking of photo and acoustics, you're combining the good contrast of the photo part of the light optical tomography with the good contrast of the ultrasound. And last but not the least, in fact, last but first, is a suitable reconstruction scheme. When we say reconstruction, it is taking this data that you measure, like in the CT scan, the data is just X-ray use. You have multiple X-rays through the body, and you simply extract the So I intend to just spend some time on to deal with specifics of a light propagation model, why we require it in our tissue, and why we can't just use existing models which are there in the physics and literature or existing softwares. If you want to build a system, you need to look into the propagation models. And the second is a very current clinical, both are clinical level problems. It's a dynamic pharmacokinetic problem where you're evaluating the leakage rates of a fluorophore or a drug which you inject into the system. You are looking at the leakage from the tissue region to the vascular region and vice versa. And that tells you about the rates of leakage, tells you the presence of cancer or not. Because the permeability of the arteries, arterioles and venules in pathological tissue differ from that of normal tissue. So the tissues, so the vasculature starts getting leakier in pathological tissue. That leakierness is what we try to measure using so-called pharmacokinetic rates. Okay. So now I It's a brief schematic of what do we mean by fluorescence optical tomography. Incidentally, fluorescence can also be used, has a big application in guided surgeries right now, and also robotic-based surgeries. So fluorescence-based optical tomography is commonly being used. Okay. Anyway. So accumulation of fluorophore in an abnormal tissue, either external or internal. You have a source which is kept on the surface of the tissue. Then you have detectors which take the light out. So mu I is your absorption coefficient. I is for intrinsic, F is for fluorophore. Now, this is your process of fluorescence. So you have ground state, gets excited and emits into a middle zone, so as to say. It comes to a in-between zone and then it emits at, as I said, typically a longer wavelength. So you have your measurements, you set up your system based upon the sensitivity of your measurements to your unknowns. Your unknowns are your absorption coefficients. So these are the measurements you have. What you want is the spatial distribution of the fluorophore inside the body. You can't see it. So what gives you the spatial distribution of fluorophore from the boundary measurement is what is called your reconstruction algorithm. And this reconstruction algorithm requires the light propagation through tissue. Okay. So basically, and in tissue, since I mentioned fluorescence, so you have two processes happening. One, light is incident, it is absorbed, re-emitted, and that re-emitted light then propagates through the tissue and comes out at the detectors. So it's a coupled system. First, you have at the excitation wavelength, you have some propagation operation happening here. QX is the incident source. Fx is just an operator. I'll give you the form shortly. Phi is an optical field quantity, like the fluence, which denotes the energy. It's in this case, it is the it's the integrated radiance over all the angles. So this is what it represents, the fluence, and this is the propagation at the excitation. Then you have the excitation gets coupled. Excitation fluence gets coupled via this term, this efficiency term here, and gives rise to the fluorescent light at the emitted wavelength. So Pm is the light at emitted wavelength. Fm is the propagation operation at emission wavelength. So you have this coupled system of typically differential or integral difference that governs the propagation of light through tissue. And this solution, we need to get this solution right in order to get a reconstruction algorithm. I'm not going into detail, but this is the essence of it. And this is what has taken us all the time. And so we can either have linear relationships, that means we have a linearized model of propagation, or we go for a full nonlinear. When I say linear or nonlinear, it is the relation between your measurement and your distribution of your fluorophore. If this relationship is nonlinear, then we call it a nonlinear problem. Nonlinear reconstruction. If it is linear, we call it a linear reconstruction. I just give you, so we use what is called the simplified, the base model used, rather the best kind of model is the radiative transfer equation. I'm sorry, I haven't written the full form here. Now the radiative transfer equation, since it talks of propagation of the radiance, photons, as you can imagine, have a certain, they have the field like the radiance, which is energy like watts per watts per centimeter square per steradian. It's inside solid angle. So the radiance depends both on location as well as direction, because light it differs from point to point, and also it has a directional aspect. So there are 5 variables sitting inside the radiative transfer field quantity of radiance, which is position 3, angle 2. So as you can imagine, it is pretty computationally expensive. So commonly used diffusion approximation. And this is nothing but a heat type equation. It has issues because of it assumes that the absorption coefficient, low absorption coefficient media, in fact, it should be less than the so-called reduced scattering coefficient, to be precise. Not so accurate most of the time. For tissues of high vasculature, such as liver, kidney, etc., which is critical in even in the pharmacokinetic applications, metabolic applications, they have much higher absorption coefficients. So they would come under high absorption tissues. So diffusion approximation commonly used doesn't hold there. So we need something of a mezzanine, like a mezzanine, computationally less intensive than the full radiative transfer, but better than the diffusion approximation. So this is simplified spherical harmonics approximation. So the SPN is short form for simplified spherical harmonics. So you have the full radiative transfer equation, you have the so-called SN, which is the discrete ordinates where you divide the angle into certain discrete angles, or you have PN, which is the spherical harmonic approximation. So we have worked on this so-called spherical harmonics approximation. It was first introduced in neutron transport and then introduced into optical tomography in the mid-2000s. And our group set up the first nonlinear reconstruction scheme based on the SPN and inflorescence. Okay. So before operator looks like, I won't again, it's a coupled type equation. It's an elliptic type equation. You can see this is your diffusion coefficient. It's a diffusion type equation. So minus del dot d grad x plus k phi equal to s. This is the external source. This is the excitation field, and this is the emission field. These are coupled from this right hand side source term here. Okay, these are the associated boundaries. I don't. The aspect here is the notion of fluorescence quantum efficiency. And this quantum efficiency tells you how much of the absorbed light is converted into a fluorescence yield. And until now, the fluorescence yield in markers like cyan and green is very low, 0.016 or something. If that number is drastically increasing now, and with low toxicity. So you need to really consider high quantum efficiency media. Okay. So if you look at the sp3 approximation, it replaces this simple. This is one equation in terms of a scalar field variable phi x is replaced in the sp3 approximation to a couple. The first equation itself is coupled. This is matrix notation. Phis are composite moments. So we express our so basically, again, as I said, the aim was not to go into the detail, just to show you the structure. It comes in the form of a coupled elliptic system and with associated boundary conditions, which are the mixed Robin boundary conditions. Measurement is of the so-called excitance. That means you measure all the light coming out of the surface in whichever angle you want. Whatever is coming out normal to the surface is what we measure. And we have the option of going through linear or nonlinear reconstructions. When you go for nonlinear reconstructions, we do get taking good model into the full nonlinear model into account. As you can see, our reconstructions are far better. This is the pathological tissue, which this is the ground truth, these blocks in simulation. This is what we get from a linearized model, and this is you start with an initial estimate. You assume you know the problem geometry, so you know the locations of your measurements. Light propagation, you assume it, you model it via the SPN approximation. We have finite element methods. We compute the sensitivity of the measurements to the absorption coefficients. That is what this notion of using a so-called method of adjoints. Put this sensitivity into any nonlinear least squares algorithm. It's a regularized scheme because the problem is ill-posed. So this ill-posedness means if you change the data a little bit, your unknown is going to change a lot because of the nature of the operator. And elliptic operators are notoriously ill-posed. So these boundary measurements are fed into this nonlinear least squares, rather nonlinear regularized least squares algorithm. And we use the light propagation model and get an update for mu AF, what we have mentioned, absorption coefficient of fluorophore at excitation wavelength. Okay. Because that absorption coefficient, where it is more, it tells you where the presence of fluorophore is more. And presence of fluorophore is more where the pathology is more. So that way you get a quantitative picture of the pathology inside your object. Now, in the immune system, in different applications, say cervical cancer, these days they say they have a vaccine, but you need to actually see the pathologies as well. Moment you go near source, you need to modify your propagation model. Moment you go to a directed source in a certain angle, again you need to modify your model. So standard methods don't work. We have made certain modifications. And so you have anisotropy in the incident flux. This is because of directed source. Okay, excuse me. Yeah. So anisotropy in the incident flux is because of directedness of the source. And then once the light comes into the domain, the medium has scatterers, multiple point scatterers. And the property of the scattering aspect is taken care of in what is called a phase function, which tells you the probability of scattering in a certain direction when light is incident from another angle. So there is anisotropy. When we say anisotropy, it's not evenly scattering in all directions. Tissue is strongly forward scattering. So anisotropy in the scattering property, which is reflected in this notion of phase function, and anisotropy in the directivity of the source. So these two aspects we have combined it. I'll go through quickly. We've named it as the delta Eddington. The delta Eddington has been brought into tomography in approximation of the radiative transfer very long back in the mid-70s. But into the SPN approximation, we have incorporated it now. And so basically, what we are looking at is various regimes of scattering. So you have this from the source which is coming in. Since it's directed, we can decouple the directed component from the isotropic component. And in the scattering part, we can also remove the directed scattering, strongly forward scattering, from the more isotropic scattering. And diffusive regime talks of that more isotropic scattering. Transport regime is, when you say mean free path, it is 1 by the absorption plus scattering coefficients. So less than 1 mean free path is what we call the ballistic regime, where you just have the source coming in. Then you have the so-called transport regime. and scattering keeps increasing, and then you get the isotropic or diffusive regime. Point is, near source, directed source aspects and anisotropy in scattering need to be taken into account when we talk of when we try to build a system as per our requirements. We're talking near source, directed source. So these are the details of our calculations. I don't go in. I just show you what is the improvement which we get. This is running out of time, so I don't spend much time on this. Thing is, the measurements. This is just to show you the measurements, partial currents, what are called. We do see improvements in the amplitude and the phase. We talk of modulated light sources, and so we find differences specifically, especially in the phase measurements, modeling of phase. Sorry. So point is, we have improved estimates of phase, better fit with the measurement at excitation wavelength, and emission is we have improved in phase. Okay, and the accuracy is less sensitive to variation in optical parameters. This is in our forward problem simulations. So reconstruction studies, just to tell you the value of all this modeling, is that if this is the actual object, using our delta SP3 approximation, most of the time we have used, you have many orders of approximation. So this is the reconstruction. It's three-dimensional. It's all this is full three. This is the kind of reconstruction we get. So there is a difference. In fact, this is also, we're looking at fully nonlinear reconstructions with simplified spherical harmonic. So our algorithms, both of them. This is for ideal uptake. That means fluorophore is entirely outside the pathological domain. There is zero uptake of fluorophore. It doesn't happen in practice. So if you have single object with differential uptake, that means some background fluorescence as well. With delta SPN, you're still getting good results. With conventional SPN, you're seeing many artifacts depending on the source. In conventional reconstructions, you have artificial source which has to be one free path inside the domain. And that leads to artifacts. If I may go back, just to show you the images here, fluence at excitation. This left-hand side is what you see. One mean free path inside the domain. If you have this, I'm just showing the amplitude aspect. So it is not as the actual propagation would be happening, because it just has this bump here, nothing much around. As scattering reduces, the mean free path increases because it is 1 by mu a plus mu s. So this depth, this point comes lower, and that creates problem because at these points you have a spurious source which is coming into the picture in phase as well. So this particular notion becomes prominent in our reconstruction. So you get these artifacts here. Double object with ideal uptake. So we are able to see two clear objects. There are artifacts close to the boundary, some which can be removed, but here, as you can see, there's artifacts all around the place because the mean free path really goes into the object. So reconstruction studies are something which we are just in the process of completing now. And so this motivates the use of that extra modeling to get good reconstructions, because that is because doctor finally doesn't want you to tell stories. He just wants to see, is there a problem, and to reasonably accurately get the reconstructions. Okay. I think I'm more or less, am I out of time or do I have 5 minutes more? Am I audible?
Professor, I think we should
wind up and it take
Okay.
10 minutes, 5 minutes more.
Sorry?
5 more minutes because we are running
Fine.
out of time.
Okay, that's why I just thought I'll close that. So to increase now the other problem which I just thought I would introduce, I'll introduce only the problem. So we use photoacoustics, as I mentioned, to stabilize the fluorescence optical tomography. And so I'll just come, the key issue is high quantum efficiency and low toxicity markers. So quantitative fluorescence photoacoustic tomography is inevitable now, and the heat source has to take into account fluorescence modeling. Current status, and this is with optics, there's very less work which has happened with respect to pharmacokinetic studies. So when you talk of pharmacokinetic with respect to CT, PET, MRI, you have this notion of dynamic contrast enhancement. So you inject this nuclear isotope and you study what is its leakage patterns as it goes through the whole body. So you have poor temporal resolution often with respect to MRI machines, and spatiotemporal resolution, a lot of trade-offs are there, and very high costs of your conventional systems. You do have CT-based, CT-MRI-based system which have good spatial and temporal resolution. Cost is very high, portability very low. So we go in, and there's another aspect of drug characterization. Again, PET spec are very bulky, and you want to improve you want to reduce radioactive content. So the only optical way is using fluorescence, which is what we are exploring. And the key thing is it is now a dynamic problem because you are injecting a drug and at the time you are seeing how does it behave. So right now there is only multispectral optoacoustic or photoacoustic tomography that is being used. Certain groups are using this. We have suggested fluorescence-based optical tomography where we are explicitly modeling the fluorescence. That kind of photoacoustic tomography hasn't been tried yet, which is what one of my students had, his PhD is based on that. And I'll just show you the figures, I mean the results finally that we get. So here we're basically looking at the leakage between the plasma, which is the blood component or the arteriole and venual aspect of your tissue, and the extracellular, extravascular space. That means the space outside the tissue, which is synonymous with the tissue. So the leakage rates, these Ks are the leakage rates in terms of inverse second to and fro. So I use photoacoustics and we characterize it just by results that we got in the algorithm. Okay, so these are two objects. The blue lines represent the solid, the actual objects. This dotted, so we have to start with an initial estimate. We don't know how many objects are there, right? So we start with an initial estimate. We use what is called, we reconstruct the shapes and the typical parameter inside. That is something which algorithms which I had developed a few years back. So those are what we have used here. So we don't assume we know that there are two objects here. Inside each domain, we assume piecewise constant. We start with this one big object, we say, okay, and then the algorithm gets us into these two little objects. And these are the concentrations of the time variation of the concentrations of the fluorophore inside and outside the pathology. And these show you the reconstructions of the pharmacokinetic rates. And this is a concave single object. Concavity is well reconstructed. That means algorithms doing well. Okay, and the agreement also is very strong of the concentrations. So these are tumor mimicking phantoms. These are tumor mimicking phantoms with so-called invasive ductal carcinoma and adenocarcinoma. So AC and IDC, depending on these are different stages of cancer which we are looking at. Different noise levels. This is 1% noise, 40 dB. And this guy here is again, this is slightly increased. No, this is for the adenocarcinoma. We're getting good reconstructions. Concavity is being reconstructed well. And this is the actual tabulated values of our unknowns. Mind it, it is a time varying problem, but what we reconstruct are just the initial values. We assume it's a state estimation problem for those well versed with that. It's a state and parameter estimation problem. We assume zero process noise. And we are, so we only reconstruct the state and the parameters, and we are getting results. So what we have done is we have introduced a so-called what is called a gradient filter approach. Normally people have heard of the Kalman filter used for state variation, for state estimation. Kalman nonlinear estimation algorithms are there. We have proposed using the gradient of a cost. We set up a cost function, use the gradients rather than the Jacobians. So there is a difference. So that's tremendous of your reconstructions. And main thing, we are using radial basis function based level sets to represent the object. So that reduces our number of unknowns very drastically. And since this is in principle, a 4-dimensional problem, this seems to be a good recipe to go into full-blown 3 dimensions as far as quantification is concerned. Results we have shown are for 2 dimensions. So these are just some, just want to give a flavor of the different types. These are just 2 snapshots of some of the work which we have done at the cutting edge of fluorescence-based optical tomography. So it talks of the physics parts, modeling, as well as the signal processing, reconstruction algorithms part. So this is all I have to say. If there are any questions, I would be happy to take them. Please.
Thank you, Professor Narayan. Nice talk. Now the session is open for questions.
Sir, my name is Pooja and I am a PhD scholar in SRM. So,
yeah.
Am I audible, sir?
Yes, you are audible. You are not visible yet. Can I stop the share? Maybe then I can see people. Yes. Yeah, now I can. Yeah, okay, please.
Yes, sir. So I'm working under photocaustic imaging, but unfortunately, I'm using the photocaustic images. I'm working on image processing.
I'm not able to hear you clearly. Sorry.
It is not audible.
Slightly better. It's breaking, but yeah, slightly better.
Okay, sir. I'm audible, sir, now?
Yes, now better. Definitely better. Yes.
Oh, okay, sir. I'm working on photoacoustic images. So
Okay.
I am using that image enhancement methods. I have recently want to write a paper regarding that. So image enhancement technique applied on photoacoustic images. But right now, what I'm facing the issue is that photoacoustic images or photoacoustic imaging device is not there to capture or what we want. So that is a basic issue I am facing in the first half of my PhD time. So after that, finally, we know about that we don't have the PAI set up in India. So it is available in India.
No. We have setups in India. Please.
Yes, sir. Okay.
There are setups. I think you can definitely setups. I'm a computational guy, so I don't work with the I don't build the experiments, but there are at least, as far as I know, minimum three, if not more. Top of my head, I can say 3. You have Isar Mohali, Samir Biswas has built a whole lab and systems. He has data. and he's working on breast cancer detection systems, which are being clinically evaluated right now. And so he has data 1. I can give you the details if you wish.
Yes.
Then you have, I think there is somebody there is another group at ICER Trivandrum, which is, again, he's developing. I don't know the status right now.
Yes.
Then there is, at least I'm getting 2 more groups also. EPIC, Allahabad. So there are multiple groups which are working. I can give you.
Like I just get the few people, so they are still working on that. So I get the details from that. So right now, I have a question is that if I am working for next is I am working for the reconstruction. So if we have a small image, like if any type of image, so if we want to convert into photoacoustic image, what change I should do in that?
Okay, the main, see, it is like when you say photoacoustic image, there are 2 aspects. One, photoacoustics is a 2-step process.
Yes.
Where first step, your reconstruction is basically what is called the photoacoustic heat source. So you have light which goes in, it is absorbed, and that gives you a first level source, heat source, which conventional algorithms reconstruct only that heat source. Photoacoustics per se does only that. That gives you, then second level is what you have if you want to get the optical parameters out of that heat source. That is the second level reconstruction that you have to do. So your universal back projection algorithm, which is commonly used from pressure data, that gives you the photoacoustic source, which commonly in literature is called the photoacoustic signal.
Yes.
So if that is the image that you are working with, then you need to look at the typical quantities based on simulations. You need to look at the values of your it's like it is mu, your absorption coefficient times the fluence. So those values for the typical tissue case studies you are considering, you have to get those physics numbers out and set up your phantom accordingly. Phantom means your, as you mentioned, your image, right? It's your test image which you want to make it realistic. So to make it realistic, you have to give it those numbers of the photoacoustic signal. Now, if you are looking at if your definition of photoacoustic image is the optical parameter, then you have to give those numbers to your image. And the shape, you can decide the realistic sizes that you'll be working with, because there's always a trade-off between region of interest, which you can reconstruct, depth of penetration, and resolution. It's, right.
Yes,
so these trade-offs would be there. So you have to also figure out how deep you want to go, how big a domain you want to image. These aspects also, typically the experimental setup people will know that there are papers which go into it as well. And these days they are looking at full optical, measurement of pressure signals of the ultrasound. So bandwidth increases tremendously. So when bandwidth increases in your measured signal, your reconstructions also change accordingly. So, but to keep it simple, I would say ensure you get the numbers of your photoacoustic signal. Get those numbers based on simulations of the specific tissue. You have to construct it, do some physics modeling, and get those numbers out.
Yes.
That is what you will need to do.
Okay. Okay. Thank you so much, sir. I will. Sir, can you please share the mail ID to me?
Yeah, sure. I will send the mail ID across. No issue. I'll send my mail ID to the co-chair as well as I can flash it on the screen once the thing is over. I think I should be able to write it on the screen as well. It is Daven AIK, it's already there on my in that. N for November, N for I'll send it across, please. It's
Yes,
okay.
sir. Thank you.
I will
Thank you
send
so
it.
much. Thank you.
Thank you, Professor Naren.
Any other questions? Please feel free to ask.
So we don't have any other questions from the audience. Thank you.
Thank you so much.
Thank you so much for your talk.
Yes. Thanks.
Take care. So now he has to end, right?
Chat can speak.
Renu is our next speaker. Okay, Renuka, can you hear me?
Yes, sir.
So are you the next speaker? Are you talking?
Yeah, okay, sir.
What is the title of your talk? I don't see.
Design insights of NCFET based energy efficient circuits.
Yeah, but I don't see Renuka's talk here. You asked people.
Can you hear my voice, sir?
Yeah, we can hear you, but I don't see your name in the. Are you in the right section?
Sir?
I don't see your title in this current section. Are you in the right section? Is it
VLSI and embedded.
No, this is actually healthcare technologies.
Okay, sir.
I will ask Pradyut Kumar Sankhi to get back to you.
Okay, sir.
You call Pradyut and tell her.
Hello, sir. Am I audible?
Saptarshi, yes. Are you ready to?
Yes, sir.
Okay.
Yes, sir. Yes, sir. I am ready to give my presentation.
Please talk. Please start your talk.
Okay.
You can share your slides.
Okay, sir.
Yeah.
Just a minute. I am having a bit graphics issue with the latest version of the Zoom. That's why a bit.
Take it. Yeah, we can see your slides, Saptarshi. You can start.
Okay, sir. Just a minute, sir. I'm just checking whether it is moving or not. Yeah, it is. Yes, sir. Facing a bit problem. Yes. Sir, am I audible? Sir, can you hear me?
Yeah, you're audible, but we are unable to see your slides.
Okay, now I guess, is it coming? Is it moving, sir, on the screen?
No. Yeah, now we can see your slides.
Okay, sir. Good afternoon, everyone. Myself, Saptarshi Raichaudhuri, a research scholar of Computer Science and Engineering Department in NIT Jamshedpur, Jharkhand. So today, I'm going to present one of my research work, that is the analysis of fingerprint biometric towards deciding on its applicability in e-healthcare systems. So these are some of the contents of this work. So starting with abstract, then introduction, then literature review objectives, and then literature review outcome, then motivation and novelty, problem statement, proposed methodology, experimental result, and conclusion and future work, and then the references. So to start with the e-healthcare system, the e-healthcare system has gained its acceptance during COVID-19 in the countries like India. So the e-healthcare involves with a large amount of data because the patient's records are a very healthy volume data. So large set of users are also the prime part of the e-healthcare systems. Whether the medical data is dedicated and it is need to be secured because it is having a very high security demand. So the biometric based authentication protocols are there as it can very proven authentic to secure any electronic health record. Now, various biometric traits are there, and there might be behavioral biometric, there might be physical biometrics. So they can be used to secure this particular data. Now, between physical and behavioral biometrics, the physical biometrics gained higher popularity in previous by the researchers, while we consider the application area in real-time applications or real-time use cases. Now, this is one simple diagram of a e-healthcare system where we can see the health record acquisition system is there to which acquires the health records, and it is being transferred to the fog layers to the healthcare cloud. And then on as per the demand of the different users, the health records can be accessed from the cloud through the fog layers to the endpoint. So if we can see the health record acquisition system and e-health record portals, both are the edge layers, and this particular edge layer is demanding the authentication security. And here we use the particular biometric authentications. Now, before going into the literature review, we have had some literature review objectives, where the first objective was to examine the availability of fingerprint sensors in the edge devices. As we know, in the modern M-Health or e-health architecture, recently the M-Health architecture has gained so much popularity because the revolution in smartphone technologies, and each and every, most of 99% of the smartphones are having the fingerprint sensors. And next is to examine how the edge becomes a key factor in the case of fingerprint biometrics, because we know the aged peoples are having some problems while producing their fingerprint biometrics. Now, the third objective of literature survey was to examine the age group population calculations for hospital patients data. So that means we have to go through the hospital patients data, and we have to find out that what are the maximum possible age groups who are getting admitted, or who are the main users of the e-healthcare systems. So the literature review outcome, from the literature review, what we have got that fingerprint biometric sensors are widely available through modern smartphones. And the fingerprint biometrics is a very convenient mode of authentication for the users, whereas the fingerprint biometrics also passed major reliability factors based analysis. Not all, but they have passed through majority of those particular analysis. So various surveys and healthcare data shows the highest percentage of the patients belongs to the age group. That means the elderly people. The elderly people are the highest percentage of the e-healthcare users. Now here in the survey that shows also that the age group 0 to 6 years, this is also a very large amount of e-healthcare patients records, this age group. But we consider that in these particular age groups, the child or the baby actually, so the baby is not going to use the e-healthcare system, their parents is going to use the e-healthcare system. So that's why we have discarded that particular factor. Now, the last one was with increasing age, in the survey shows that with increasing the age, the human fingerprint features have become less robust. So that means with the ages, there is some deformation issue in the case of human fingerprints. Now, the motivation of this particular work, while having the high availability, as we have discussed that as with the increasing count of the, or there is increasing research in the smartphone technology, there is high availability of this particular fingerprint sensors. So it is very much available to the users. So when it is very much available, should we use that particular fingerprint based authentication for the e-healthcare system or not? So we have to make a decision on this particular thing. So this is the first motivation of this particular, behind this particular work. And the next one is that when we are having a high availability and usability of this particular fingerprint biometric, in the other hand, we are having the age related issue with the fingerprint biometric, and we are having a high percentage of e-healthcare users are elderly people. So that's why we have to make a comparison between these two to take a decision whether the particular fingerprint biometric should be used for e-healthcare systems or not. Now, to do this, we are having one particular option, that is the multi-criteria decision making. So there can be multiple factors when we have to decide on calculation of the multiple factors. Then we can have this particular procedure, that is multi-criteria decision making approach. And in previous research works, there was no any decisions have been taken on the basis of multi-criteria decision making approach while making a decision on choosing a particular biometric trait for e-healthcare systems. So when we have multiple contrasting factors, we have to decide on a particular factor to use. Then we are going to use this particular analysis, which is multi-criteria decision making. So in this paper, it has been introduced. So this approach is novel because this is the first approach which uses the multi-criteria decision making in terms of deciding the proper biometric trait for e-healthcare systems. So the problem statement, to decide the applicability of the fingerprint biometrics in e-healthcare systems using multiple multiple multi-criteria decision making. Now, what is multiple multi-criteria decision making? We have used multiple multi-criteria decision makings. Why? Because there are 8 different analysis has been done. Now, what are the 8 different cases? The cases are different with the 8 different Likert scale points. So the Likert scale points has been started with 3 and ended with 10. So 3 to 10. So there was 8 different analysis has been done to decide on the applicability of the fingerprint biometrics in e-healthcare systems. Now this is our proposed methodology. First, we have to set the n for the endpoint Likert scale. So we have to decide on the value. Suppose we start with 3, and then we have to assign the weight to every values of n, and then we have to assign the weights to every factors. So that means suppose age is a very critical factor. So we have to give larger weight or heavier weight to the particular age factor. In the other hand, applicability or usability or reliability, these are the factors. So these particular factors should be given appropriate weights to make this particular analysis. Then we have applied the weighted sum model to achieve the analysis outcome. There are several models available in the case of multi-criteria decision making, but as we are not going for the multi-dimensional outcome, our outcome should be unidirectional. So that's why weighted sum model is a simple model and which is a very good previous outcomes for this particular unidirectional outcome. Now, when we have end with a particular starting endpoint Likert scale, go to the starting point for the next endpoint Likert scale. So that means if we have started with 3 for the value of n, so next we'll repeat the process for the value of 4, then 5, and then 6, and up to 10. So the experimental results shows that the Likert scale point when the value of n was 3, the MCDM outcome, that is the multi-criteria decision making outcome, was the outcome has been pointed in a 5-point Likert scale, where 3 is the medium one, and starting with 1 up to 5. So 3 will give us the likely result, and 4 is going to give us the not likely. So, and 5 is going to be not recommended. So this particular, when the Leica scale point was 3, the result was 3. That means we can use the fingerprint biometric, but with the increasing number of Leica scales points. So that means with the increasing values of the, or with the increasing detailing of the features, we can see that it is showing us that the fingerprint biometric is not very much applicable for the e-healthcare systems. Now these variations, how we got, or why this particular variation is coming, because we have given the age as the maximum weight. Because in the literature survey, we have seen that age is having a very greater factor in terms of e-healthcare system, as maximum people are the elderly people. So we have to give the age factor as the highest weighted factor. So that's why this particular outcome we are getting. Now, this is the plot with the MCDM outcome in 5 per Leica scale versus the Leica scale points. So 8 separate analysis outcome has been plotted over here. So conclusion, and as a conclusion, we can get that our objectives has been our objectives or the problems is being solved by using this particular method, because our objective is to find out the applicability of the fingerprint biometric in the case of e-healthcare, and it shows us the fingerprint biometric is not applicable in the case of, or it's not likely applicable in the case of e-healthcare systems. Now, the future work, the analysis has been done by using the weighted sum method, but there are some other method also which is very much good for the unidirectional outcome. So we can use that particular thing in future, and the number of features can be increased, and we have to see whether the outcome is being changed with the increasing number of features. Okay, so these are the 2 future scopes. So these are the some references. So thank you, everyone. Any question?
Good job, sir. That's it.
Yes, sir.
Good job.
Thank you, sir.